and welcome to Pre-Algebra Lesson 24. In this video, we're going to look at some divisibility rules. So our lesson objective for today is just to learn how to determine if a number is divisible by. Then we have the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So essentially, it's the numbers 2 through 12. Now we're going to hold off on this number 7 and this number 11 until the very end, because the divisibility rules for 7 and 11 are a bit more time consuming. I'm not going to say they're complex, but they're more time consuming than the other ones. So what does it mean when we say a number is divisible by another? So a number is divisible by another if the result has no remainder. So for example, 25 is divisible by 5. So 25 is divisible by 5 because 25 divided by 5 is 5 and it does not have a remainder. 30 is divisible by 3 because 30 divided by 3 is 10 with no remainder. If I look at something like 19 divided by 4, is 19 divisible by 4? Well, no, it's not. If I take 19 and I divide it by 4, I'm going to get 4 with a remainder of 3. So because there's a remainder involved, 19 is not divisible by 4. So when we have a number that is divisible by another, the result has no remainder. So what we're going to do is we're just going to look at the divisibility rules. I'm going to do 2 through 12, and we're going to exclude 7 and 11 until the very, very end. The ones 2 through 12, excluding 7 and 11, are very, very easy. You just need to write them down as you go. You will memorize them as you practice, and then eventually you won't need your paper anymore. So let's begin by looking at divisibility by 2. So a number is divisible by 2 if it is even. So we've briefly kind of talked about even numbers, and I kind of gave you the definition of even and said that a number is even if it's divisible by 2. Well, yeah, that's true. But kind of the shortcut is the final digit is a 0, 2, 4, 6, or 8. That's the way you can tell if something's going to be even and therefore divisible by 2. Now, if you looked at, let's say, the first 10 numbers, you can see the pattern. If you look at 0, 2, 4, 6, 8, and 10, those are the even numbers here. The other numbers, and let me change the color here, 1, 3, 5, 7, and 9, those are called odd numbers. So if a number is not even, it's odd. So they alternate. You go even, then odd, then even, then odd, then even, then odd. And that's just how it goes forever and ever and ever. So again, for divisibility by 2, you're looking at the final digit of the number. If it's a 0, 2, 4, 6, or 8, then it is automatically divisible by 2. It is an even number. So for divisibility by 3, the sum of its digits is divisible by 3. And if you don't get it at first, the first time you add the digits, you say, well, I don't know if this is divisible by 3. You can keep adding digits. You can keep going until you find out, hey, is this number divisible by 3? For divisibility by 4, the final 2 digits of the number forms a number that is divisible by 4. For divisibility by 5, the final digit is a 0 or a 5. For divisibility by 6, the number is divisible by both 2 and 3. So for divisibility by 8, it's similar to the rule that we had for divisibility by 4. So the final 3 digits of the number forms a number that is divisible by 8. Then for 9, it's similar to the rule for 3. So the sum of its digits is divisible by 9. And just like we saw with 3, when we're checking for divisibility by 9, if we form the sum of the digits and we don't recognize whether that sum is divisible by 9, we can take that sum and we can sum the digits again. For divisibility by 10, the number ends with a 0. And then finally, for divisibility by 12, the number is divisible by both 3 and 4. All right, so let's get some practice going. So we want to determine whether each number is divisible by 2, 3, 4, 5, or 6. So I'm starting with the number 232. So is it divisible by 2? Is it divisible by 2? Well, a number is divisible by 2 if it's even. And again, I told you that a number is even if the final digit is a 0, 2, 4, 6, or 8. The final digit here is a 2, so this number is even. So yes, it's going to be divisible by 2. Now let's check divisibility by 3. So a number is divisible by 3 if the sum of its digits is divisible by 3. So what I would do is I would go through and say, okay, what is 2 plus 3 plus 2? 2 plus 3 is 5. 5 plus 2 is 7. So you would then ask yourself, if I divide 7 by 3, would I have a remainder? And yes, you would. 7 divided by 3 is 2 with a remainder of 1. 2 with a remainder of 1. So 7 is not divisible by 3, and therefore 232 is not divisible by 3. What about 4? So a number is divisible by 4 if the final two digits of the number forms a number that is divisible by 4. So just look at the final two digits of the number. Just think about only those two digits. So the number 32. Is that divisible by 4? Well, yes, it is. 32 divided by 4 is 8 with no remainder. So this would be a yes. Then what about 5? A number is divisible by 5 if the final digit is a 0 or a 5. So if I look at the final digit here, it's a 2. That's not a 0 and it's not a 5. So the answer would be no. And then lastly, we want to ask, is it divisible by 6? Well, a number is divisible by 6 if it's divisible by both 2 and 3. So 232 we found earlier is divisible by 2, but it's not divisible by 3. So if it's not divisible by both 2 and 3, it will not be divisible by 6. So this is a no. Okay, for the next one, we're looking at the number 93. And again, we're doing 2, 3, 4, 5, and 6. So for the number 2, remember, we're looking at, is it an even number? Meaning, does it end in 0, 2, 4, 6, or 8? This ends in a 3. 93 is an odd number. It's not even. It doesn't end, again, in a 0, a 2, a 4, a 6, or an 8. So it's not going to be divisible by 2. This is a no. What about 3? Well, to be divisible by 3, the sum of the digits for the number would be divisible by 3. So you do 9 plus 3, that's 12. 12 divided by 3 is 4 with no remainder. So therefore, because the sum of the digits, which is 12, is divisible by 3, the number 93 is divisible by 3. So this is going to be a yes. This is a yes. Now next, is this number divisible by 4? Now generally, you're going to ask, okay, the final two digits of the number forms a number that is divisible by 4. But we only have a two-digit number here. So we have to think about another trick. Now, one of the things I'm going to teach you, and you'll understand why in the next lesson, 4 is built from 2 times 2. So for that reason, if a number is not divisible by 2, if a number is not even, it will not be divisible by 4 automatically. So we don't need to go through and say, okay, 93 divided by 4, is there going to be a remainder? 93 is an odd number. There is no odd number that's going to be divisible by 4. And so this is going to be no. Next, we look at 5. So for a number to be divisible by 5, the final digit is a 0 or a 5. Here, our final digit is a 3, so this is going to be a no. And then the last one, is this number divisible by 6? A number is divisible by 6 if it's divisible by both 2 and 3. So we got a yes on 3, but a no on 2. So it's not going to be divisible by 6. So no. All right, let's look at one final problem, and then we'll look at some practice problems that deal with 8, 9, 10, and 12. So what about 300? So again, we're working with 2, 3, 4, 5, and 6. So is it divisible by 2? Well, yes, it is. When your final digit is a 0, it tells you it's an even number. And for divisibility by 2, we need the number to be even. What about 3? Well, you can see that that's yes right away, because if you sum the digits here, 3 plus 0 is 3. 3 divided by 3 is 1, no remainder. So that's a yes as well. What about 4? You look at the final two digits of this number. Now, you might find it odd. You see 0, 0. You say, well, what number does that form? It just forms 0. So basically, you're saying, is 0 divisible by 4? Well, yes, because 0 divided by anything other than 0 is 0 with no remainder. So this is 0, no remainder. So because it doesn't have a remainder, you can say that yes, 300 is divisible by 4. So this is a yes. Then what about 5? Again, for 5, we're looking at the final digit of the number. And in this case, it is a 0. So yes, if a number is divisible by 5, it's going to have a final digit of a 0 or a 5. So this is a yes as well. And then lastly, for 6, we know that that's a yes because we just look at what we've already done for 2 and 3. Those are both a yes, so this is a yes. Right? For a number to be divisible by 6, it needs to be divisible by both 2 and 3. And in this case, it is. Okay, now we're going to look at 8, 9, 10, and 12. So determine whether each number is divisible by 8, 9, 10, or 12. All right, so we have 918. Again, we're working with 8, 9, 10, and the number 12. So the rule for 8 is that the final 3 digits of the number forms a number that's divisible by 8. Now, that's not really going to help us here because we have a 3-digit number. One of the things you can kind of think about is 8 is built out of 2 times 2 times 2. So if it's not an even number, which in this case it is, so if you had something like 917, you could just say no, right? That's an odd number. It's not even. It's not divisible by 2. So you could just say no right off the bat. But in this case, we do have an even number. So we really just have to check it by doing a long division. So we'd say 918 divided by 8. 8 goes into 9 once. 1 times 8 is 8. Subtract, you get 1. Bring this down. 8 goes into 11 once. 1 times 8 is 8. Subtracting, you get 3. Bring down the 8. 8 goes into 38 how many times? Now here's where you could stop because 8 times 5 is 40. That's too big. 8 times 4 is 32. So you know you're going to have a remainder, right? 4 times 8 is 32. I get a remainder of 6. So it didn't divide evenly, meaning we had a remainder. So we know that the answer here is just going to be no. So this is no. What about divisibility by 9? Well, that's a similar rule to 3. The sum of the number's digits will be divisible by 9. So we just sum this. 9 plus 1 is 10. 10 plus 8 is 18. Think about 18 divided by 9. That's 2 with no remainder. So this one's going to be yes. This will be yes. Then what about 10? So the rule for 10 is you look at the final digit, and if it's a 0, it's going to be divisible by 10. If it's anything else, it's not. So because this is an 8 for the final digit, so the answer is no. So what about 12? Well, for 12, we look at the fact that it needs to be divisible by both 3 and 4. Okay, 3 and 4. So we don't know if it's divisible by 4 yet because we haven't checked that. But for 3, if something's divisible by 9, it's automatically divisible by 3 because 9 is 3 times 3. So we got a yes on the divisibility by 3. Is it divisible by 4? Look at the last 2 digits of this number. If I had 18 divided by 4, would I get a remainder? Well, yes, I would. 18 divided by 4 is 4 with a remainder of 2. Right? If I did 18 divided by 4, 4 goes into 18 4 times. 4 times 4 is 16. Subtracting, you get 2. So 4 with a remainder of 2. So this one is going to be no. And again, although it's divisible by 3, it's not divisible by 4. And so because it fails that one, it's not divisible by 12. Okay, what about 16,299? So again, let's look at 8, 9, 10, and 12. So the number is not even. The final digit is a 9. So it's not an even number. It needs to end in a 0, a 2, a 4, a 6, or an 8 to be even. So because it's not an even number, it's not divisible by 2, so there's no way it's going to be divisible by 8. So this is a no. What about the number 9? Well, for 9, we sum the digits. So we have 1 plus 6, that's 7. 7 plus 2 is 9. 9 plus 9 is 18. 18 plus 9 is 27. So 27 divided by 9 is 3 with no remainder. This is a yes. What about 10? A number is divisible by 10 if the final digit is a 0. In this case, our final digit is a 9. So we're going to put a no there. A number is divisible by 12 if the number is divisible by 4 and 3. although it would be divisible by 3, again, if a number is divisible by 9, it's automatically divisible by 3, it's not going to be divisible by 4. And the reason for that is it's an odd number, right? If it's not divisible by 2, it can't be divisible by 4. So this is an automatic no. All right, we'll look at one last one, and then we're going to talk about the rules for 7 and 11. So here we have 10,800. Let me kind of change the colors up. So we have 8, 9, 10, and 12. So for 8, again, we look to see, first and foremost, is it even? And yes, it is, right? It ends in a 0. And then we can look at the final 3 digits of the number. That's 800. Is 800 divisible by 8? Well, yes, it is. And that should be easy for you because 800 divided by 8, you can pretty much do that in your head. That's 100, right? Because 100 times 8 would be 800. So we know that this would be a yes. Next, we look at 9. So we would add here. 1 plus 0 is 1, plus 8 is 9, plus 0 is still 9. Now, 9 divided by 9 is 1 with no remainder. So this would be a yes as well. Then what about 10? Look at the final digit of the number, and it's a 0. So this is yes. And then what about 12? Well, we know it's divisible by 3. If a number is divisible by 9, it's automatically divisible by 3. So that part checks out. But what about 4? The final 2 digits of the number would form the number 0. 0 divided by 4 would be 0 with no remainder, so it's divisible by 4. So the answer here would be yes. Because it's divisible by both 3 and 4, it is going to be divisible by 12. Okay, so what about the rules for 7 and 11? So I'm going to tell you the rules for 7 and 11, a lot of teachers just skip them over because they can be a little confusing. But in all reality, if you practice them, just like anything else, it's not that hard. So for 7, there's some steps you need to follow. The first thing you're going to do is remove the last digit from the number. Then you're going to take the number you removed and double it. Subtract this away from the shortened original number. And I put here that we may need to repeat the process a few times. Sometimes you have a large number and you'll do it once or twice and you just don't know if it's divisible by 7 yet. So you just keep going until you have a single number left and you can say, okay, is it 7? Or you can have a multi-digit number like 14 and say, okay, well, 14, I know that's divisible by 7. All right, so let's practice. Determine if each number is divisible by 7. All right, so we have 26,411. Now, the first thing I'm going to do is I'm going to remove the last digit from the number. So basically just think about it as I'm cutting this number off and I'm turning the number into 2,641. That's my new number. Now the number that I cut off, what I'm going to do is I'm going to double it, meaning I'm just going to multiply it by 2. So 1 times 2 is 2. And then I'm going to subtract it away from this shortened number. So I'm going to subtract away 2. Now what am I going to get? Well, I need to borrow here. 11 minus 2 is 9. Bring down the 3, bring down the 6, bring down the 2. Does anybody know if 2,639 is divisible by 7? I sure don't. So you would continue, right? You would just do the same thing. So now I'm going to go, okay, 2,639, cut off the last digit, bring that guy over here. I have 263 now as my shortened number, and I'm going to double 9. So I multiply it by 2. 9 times 2 is 18. So 9 times 2 equals 18. And I'm going to subtract that away from 263. So I'll borrow here. This becomes 5. This becomes 13. 13 minus 8 is 5. 5 minus 1 is 4. Bring down the 2. I have 245. I still don't know if this is divisible by 7, so I'm going to continue. I'm going to bring this over here. I have 245. Cut off the last digit. That's a 5. And so that leaves me with a shortened number of 24. Double 5. 5 times 2 is 10. Subtract that away from 24, and I get 14. So now I do have a number, and I know if it's divisible by 7. 14 divided by 7 is 2 with no remainder. So after going through this process, I can see that my original number, which is 26,411, is in fact divisible by 7. Okay, let's try another one. We have 6,480. And essentially what we want to do here, again, is just chop off the final digit. So I'm going to write this number as 648. And then I take that final digit and I double it. So what happens if I take 0 and I multiply it by 2? I get 0. So I could say 648 minus 0 if I wanted to, but we all know that's 648. So I continue. I chop off the final digit of the number again, and I'll have 64. And I'll take this over here, and I'll say, what is 8 times 2? Right, you're going to double it. 8 times 2 is 16, and we'll subtract that away. 14 minus 6 is 8. 5 minus 1 is 4. So I have 48 now, and I can already tell that 48 is not divisible by 7. And I know that through my multiplication tables. If I think about 48 divided by 7 equals what? Work backwards. What times 7 equals 48? Well, I know that 6 times 7 is 42. 7 times 7 is 49. That's too big. So I don't have a whole number here that's going to work, and so I'm going to have a remainder. Right? So I know that 48 is not divisible by 7, and therefore this number 6,480 is not going to be divisible by 7 as well. Okay, so let's look at the rule for 11 now. 11 is less complicated, but it's still more complicated than the rules that we looked at earlier. So the first thing you do is you find the sum of the digits in the odd places and subtract away the sum of the digits in the even places. And I'll show you how to do that in the example. Then the next thing is that if the result is a 0 or a number that is divisible by 11, then the original number is divisible by 11. So let's look at some examples. Determine if each number is divisible by 11. So what you'll do, if you get this on a test, just go through, starting at the leftmost number, and say, okay, this is position 1, then 2, then 3, then 4, then 5. So remember the difference between odd and even. An odd number would be something like 1, 3, 5, 7, 9, so on and so forth. An even number is a number that ends with 0, 2, 4, 6, or 8. So 2, 4, and then if we had a 6th digit, an 8th digit, something like that, we'd have even. So I want to start by just forming the sum of the digits in the odd places. So 9 plus 7 plus 0. So 9 plus 7 plus 0. Then I'm going to subtract away the sum of the digits that are in the even places. So we'd have 0 and then 2. So 0 plus 2 is 2. 0 plus 2. So 9 plus 7 plus 0 is 16. 0 plus 2 is 2. 16 minus 2 is 14. 14 is not divisible by 11. 14 divided by 11 is 1 with a remainder of 3. So this number, 90,720, is not divisible by 11. All right, let's look at 361,152. And again, we're going to start by labeling it. So the leftmost digit of the number, we're going to say that's in position 1, then 2, then 3, then 4, then 5, then 6. And what we're doing is we're going to sum the digits in the odd places. So the digits that's in the position of 1, 3, and 5. So 3 plus 1 plus 5. 3 plus 1 plus 5. And it's just a coincidence that the digits that's in the 5th position happens to be a 5. I know that can be confusing, but that's a coincidence. Now we're going to subtract away the sum of the digits that are in the even places. So in this position of 2, 4, and 6. So 6 is the number in the 2nd position, plus 1, which is the number in the 4th position, plus 2, which is the number in the 6th position. So again, 6 plus 1 plus 2. So 3 plus 1 is 4, 4 plus 5 is 9. Subtracting away, 6 plus 1 is 7, 7 plus 2 is 9 as well. So when we do this subtraction, we get 0. Now remember, we said that it would be divisible by 11 if the result was a 0 or divisible by 11. Here we got a result of 0, so that tells me that this number, 361,152, is in fact divisible by 11.
Hello and welcome to Pre-Algebra Lesson 25. In this video, we're going to learn about factoring whole numbers. So the lesson objectives for today, we want to learn how to determine if a whole number is prime, composite, or neither. And additionally, we want to learn to write a whole number as the product of prime factors. All right, before we get into factoring whole numbers, let's think about the concept of a prime number. So we have that a prime number is a whole number larger than 1 that is only divisible by itself and 1. So first, let's think about the whole numbers again. So we've talked about these a lot in this course. So let me write out the whole numbers here. And then basically I'm going to start with the smallest whole number, which is 0. And then we increase in increments of 1. So next comes 1, then 2, then 3, then 4. And of course, at some point we have to stop. We can't list all the whole numbers. So I'm going to put a final comma and then the 3 dots here to show that the pattern continues forever. When we think about this definition, a prime number is a whole number larger than 1. So automatically, I've got to go into these numbers here, and I've got to basically say, okay, I'm only looking at the whole numbers, starting with 2 and going to the right, or starting with 2 and anything that's going to be larger. So it has to be divisible by only itself and 1. We know that every non-zero number is divisible by itself. So a non-zero number divided by itself will always give you 1. So 2 divided by 2 is 1, no remainder. We also know that every number is divisible by 1. If you divide a number by 1, you just get the number. So for example, 13 divided by 1 is 13. So when I think about, let's say, the number 2, that's going to be a prime number because it's only divisible by itself. 2 divided by 2 is 1, and 1. 2 divided by 1 is 2. In each case, you get no remainder, but there's nothing else you can really do with the number 2. So for that reason, 2 is a prime number. And we're going to find that 2 is the only even prime number. So that's really important. Any even number larger than 2 is going to be divisible by 2 and therefore not a prime number because it would be divisible by something other than the number itself and 1. All right, it might be extremely helpful to memorize the first few prime numbers. So I have here the first 10 prime numbers. We have 2. That's the smallest prime number. And then we go to 3, 5, 7, 11, 13, 17, 19, 23, and then 29. So that's the first 10. There's an infinite number of prime numbers, and how many you want to memorize is up to you, but just doing the first 10 will greatly speed up your work in many cases. All right, so how can we check to see if a number is prime? So we're going to use the divisibility rules up to the square root of the number. All right, let's briefly touch on the concept of a square root again. So something like the square root of 64 is equal to 8 because 8 times 8 is 64. When I ask for the square root of a number, remember there's 2 different notations. The first one is the principal or positive square root of, in this case, 64. I am asking for what positive number, when multiplied by itself, gives me this, what we call radicand, or number under the square root symbol. Since 8 times 8 is equal to 64, the square root of 64 is equal to 8. And again, this is the principal or positive square root. If you want the negative square root, you need this notation here. So this is the negative of the square root of 64, and that equals negative 8. So this is asking for what negative number, when multiplied by itself, gives me the radicand, or number under the square root symbol. So since negative 8 times negative 8 is going to give us positive 64, the negative square root of 64 is going to be negative 8. So in this lesson, I'm only going to ask for the principal square root, so don't worry about this negative answer here. So if I asked you for something like the square root of 4, you're just going to answer 2. If I said, what is the negative square root of 4, which I'm not going to do in this lesson, that would be negative 2. Now, the reason it's important to understand about square roots, when we look at the factors of a number, and of course, this is just going to be with positive factors, we would have something like for 64, 1 times 64, then 2 times 32, then 4 times 16, then 8 times 8. Now, 8 is the square root. And what's going to happen is after this, you're going to have factors, but they're going to repeat. So in other words, the next one would be 16 times 4. Then you would have 32 times 2, and then you'd be back to 64 times 1. So this one right here and this one right here, those are just reversed in terms of the order. Same thing for this one, and then this one and this one. So you basically have duplicates after you hit the square root of the number. Now, in most cases, you're not going to get an integer answer when you take the square root of a number. So we're going to talk about that here. All right, so what if I asked you, is 103 a prime number? So to figure this out, we would need to use our divisibility rules up to the square root of 103. But you might stop for a minute and say, well, what is the square root of 103? I know that something like the square root of 100 is equal to 10, because 10 times 10 gives me 100, or here I've written that 10 squared is 100. Then the square root of, let's say, 121, I know that's 11, because 11 times 11 is 121. When we think about a number like 100, or 121, it's called a perfect square. So a perfect square is a number that can be formed as, let's say, an integer times itself to give you that number. So here, 100, we could form it as 10 times 10, or you could also do negative 10 times negative 10, but let's not worry about that for right now. Then for 121, we could do 11 times 11. So that's why it's a perfect square. Later on, you'll hear about something called rational numbers, and you will extend that definition to say that a perfect square is any number where you could basically take a rational number and multiply it by itself to get the number. But in this case, we're just dealing with integers, so we're just going to go with a simpler definition. Now, 103 is not a perfect square. There's no integer that I can multiply by itself to get 103. So if I say, what is the square root of 103? I'm kind of stuck. But really what you would want to think about is 10 squared is 100 and 11 squared is 121. Well, okay, this number right here is between these two perfect squares. In other words, writing this as an inequality, I could say 103 is greater than 100 and it's less than 121. So if I take the square root of 103, it should be greater than the square root of 100 and less than the square root of 121. Let me actually get rid of this for right now. So if I think about this, I'm just going to drag this up here. This would be that 10, which is the square root of 100, is going to be less than the square root of 103, whatever that ends up being, which is less than the square root of 121, which is 11. So just thinking about this, I can say, okay, well, this would be 10, and I know we haven't gotten to decimals yet, 10 point something. Okay, so it's going to be between 10 and 11. I don't really care what comes after that decimal point. I only care that it's going to be between 10 and 11, and I'm just going to go with that lower integer value. So I'm just going to go with 10. So I would check up to that. If you're lucky and you can use a calculator and you punch this in, you would get about, and I'm going to round this to the nearest hundredth, and we haven't talked about that yet, but I'm just going to put 10.15. So we haven't talked about decimals. We haven't talked about rounding decimals. Just trust me for right now that this is the answer. So it's about 10.15. You can see that that would be greater than 10 and less than 11, but you really don't need any knowledge of decimals. You're just going to, if you're using a calculator, cut this part off and just take that whole number. Just take that 10 and you're going to check up to whatever that is. Okay, so now that we've established that we're going to check up to 10, we can just run through the divisibility rules. For this one, it's going to be actually pretty quick. So we know that this is an odd number, so immediately you can mark out 2, 4, 6, 8, and 10. Then when you think about divisibility by 3, you sum the digits. So 1 plus 0 plus 3. 1 plus 0 is 1, plus 3 is 4. So you think about, is 4 a number that's divisible by 3? No. 4 divided by 3 would give you 1 with a remainder of 1. So because there's a remainder there, you can mark this out. And then if a number is not divisible by 3, it can't be divisible by 9, so mark that out. So now we're left with 5, which is pretty easy, and then 7, which is a little bit tricky. So 5, you just look at the last digit of the number. Is it a 0 or is it a 5? In this case, it's a 3, so 5 is out. So cross that out. And then we think about 7, which is the most challenging. We would think about cutting off the final digit of the number. So in this case, that's 3. So you just cut it off. And then basically over here, I'm going to double it. So 3 times 2. And you're going to subtract that away. So this would be what? 3 times 2 is done first. So that would be 6. So you get 10 minus 6, which gives you 4. So if this number is 0, or some number that's divisible by 7, then basically the number you were working with is divisible by 7. Here, this is a 4, so that's obviously not 0, and it's not going to be divisible by 7. So this will not be divisible by 7. So let's go ahead and say that this number, 103, is a prime number. Now you can see how much work it is to actually go through and check and see if something is prime. So in most cases, your teacher is going to give you something from a list that you've already memorized. But in case you get something that's not, you can go through and use this strategy to determine if something is prime. All right, now let's think about a composite number. So a composite number is a whole number that is greater than 1 and is divisible by a whole number other than itself and 1. So when we say it's a whole number that is greater than 1, again, it's the same numbers that we're working with. We write out the whole numbers, and then basically we start with 2, and then we move to the right on that list, or you say anything that's 2 or larger, that's what you're thinking about. So it's got to be divisible by a whole number other than itself and 1. So here are the first 10 composite numbers. So when you look at 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18, notice that 4, 6, 8, 10, 12, 14, 16, and 18, those are even numbers. Again, they are automatically going to be divisible by 2 because they're even numbers, so they can't be prime numbers. They're automatically going to be composite numbers because they are divisible by some whole number other than itself and 1. So now looking at the other ones, we have this 9 here. 9 is divisible by 3. You have 15. 15 is divisible by 3 and also 5. And that's pretty much it for the first 10 composite numbers. Obviously, there's an infinite number of composite numbers, just like there was an infinite number of prime numbers. You can't memorize all of them, so you just have to go through the strategies to determine if you have something that's prime or composite. All right, now on your test, you might be asked about 0 and 1. Remember, in the definition for a prime number and also in the definition for a composite number, we specifically said it was a whole number larger than 1. So basically, we're starting with 2 and we're looking for anything larger. So what about 0 and 1? The numbers 0 and 1 are not prime, so they're not prime, and they're also not composite. If you get that question on a test, they are neither. Okay, you want to put that down. They are neither. They're not prime and they're not composite. All right, let's run through a few of these. So we want to determine if each number is prime, composite, or neither. We're going to begin with 123, and coming down here, you see that I have some numbers listed here. So starting with 2 and then going up to 11. So why did I stop with 11? Remember, we only need to check up to the square root of the number. Now, in this particular case, 123 is not what we call a perfect square. There's no rational number, or some books will say integer, that multiplies by itself to give you that number. So when I have this situation, I'm going to think about the fact that 11 squared is going to be 121. And then 12 squared is going to be 144. So these are things that I know. If you don't, you can do a multiplication. So if you're not using a calculator, you're just going to think about the fact that, okay, well then the square root of 121 is 11, and then the square root of 144 is going to be 12. Well, this number 123 is going to be between those two numbers. In other words, 123 is greater than 121 and less than 144, so then the square root is going to be somewhere between 11 and 12. I don't actually care where it is because I'm just going to go down to 11, right? So I only have to check up to 11. If your teacher is nice, then it's a lot quicker. You can just say, what is the square root of 123 in your calculator? And we're going to approximate this. And I get, if I round to the nearest hundredth, about 11.09. Okay, so about 11.09. And again, just cut this part off. Just get rid of this and just take the whole number part. And basically, I'm going to check up to 11. That's all you need to do. So looking at this, I know that this is an odd number. So immediately, it's not going to be divisible by 2 or 4 or 6 or 8 or 10. Okay, get rid of that right away. Then when I think about 3, well, this number you would sum the digits. 1 plus 2 is 3. 3 plus 3 is 6. Well, yes, 6 divided by 3 is 2, no remainder. So yeah, immediately I know this is a composite number. So this is a composite number. What about the number 51? Again, if I'm thinking about the square root of 51, if I'm lucky and I have a calculator, well, I would say that's about 7.14 if I round to the nearest hundredth. So I only need to check up to 7. Again, if you don't have a calculator, then just think about the fact that 7 squared is 49, and then 8 squared is 64. So if you think about this, get rid of this for a moment, we know that 51 is greater than 49 and less than 64. So that means when I take the square root of 51, I'm going to get something that's between 7 and 8. I don't actually care what it is. I know that I'm just going to go down to 7. So checking this, I need to look at 2, 3, 4, 5, 6, and then 7. So just going up to 7. This number's not even, so you can immediately get rid of 2, 4, and 6. And then just think about, is it divisible by 3? 5 plus 1 is 6. 6 divided by 3 is 2, no remainder. So yeah, this is going to be a composite number. All right, what about 59? So again, I can take the square root of 59 in my calculator if I'm lucky, and that would give me about 7.68 if I round to the nearest hundredth. Or if I don't have a calculator, I can think about the fact that 7 squared, again, is 49, and then 8 squared is 64. So the square root of 59, because, again, 59 is greater than 49 and less than 64, it's going to be between 7 and 8. Again, I don't care about this 0.68 part. I only care about the whole number, so I only care about that 7, just going down. So I want that 7 there, so I only want to check up to 7. This is not an even number, so I can get rid of 2, 4, and 6. Think about 3. 5 plus 9, that's going to be 14, so you can get rid of 3. 14 is not divisible by 3. Now for 5, again, the final digit has to end with a 0 or a 5. This does not end with a 0. If it did, it would be an even number. And it does not end with a 5. So let me get rid of that. So now we have to check 7. For that one, we know the rule is a bit complicated. It might actually be quicker to just do a division. But what you do is actually cut off the final digit of the number and you double it. So 9 times 2. And you subtract that away. So basically 9 times 2 is 18. So this would give me 5 minus 18. And this would give me negative 13. And forget about the fact that it's negative. Just say, is 13 divisible by 7? The answer is no. So you can cross this out. And then we can conclude that 59 is going to be a prime number. So it's only divisible by itself. So 59 divided by 59 is 1. And then also 59 divided by 1 is 59. All right, now let's actually move into factoring whole numbers. So I'm going to start off with a basic definition that of course we already know, but I want you to recall that 2 or more numbers that are multiplied together are known as factors. So in this multiplication problem, 3 times 5 equals 15. The 3 and the 5 are known as factors. They're being multiplied together. The 15, the result of the multiplication operation, is the product. Then 8 times 7 equals 56. The 8 and the 7 are the factors. The 56 is the product. So when we have factors that are prime numbers, they are known as prime factors. Now, a lot of times you're going to be asked to find the prime factorization of a number, and that just means you're going to break the number down into the product of prime factors. So I have here that it is often useful to write a number as the product of prime factors. We're going to have a lot of operations moving forward that are going to depend on this knowledge. So I have here to write a number as the product of prime factors. We continue to factor each factor until it's prime. So I'm going to start off with this 80 here, and then I'm going to show you how to do this with a factor tree, which is a great way to visually organize your work. So here I have, let's try to write 80 as the product of prime factors. So I'm just going to start off with 80 is equal to, just pick any 2 numbers other than itself and 1. So I'm not going to pick 80 and 1. I'm going to pick something like, let's say 8 and 10. So 8 times 10. And then just keep breaking these numbers down. So 8, I know that's 4 times 2. 2 is a prime number. And then times, for 10, I'm going to put 5 times 2. So 5 is prime and 2 is prime. But I can break 4 down and say that's 2 times 2. So then times 2 and then times, let me reverse the order here. So put 2 there and then times 5. So what do I have? I have 1, 2, 3, 4 factors of 2. So let's say this is 2 to the 4th power. And then times 1 factor of 5. So 2 to the 4th power is 16, and 16 times 5 is 80, right? So we've basically broken this down into the product of prime factors. And again, you're going to need to do this a lot moving forward. So this is the process you could use. Using a factor tree is generally a little bit better because it helps you to organize your work. This right here is kind of a mess and not organized. So in order to use a factor tree, you want to write the number to be factored and extend 2 lines below. So these lines that you're extending below, they're going to basically be called branches. Then you want to list any 2 factors of the number. So then other than the number itself and 1, and you're going to place each under one of the lines or what we call the branches. Then we're going to circle any prime factors. And for any factors that are not prime, we just repeat the process. So you're going to extend 2 branches, list any 2 factors other than the number itself and 1, and then you're going to circle the prime factors. So I have here, this continues until all factors are prime. Okay, let's look at some examples. We will look at 80 again using a factor tree. So let me write 80 here, and then these are going to be my branches. So you can do anything other than the number itself and 1. So before we did 8 and 10, let's change that up and do 16 and 5. So now, once you've listed 2 factors, check to see if one of them is prime. 5 is prime, so you're going to circle it and you're going to stop. For 16, it's not prime. I could say this is 4 times 4, and then you're going to check neither of those is prime. And so this is 2 times 2, and then this is 2 times 2. And so you're going to circle these. So this, 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 and this, those are all prime numbers. So this gives me that 80 is equal to 1, 2, 3, 4. So 2 to the 4th power times 5. Now let me do this a different way just to show you that you get the same result. Let's say I didn't start with 16 and 5. I could have done 8 and 10. So let's say I do 8 and 10. And so this, neither of those is prime, so I'm going to go 5 and 2. 5 and 2 are both prime, so I'm going to circle and stop. And then for 8, let's go with 4 and 2. And then 2 is prime, so circle that and stop. And then for 4, it's 2 times 2, so circle those and stop. So basically you get 2 times 2 times 2 times 2, which is 2 to the 4th power, and then times 5. So same thing either way. Let me just do it one other way just to show you that it doesn't really matter. So I'm going to go 4 and 20. Okay, so 4 is 2 times 2, and we're going to stop, right? So this is prime and this is prime. 20 is 4 times 5. 5 is prime, so we're going to stop. Then 4 is 2 times 2, circle those and stop. So no matter how you do this, you end up with 2 times 2 times 2 times 2, which is 2 to the 4th power, times 5. Okay, let's look at 95. So 95. So for this one, you might think about, okay, how do I get started? 95 is not something I really work with that often. If you notice the number ends with a 5, you know it's divisible by 5. So I would come over here, if you don't have a calculator, and just do a quick long division. 5 goes into 9 once. 1 times 5 is 5. Subtract 9 minus 5 is 4. Bring down this 5 here. 5 goes into 45 9 times. 9 times 5 is 45. Subtract and you get 0. So I could do 19 and then 5. So let me get rid of this. And we know 5 is a prime number. What about 19? Well, I did list this as one of the first 10 prime numbers. If you didn't know that, again, you can go through the process we talked about earlier in the lesson, and you could check and confirm that this is a prime number. So this right here, 95, would be equal to 19 times 5. What about 240? 240. So if a number ends with a 0, it's divisible by 10. Usually that's the easiest to start with. So I'll just say this would be 24 times 10. So then from here, I know that neither of these is going to be prime. So this right here would be 5 times 2. Circle these. 5 and 2 are both prime. For 24, a lot of different things you could do. You could do 4 and 6. You could do 8 and 3. You could do 12 and 2. Whatever you feel like. Let's just go with 4 and 6. So neither of those are going to be prime. So 6, I'm going to do 3 and 2. And this is going to be 2 and 2. Let me circle this and this and this and this. All of those are prime. So 240 would be equal to 1, 2, 3, 4 factors of 2, so 2 to the 4th power, and then times, you've got 1 factor of 3, and then times, you've got 1 factor of 5. Now, let's say, just for the sake of completeness, I get rid of this, and I would have started with, let's say, 20 times, let's say, 12. I'm just showing you it doesn't matter how you start. So 20 and 12, neither one is prime. This one, you could do 5 times 4, 5 is prime, 4 is 2 times 2, 2 is prime, and 2 is prime. 12, you could do 4 times 3. So 3 is prime, 4 is 2 times 2. And again, you get 1, 2, 3, 4 factors of 2, 1 factor of 3, 1 factor of 5. So it doesn't matter what you start out with. Just pick any 2 factors other than the number itself and 1, and you're going to be good to go. Just keep going down and breaking each number down this way. All right, what about 126? So this number, it's an even number, so I know it's divisible by 2. And then 1 plus 2 is 3, plus 6 is 9. So that tells me it's divisible by 3 and also 9. But because it's divisible by both 2 and 3, it's going to be divisible by 6. Let me do that off to the side. So 126 divided by 6. 6 does not go into 1, but it will go into 12 twice. 2 times 6 is 12. Subtract, you get 0. Bring down the 6. 6 goes into 6 once. 1 times 6 is 6. Subtract, and we get 0. So basically, you could do 21 times 6. So this would be 21 and 6. Now 21 and 6, neither of those is going to be prime. 6 is going to be 3 times 2. Let's circle these. 3 and 2 are both prime numbers. 21 is 7 times 3. Let's circle those. 7 and 3 are both prime numbers. So let's say 126 would be equal to, let's go 1 factor of 2, and then times, we have 2 factors of 3. So let's say 3 squared, and then times 1 factor of 7. All right, what about 828? So it's kind of a big number. I know it's an even number, but I would look at the last 2 digits here. This is a 28, so this number is going to be divisible by 4. And I would also check and see if it's divisible by 3. 8 plus 2 is 10. 10 plus 8 is 18. So it will be divisible by 3 and also 9. Now, if a number is divisible by both 3 and 4, it's going to be divisible by 12. So I'm just going to start with that. So 828 divided by 12, and you could do something else. It's really up to you. So 12 goes into 82. How many times? Well, I know that 6 times 12 is 72. So let's put a 6 here. And 6 times 12 again is 72. Let's subtract. 2 minus 2 is 0. 8 minus 7 is 1. So this is 10. Bring down the 8. So 12 goes into 108 how many times? Well, from the multiplication tables, that would be 9, because 9 times 12 is 108. So we'll subtract here and get 0. So I could go 69 times 12. 69 times 12. And again, you could have started with something else. It's really up to you. So for this one, I'm going to go 4 and 3. 3 is prime, so let's circle that and stop. 4 is 2 times 2. Those are prime. Over here for 69, let's think about that for a moment. So it's not an even number. And 6 plus 9 is 15, so this is divisible by 3. So let me start with that. So 69 divided by 3. 3 goes into 6 twice. 2 times 3 is 6. Subtracting, you get 0. Bring down the 9. 3 goes into 9 3 times. 3 times 3 is going to be 9. Subtracting, you get 0. So this would be 23 times 3. Let me get rid of this. So hopefully you remember that 23 is a prime number. That was in the list of the first 10 prime numbers. And 3, of course, is a prime number. Again, if you don't know that 23 is a prime number, you can quickly find that out using your divisibility rules, going up to the square root of the number. So let me write out that 828 is going to be equal to, we have 2 factors of 2, so 2 squared. Let me slide this down just a little bit here so it fits. And then times, and then you have 2 factors of 3, so 3 squared. And then times, you're going to have this 23. Let's do one more, and this is a really big number. Usually you get numbers that are at most 3 digits, but I'll do one with 4 digits just so you get some practice. So 4,320. Again, this ends with a 0, so it's not that bad. I would just start by saying, okay, well, this is going to be 432 times 10. And then for this one, this is 5 times 2. Circle these, you're done over there. So now you got to think about 432. So I know immediately, looking at the final 2 digits, that this guy right here, since 32 is divisible by 4, 432 will be divisible by 4. So you could start with that. But then again, if you look at 4 plus 3, that's going to be 7. 7 plus 2 is 9. So this number is also divisible by 3 and 9. Okay, so if it's divisible by 4 and 3, you can go with 12. There's other things you can do, but I'm just going to go with 12. So let's say 432 divided by 12. So 12 will not go into 4. It will go into 43. We're going to do that 3 times. 3 times 12 is 36. Let's subtract. I'm going to borrow here and say this is a 3, and this is a 1. 13 minus 6 is 7, and then 3 minus 3 is 0. So we're going to bring down this 2 here. So 12 goes into 72 exactly 6 times. 6 times 12 is 72. Subtracting, you get 0. So this right here is going to be 36 times 12. All right, for 36, we could do, let's say, 6 times 6. You could also do 4 and 9, whatever you want to do. And then for 6, we could go 3 times 2, and then 3 times 2. So we'll circle these. These are all prime numbers. Then for 12, let's go 4 and 3. I'll circle 3. And then for 4, this is going to be hard to fit. So let me branch down here like this. This is going to be 2 times 2. So let me circle those. Okay. This one's pretty big. Let me actually slide this whole thing over to the left so I can fit it. All right, let me write this 4,320. I'm just going to highlight my 2's. So 1, 2, 3, 4, 5 factors of 2. So this is equal to 2 to the 5th power, then times. So now let me go through with a different highlighted color, and I'm going to look for my 3's. So I got 1, 2, 3 of those guys, just so I don't miss anything. So this is 3 cubed, and then times, you've got that 1 factor of 5. Let me highlight that for consistency here. So I'm just going to put times 5. And you can verify that if you have a calculator, but basically 2 to the 5th power is 32. So this is 32, and then times 3 cubed would be 27, and then times 5. So if you want to punch that into a calculator real quick, you'll see that you do get 4,320. Or of course, you could do a vertical multiplication with these 2 right quick, and then do another one with this one and verify it the long way.
Hello and welcome to Pre-Algebra Lesson 26. In this video, we're going to have an introduction to fractions. So for our lesson objectives for today, we want to gain a basic understanding of fractions. We also want to learn the difference between a proper fraction, improper fraction, and mixed number. So up to this point in our pre-algebra course, we've really only thought about the whole numbers and the integers. But what happens when we have an amount that is larger than 0 but less than 1? Something that's a part of a whole amount. Well, when we come across this scenario, we can turn to fractions for help. And I know some of you watching this video already have extensive experience with fractions, while others have no experience whatsoever. No matter what, all of us have worked with fractions in our everyday life, even if we haven't realized it. So a typical scenario would involve you splitting up a pizza with your friends. So as an example, let's take a look at this pepperoni and cheese pizza that we have on the screen. So the first thing I want you to notice is that the pizza is cut up into 4 equal parts. All right, we have 1, 2, 3, 4 equal parts. Now, when we work with fractions, we're going to have some whole amount that's cut up into equal parts. So our whole amount would just be the pizza. So 1 pizza is our whole amount. It's cut up into 4 equal parts. So that means if I have 4 parts, out of 4 parts, I have 1 pizza. Now, let's suppose that 3 of your buddies come over to the house and there's a total of 4 of you. So let's put that there's 4 people. Now, in the interest of fairness, we're going to make sure that each person gets the same amount of pizza. So everybody's going to get 1 slice out of a total of 4 equal slices. So each person would get 1/4 of the pizza. Now, you might say, where did that 1/4 come from? Well, the 1 is called the numerator. This is the numerator. It's the top part of a fraction, and it tells us the number of parts being discussed or used. Since we're talking about how much each person's going to get, the numerator is a 1 because each person is getting 1 part, or in terms of the pizza, 1 slice. Now, the bottom number here is the denominator. This is the denominator. This tells me how many equal parts my whole amount is split up into. My 1 pizza, my whole amount, has been split up into 4 equal parts, so my denominator is a 4. Now, this middle part is called a fraction bar. Called a fraction bar. And later on, we're going to learn that the fraction bar represents division. We actually have the numerator divided by the denominator. But we don't need to think about that for now. Just think of the fraction bar as a way to separate your numerator, or your top part, from your denominator. So in this scenario where there's a total of 4 people, and we have 4 equal slices for our pizza, each person gets 1 slice out of 4, or 1/4 of that whole pizza. So as we just saw, fractions are generally used to describe how many equal pieces, we have of a whole amount. Now, in the previous example, we talked about how many equal pieces each person got, right? Each person got 1/4 of a whole pizza. So let's take a look at this cookie here. So again, the cookie represents our whole amount. So 1 cookie is what we have. And again, you'll notice that it's split up into 4 equal parts. 4 equal parts. 3 of the parts, you'll notice, have chocolate chips. That's what these black circles are. And then 1 part has macadamia nuts. Okay, that's what the white circles are. What if I was to ask you how much of this cookie has chocolate chips? Well, again, 3 parts out of the 4 have chocolate chips, so our numerator is going to be a 3. Okay, our numerator is going to be a 3. Again, the numerator is the number of parts being used or discussed. In this case, we're discussing how much of the cookie has chocolate chips. That answer is 1, 2, 3. So we have 3 there. So that's our numerator. So let me just label this. This is the numerator. We have our fraction bar to separate the numerator from the denominator. And the bottom number of the denominator is a 4 because we have 4 equal pieces in our whole amount. Again, this is the denominator. What if I asked you how much of the cookie has macadamia nuts? Well, that would be 1/4, right? We have 1 piece, or 1 part, out of a total of 4 equal parts. So the numerator is going to change. Now we're discussing macadamia nuts, so that's going to be a 1. The denominator will not, because I still have 4 equal parts in this cookie. So now we're talking about the fraction 1/4. As another example, let's take a look at this apple that's cut into 2 equal pieces. So we have 1 piece and then a second piece. So let's suppose it's me and you, and we're in a room, and we both want the apple. So we decide, in the interest of fairness, that we'll cut it down the middle, just like we have. Each person has an equal amount. How much will each person get? Well, each person gets 1 piece out of a total of 2 equal pieces. Right? The numerator is a 1. The denominator is a 2. Right? The numerator, again, tells me the number of parts being used or discussed, And again, we're discussing how much each person's going to get. Each person is going to get 1 part, so that's why the numerator is 1. The denominator is 2 because there's 2 equal parts in the whole amount, right? In the apple, we've cut it up into 2 equal parts, so the denominator is 2. Each person is going to get 1/2 of the apple. Now let's suppose as we're about to bite into this apple, 6 more people show up and they say, hey, we each want an equal amount. So now we've got to cut up the apple into 8 equal pieces. 8 equal pieces. And each person asks you, how much am I going to get? Well, they're going to get 1 piece out of a total of 8 equal pieces, or the fraction 1/8. Right? So 1 again is the numerator, and 8 is the denominator. So again, each person would get 1/8, or 1 piece, out of a total of 8 equal pieces for this apple. Let's say that you're watching a video on the web, and this video has 3 equal parts. So let's say this is the first part. This is part 1, and then this is part 2, and this is part 3. Okay? And I know this might not be perfectly equal how I drew it, but let's just pretend that it's 3 equal parts. Now the part in red shows you what you've already watched. So what if I asked you the question, how much of this video have you watched so far? Well, if we look at the red progress bar, we see that that takes up 1 part out of a total of 3 equal parts for the video. So you've watched 1 part, again, out of a total of 3 equal parts. That's the fraction 1/3. Again, where 1 is your numerator, this is the numerator, and 3 is the denominator. Now what if I asked you the question, how much of the video is left? Well, I have this part here, and then this part here. So unwatched, we would have 2 parts out of a total of 3 equal parts. So that's 2/3. So 2 is the numerator in this case, and 3 is the denominator. Again, in each case, the video was split up into 3 equal parts. So that's where our denominator came from in the watched and the unwatched. For the watched, we had seen 1 part out of the 3. So that's how we got a numerator of 1. For the unwatched, we have not watched 2 parts out of the 3. So that's how we got a numerator of 2. All right, so I think we have the basics down on how to come up with a numerator and denominator. Let's just do a quick practice exercise to see if you can identify the numerator and denominator in each. And we're going to start out with 1/5. So the top number is the numerator. And I'm going to write it out for the first one, and then I'm going to abbreviate after that. And the bottom number, the 5, is the denominator. So for the fraction 1/5, you have 1 as the numerator, 5 as the denominator. So this means I have 1 part out of a total of 5 equal parts. Next, we'll look at the fraction 2/9. The 2 is the numerator, so I'm just going to put a capital N. The 9 is the denominator, and I'm going to put a capital D. So I have 2 parts out of a total of 9 equal parts. Next, we have the fraction 1/4. 1 is the numerator, that's the top number. 4 is the denominator, that's the bottom number. So for this scenario, I have 1 part out of a total of 4 equal parts. Then for 3/8, 3 is going to be our numerator, and 8 is going to be our denominator. Again, if I have 3/8 of something, I have 3 parts out of a total of 8 equal parts. Okay, we'll look at 2 more. 5/7, 5 is the numerator, 7 is the denominator. Again, the numerator is in the top, the denominator is in the bottom. And if I have 5/7 of something, I have 5 parts out of a total of 7 equal parts. Then for the last one, I have 15/17. So 15, the number on top is the numerator. 17, the number on the bottom is the denominator. If I have 15/17 of something, then I have 15 parts out of a total of 17 equal parts. So there's kind of more to fractions than just what we covered so far. Once you start getting higher in math, you're going to replace your division symbol with a fraction bar. And I kind of talked about this in the beginning when I said the fraction bar represents division. So I want to just quickly cover some important division rules that we need to remember when we're working with fractions. So the first one is going to be that any non-zero number that is divided by itself is going to result in 1. So if I have something like 4 divided by 4. I can now write this using a fraction as 4 over 4, or 4/4, and this is going to be equal to 1. And think about the scenario we had with a pizza. Let me just go all the way back up real quick. So kind of looking at this, I see that I've split up my pizza into 4 equal slices. So if I consume 4/4 of the pizza, or I eat 4 pieces out of a total of 4 equal pieces, then I've consumed 1 whole pizza. The next rule to remember is that 0 divided by any non-zero number is always 0. So 0 divided by, let's say, 3 equals 0. And now we can write this using a fraction as 0 over 3 equals 0. And just think about having something that's cut up into equal parts of 3, and you get 0 parts. So how much of it did you get? You got 0. Right? If I get 0 out of a total of 3 equal parts, I'm still getting 0. So fractions represent division of the numerator by the denominator. We can write a division problem using fractions. So again, if we see something like, let's say 8 divided by 4. This is traditionally how we write it in elementary school. Now we can write it using fractions as 8 divided by 4 like that. The numerator divided by the denominator. Here we have 8 divided by 4. 8, the leftmost number. The dividend goes up on top as the numerator. 4, your divisor, goes on the bottom as your denominator. So 8 divided by 4, we know that's 2. Or something like 20, divided by 5. We could write this as 20 over 5. Right? It's just the numerator divided by the denominator. So the leftmost number, your dividend, goes on top as the numerator. Your rightmost number, your divisor, goes on the bottom as your denominator. So 20 divided by 5 is 4. And we can do one more. Let's say we had, 100 divided by 25. So we could write this as a fraction. We take 100. That's going to be our numerator. And then 25 is going to be our denominator. Right? Numerator divided by denominator. 100 divided by 25 is the same as 100 over 25. And this is going to be equal to 4. Okay, so let's kind of wrap up our lesson by just talking about the differences between a proper fraction, an improper fraction, and a mixed number. So a proper fraction is used to describe a quantity whose value is less than 1. So the easy way to tell if you have a proper fraction is just to look at the numerator and see if it's less than the denominator. If it is, you have a proper fraction. So something like 2/5 or 5/7 or 2/11 or 1/9. In each case, the numerator is smaller than the denominator. If I got something like 15/7, that's not a proper fraction. The numerator is larger than the denominator. This is an improper fraction. Now, before we go any further, let me just try to warn you that your teacher might try to trip you up with some negative fractions. Let's say you get something like -2/3. -2/3. If you get a negative fraction, ignore the negative sign and just pretend the fraction's positive. So I'm just going to think about this as +2/3 and just look at the 2 and the 3. The numerator is smaller than the denominator, so it's a proper fraction. I can just put my negative sign back and say, okay, -2/3 is a proper fraction. If I had something like -11/9, ignore the negative sign, pretend it's 11/9, and look at the 11. It's bigger than 9, so it's not a proper fraction. Okay, it's not a proper fraction. So that means -11/9 is not a proper fraction either. So kind of next up, an improper fraction is used to describe a quantity equal to or larger than 1. So kind of the easy way to think about this is that if your numerator is the same as or larger than your denominator, you have an improper fraction. So like 8/8, the numerator is the same as the denominator, so this is improper. Right? So equal to or larger than 1. If you had something like 13/11, equal to or larger than 1. Again, if you get negative numbers involved, just think about them as if they were positive, right? Take the absolute value before you think about the definition. So if I had something like -15/14, let's say I try to go by this definition. An improper fraction is used to describe a quantity equal to or larger than 1. Well, any negative number is less than 1. So if you try to apply this definition using this as a negative, you get the wrong answer. So that's what I'm saying. Just ignore the negative sign. Just look and see if the numerator is bigger than the denominator. 15 is larger than 14. And so you would know this is an improper fraction, right? -15/14 is improper. Okay, the last thing we're going to learn about is called a mixed number. So a mixed number is kind of a fancy way to write an improper fraction, right? And you can go back and forth, and we'll see how to do that in the next lesson. So basically what it is, it's the sum of a whole number and a proper fraction. So something like 3 1/4. And what this is it's 3 plus 1/4. We just write it like this for convenience, right? And a lot of students get confused and think that's multiplication because they're sitting next to each other. But no, it's 3 plus 1/4. Or something like 6 1/8, right? This is 6 plus 1/8. But it's very important that you have a whole number and then a proper fraction. It can't be a whole number and an improper fraction. Okay, so let's look at one final quick exercise. We just want to determine whether each is a proper fraction, improper fraction, or mixed number. So we're going to take a look at 7/5. So the numerator is larger than the denominator. This is improper. Again, that's all you need to look at. 3/11, the numerator is smaller than the denominator. So this is proper. For 4/5, the numerator is smaller than the denominator. So this is proper. For 9 1/8, it's easy to see that this is a mixed number, right? It's a mixed number. And I don't think anybody gets confused between mixed numbers and proper fractions and improper fractions. They mostly get confused on the definition between a proper fraction and an improper fraction. For a mixed number, you have a whole number just hanging out to the left. So it's pretty obvious that it's a mixed number. For 10/7, the 10, the numerator is larger than the 7. So this is an improper fraction. For 6/7, the 6, the numerator, is smaller than the denominator, 7. So this is proper. Hello and welcome to Pre-Algebra Lesson 27. In this video, we're going to talk more about mixed numbers and improper fractions. So for our lesson objective, we want to learn how to change a mixed number into an improper fraction and vice versa. Meaning we also want to learn how to take an improper fraction and change that into a mixed number. All right, so we're going to begin by learning how to take an improper fraction and change that into a mixed number. So this is very, very simple. Just write down the steps, use them as you practice, and just like anything else, over time, you can just kind of throw your paper away because you will memorize this. So the first step is just to divide the numerator by the denominator. So if I have something like, let's say 10/3, okay, let's say 10/3, I would take 10 and I would just divide it by 3, just like that. So 3 goes into 10 3 times. 3 times 3 is 9. Subtract and get 1. So this division gives me 3 with a remainder of 1. So let's kind of copy this. We're going to bring it down to the next step. Okay, so I have here that the quotient is the whole number for the mixed number. So this 3 here, which remember, that's our quotient, that's going to be the whole number for the mixed number. So the 3 will be your whole number part. Then the remainder, which in this case that's that 1 there, is the numerator of the fraction part. So I'm going to put a 1 there. Now where do I get my denominator for the fraction part? Well, it's the original denominator from the improper fraction. So that doesn't change. That's still your denominator here for the fraction part. And remember, that was a 3. 3 1/3 is the same thing as 10/3. Okay, 3 1/3 is the same thing as 10/3. All right, let's take a look at some examples. We're going to start out with 18/7 or 18/7. So again, my first step is just to do a basic division. So I'm going to take 18 and I'm going to divide by 7. So 7 goes into 18 twice. 2 times 7 is 14. Subtract and you get 4. So the answer here is 2 with a remainder of 4. So again, to convert this into a mixed number, the quotient part, which is 2, is going to be the whole number part. The remainder, which is 4, is going to be the numerator for the fraction part. And then your denominator for the fraction part is the denominator from the improper fraction. So that's going to be 7. Or you could just say, okay, it's my divisor from when I did my division, right? 18 divided by 7. However you want to remember that. So 18/7 is the same as, or is equal to, 2 4/7. All right, let's take a look at another one. We have 19/3. So again, we just set up a basic division. 19 divided by 3. So 19 divided by 3. And 3 is going to go into 19 6 times. 6 times 3 is 18. Subtract and we'll get 1. So that's our remainder. So we get 6 with a remainder of 1. So again, The 6, the quotient part, is your whole number. The 1, which is your remainder, is going to be the numerator for your fraction part. And then the denominator for the mixed number is going to be 3, right? It's the same denominator as from the improper fraction. So 19 thirds is the same as, or again, is equal to 6 1/3. What about 11 sevenths? So again, we're going to divide. We have 11, and we're dividing by 7. 7 goes into 11 once. 1 times 7 is 7. Subtracting, we get 4. So the remainder here is 4. So 1 with a remainder of 4. And let me kind of move this down so I can write my answer. Move that over there. So this is equal to, again, the whole number part will be 1, right? That's your quotient. The numerator for the fraction part will be 4. That comes from my remainder. And then the denominator for the fraction part is the denominator from the improper fraction. So that's a 7. So 11 sevenths is equal to 1 4 sevenths. All right, what about 31 over 15? So again, we set up a long division. We have 31 divided by 15. So 15 goes into 31 twice. 2 times 15 is 30. Subtracting, we get 1. So this is 2 with a remainder of 1. So again, the 2, the quotient part, is your whole number. 1, the remainder, is your numerator for the fraction part. And then 15, which is the denominator from the improper fraction, is going to be the denominator for the fraction part. So 31 fifteenths is equal to 2 1/15. All right, let's take a look at one more. So we have 59 eighths, or 59 over 8. So again, divide 59 by 8. 8 goes into 59 7 times. 7 times 8 is 56. Subtracting, get 3. So this would be 7 with a remainder of 3. So this is going to be equal to, again, the whole number part is going to be 7. You get that from your quotient. The numerator for the fraction part is going to be 3. Again, that comes from your remainder. And then the denominator for the fraction part is 8. That comes from your improper fraction. So 59 eighths is equal to 7 3/8. So really that was pretty easy overall. Your general strategy for those type of problems, again, just write down your steps, use the steps as you practice, and then after you get enough practice, you won't need to look at those steps anymore. You will have memorized them, right? So these things will become automatic for you. Now we're going to talk about changing from a mixed number to an improper fraction. And this isn't going to be any more difficult. So the first step is to multiply the denominator of the fraction part by the whole number part. So if we had something like, let's say 3 1/8, I would take the denominator of the fraction part, which in this case, that's this 8 here, and I would multiply it by the whole number part. So I would have 3 times 8 to start. So 3 times 8. And let me copy this. We're going to bring this down to the next step. Then the next thing we want to do is add the result to the numerator of the fraction part. So I have this 3 times 8 here. That's to be done first. When that's done, I'm going to add the numerator of the fraction part. So that's 1. So I can put plus 1 here if I want. And because of the order of operations, I would do 3 times 8 first, and then I would add 1 to that result. So I really don't need to do anything to clarify that if I just follow the order of operations. But if you want to make it completely crystal clear, you can put parentheses around 3 times 8 just to say, hey, I absolutely must do 3 times 8 first before I add 1 to that. The result of this is the numerator for the improper fraction. So 3 times 8 is 24, and if I add 1 to that, I get 25. All I'm missing now is my denominator, and the denominator is going to be the same as the denominator from the fraction part for the mixed number. So that's going to be an 8. So we have 25 eighths here. Now what I want to show you is we know how to go from 25 eighths to 3 1/8. Again, we set up a division. So 25 divided by 8. 8 goes into 25 3 times. 3 times 8 is 24. Subtracting, get 1. So the remainder is 1. So if I convert between this and a mixed number, I would get a 3, which is what we have here for my whole number part. My remainder is a 1, so that's the numerator for the fraction. And my divisor is an 8, or my denominator for the fraction is an 8, so that's going to be my denominator for the fraction part of the mixed number. So 25 eighths is the same as, or is equal to, 3 1/8. All right, so we're going to begin with 8 1/3. And really very simple overall. Again, if you wrote down the steps, step 1 is to multiply the denominator of the fraction part by the whole number part. So I'm going to take 3, which again is the denominator of the fraction part, multiply that by 8, which is the whole number part. So I would start out with 8 times 3. 8 times 3. Now, once I've done that, it tells me to add the result to the numerator of the fraction part. And recall that I put parentheses around 8 times 3 to make it crystal clear that we multiply that before we do any addition. But again, you don't need to do that because of the order of operations. If I come over here and I put plus 1, okay, because I'm adding the numerator from the fraction part next, whether I have parentheses around 8 times 3 or not, it doesn't matter, right? The order of operations tells me, hey, multiply before I add. But for this lesson, I'm going to put parentheses around it just so we're clear. We're doing 8 times 3 first before we add that result to 1. So 8 times 3 is 24, and 24 plus 1 is 25. And now, where do I get my denominator from? Again, the denominator is the same denominator from the fraction part of that mixed number. So this is going to be over 3 over 3. So 8 1/3 is equal to 25 thirds. Okay, let's take a look at 9 4/7. So again, the first step is to multiply the denominator of the fraction part by the whole number part. So this right here, this 7, is getting multiplied by 9. So what is 9 times 7? I'm going to put that in parentheses. And then when we're done with that, we add the result to the numerator of the fraction part. So the numerator for the fraction part is 4. So I'm going to say plus 4 when I'm done. And my denominator is going to be the same as the denominator from the fraction part of the mixed number. So that's going to be a 7. So 9 times 7 is 63. And then if I add 4 to that, I'm going to get 67. So this would be 67 over 7, or I could say 67 sevenths. What about 3 5/8? Well, again, we want to start out by multiplying the denominator of the fraction part by the whole number part. So I'm going to take 8 and multiply it by 3. So 8 times 3. Then when I'm done, I'm going to add to that the numerator of the fraction part. So in this case, that's this 5 here. And this is going to be over my denominator from the fraction part of the mixed number is an 8. So that's going to stay the same, right? That's going to be my denominator for the improper fraction as well. So now I just crank this out. 8 times 3 is 24. 24 plus 5 is 29. So this is going to be 29 over 8, or again, 29 eighths. And we could just say that 3 5/8 is equal to 29 eighths. What about 13 5/11? Well, again, I'm going to take this part right here, this 11, the denominator from the fraction part, and I'm going to multiply it by the whole number part. So we would have 11 times 13. Now, once we've performed this operation, we're going to add the result to the numerator of the fraction part. So I'm going to add that to 5. So plus 5. And this is going to be over. Again, we use the denominator from the fraction part of the mixed number. So this is going to be over 11. So what is 11 times 13? 11 times 13. A lot of you already know that it's 143. Well, let's go ahead and crank this out. 3 times 11 is 33. And then 1 times 11 is 11. So we're going to add, bring down the 3. 3 plus 1 is 4. Bring down the 1. So again, 143. If I add 5 to that, I'd have 148. So this would be equal to 148. And again, that denominator is going to be 11. So 13 5/11 is equal to 148 elevenths. What about 107 ninths? Well, again, we're going to start by taking the denominator from the fraction part, multiplying it by the whole number part. So you'd have 9 times 100, 9 times 100. And then when we're done, we're going to add to it the numerator from the fraction part. So that's a 7. I'm going to add a 7 on there. My denominator stays the same as the denominator from the fraction part of the mixed number. So that's going to be a 9. And let's just crank this out. What's 9 times 100? Well, we have two trailing zeros here. So I just need to do 9 times 1, that's 9, then attach 2 trailing zeros to the end, so that would give me 900. Then I would add 7 to that, so that would be 907, and then over 9. So 107 ninths is the same as 907 ninths. Hello and welcome to Pre-Algebra Lesson 28. In this video we're going to learn how to find the greatest common divisor, which I've abbreviated as GCD. So the lesson objective for today is just to learn how to find the greatest common divisor, again abbreviated GCD, for a group of numbers. So before we kind of get into the lesson, I want to clear something up that causes a lot of confusion for students. As someone who makes a lot of video tutorials, one thing I've noticed is that if I post a video on, let's say, finding the greatest common divisor, like we have here, students will watch that and they will post in the comments, hey, do you have anything on finding the greatest common factor? And my reply will always be, yeah, you just watched it. If someone's asking you to find the greatest common divisor for, let's say, two numbers, it's the same thing as if they asked you to find the greatest common factor for those two numbers. So if I said something like, what is the greatest common divisor of, let's say, 12 and 30, it's the same thing as if I asked you, what is the greatest common factor of 12 and 30? Same exact thing. And to kind of think about this for a second, we all know that if we have 4 times 3 equals 12, that 4 and 3 are called factors. They're called factors of 12. But really, they're also divisors, right? So if I have 12 and I divide by 4, I get 3. There's no remainder there. If I have 12 and I divide by 3, I get 4. There's no remainder there. If a number is a factor of another, it's also a divisor, meaning if I take 12 and I divide it by any of its factors, I'll get a result that doesn't have a remainder. So when we ask for the greatest common divisor and we ask for the greatest common factor, we're asking for the same thing. So when working with two or more numbers, the greatest common divisor, again I abbreviate this GCD, is the largest whole number that is a divisor of all numbers. And I could have just as easily said, when working with two or more numbers, the GCF, the greatest common factor, is the largest whole number that is a factor of all numbers. Again, we can interchange those. Now, actually finding the greatest common divisor or the greatest common factor for a group of numbers is very simple. Go ahead and write down the steps and then use them as we practice. And then again, as you do more practice, you won't need to look at the paper. You will have committed the steps to your memory. So for finding the greatest common divisor, the first thing you want to do is find the prime factorization of each number. We all know how to do that at this point. We learned it a few lessons back. You can use a factor tree or some other method that you've learned if that's more comfortable for you. The next thing we're going to do is create a list of prime factors that are common to all numbers. And this part's important. When you're creating that list, make sure that the prime factors are common to all numbers. If you're trying to find the greatest common divisor for, let's say, 5 numbers, and you have a prime factor that's common to 4 of them, but not common to the 5th number, you can't use it. It has to be common to all numbers. Then the last thing, you're just going to take that list that you made, and you're going to form the product of the numbers on the list. That's going to give you your greatest common divisor, right? So the greatest common divisor is the product of the numbers on the list. Very, very easy. So we're going to jump in and look at some practice problems. We want to find the greatest common divisor for each group of numbers. We're going to start out with this GCD of 12 and 20. So what is the greatest common divisor? Or I could have just as easily said, what is the greatest common factor of 12 and 20? The first thing we're going to do is find the prime factorization of each number. I'm going to do that using a factor tree. But again, if you have another method you're more comfortable with, use that. So for 12, I'm going to start out with 4 times 3. Again, you can just start out with any two factors for 12. It doesn't matter what it is. And then anytime I have a prime factor, I just circle it and I stop. So 3 is prime, I circle and I stop. 4 is 2 times 2. 2 is prime, so I'm going to circle both. And then now let's do 20. I'm going to start out with 5 times 4. Again, any two factors for 20 would work. 5 is prime, circle that and stop. 4 is 2 times 2. 2 is prime, so circle both. Now that we have the prime factorization for each number, and let's just write it out. We have 12 is 2 times 2 times 3, and 20 is 2 times 2 times 5. We're looking to see what is common to both. And I know a lot of people will make a table, and we'll do that kind of when we get to some bigger numbers. For right now, we can kind of eyeball it and see that we have 1 2 that's in common, and then a second 2 that's in common, and nothing else that's in common. So if we were to form a list, that list would contain 2 2s, right? 2 2s. So for my greatest common divisor, remember, I just formed the product of the numbers on the list. So the greatest common divisor is going to be 2 times 2, which is going to be equal to 4. Right? And I could have just as easily written greatest common factor of 12 and 20 is 2 times 2, which is 4. Again, these are the exact same thing. I want to embed that in your head so that you understand it. All right, let's take a look at the greatest common divisor of 36 and 54. So again, start out by finding the prime factorization for each number. For 36, it's 6 times 6 we could do. So 6 is not prime, so we're going to continue. 6 is 2 times 3, and 2 times 3 over here. And 2 and 3 are both prime, so we're going to circle all of these. And we're done. Now for 54, I could think about 9 times 6. And neither number is prime, so we're going to continue. 9 is 3 times 3. 6 is 3 times 2. And all of those are prime. So we're going to circle all of these. And we have our prime factorizations. So 36 is 2 times 2 times 3 times 3. 2 times 2 times 3 times 3. 54 is 3 times 3 times 3 times 2. So I'm going to write this as 2 times. I'm just going to put a space here because I don't have another 2. And then I'm going to put times 3 times 3 times 3. And I'm basically just doing that so that we can glance at this and see what's common, right? So I can look right now and see that I have a 2 that's common to both. I have a 3 that's common to both, and another 3 that's common to both. So if I was to make a little list, it would contain 1 2, 1 3, and then a second 3. So the greatest common divisor of 36 and 54 is going to be equal to 2 times 3 times 3. So 2 times 3 is 6, 6 times 3 is 18. So your greatest common divisor for 36 and 54 is going to be 18. All right, let's take a look at one with 3 numbers involved. So not any more difficult, just a little bit more tedious. The more numbers you put in there, the more tedious it gets. So we have the greatest common divisor of 25, 80, and 90. So we're going to find the prime factorization for each number. 25 is 5 times 5, and 5 is prime, so we're going to circle both. 80, I'm going to start out with 8 times 10. 8 is 4 times 2. 4 is 2 times 2. Now 2 is prime, so I'm going to circle all of these guys. And then 10 is 5 times 2. 5 and 2 are prime, so I'm going to circle those guys. And then what about 90? Well, I'm going to do 90 as 9 times 10. Neither's prime, so I continue. 9 is 3 times 3. 10 is 5 times 2. And all of these are prime, so I'm going to circle them. So now I have my prime factorizations. So 25 is 5 times 5. So I'm just going to write this like this. 5 times 5. 80 is 2 times 2 times 2 times 2. Then times 5. And then 90, I got 2 times 3 times 3 times 5. So one thing we can do is we can write the numbers that are common on top of each other so it makes it completely clear. And I kind of did that in the last example, but as you get better at this, you really don't need to do it. Particularly when you look at 25, you see that it's 5 times 5. So right away you know that when you go to the other numbers, you're only looking for a 5, right? Because that's all that's involved in here, and it has to be common to everything. So I'm not looking at any of these 2's, and I'm not looking at any of these 2s or 3s here. So really, I would just highlight this 5, this 5, and this 5. I just have one 5 that's common in everything. Now, there's a second factor of 5 in the prime factorization of 25, but it's not matched in the prime factorization of 80 or 90, right? There's just one 5 in the prime factorization for 80 and 90, so we can only put one 5 on our list, so it makes it really easy. The greatest common divisor of 25, 80, and 90 is going to be 5. I don't need to multiply anything here. There's only one number that's in common to everything, and again, that's 5. All right, for the last problem, let's look at one that's a little challenging. So we have the greatest common divisor of 198, 165, and 132. So let's start out by just factoring 198. So I know it's an even number, so I know it's at minimum divisible by 2. Now, it's not going to be divisible by 4 because if I look at the final two digits here, 98, that's not divisible by 4. So let's go ahead and just start out with dividing this guy by 2 and just seeing what we get. 2 will go into 19 9 times. 9 times 2 is 18. Subtract, you get 1. Bring down the 8 there. 2 goes into 18 9 times. 9 times 2 is 18. Subtract, you get 0. So 99 times 2 gives you 198. So 2 is a prime number, so we can circle this and stop. 99 is not. Right away when I look at 99, I'm thinking, is it divisible by 9? 9 plus 9 is 18, so yeah, it's divisible by 9. So this is 9 times, and you might know by now this is 9 times 11. But again, in case you didn't, you could just do a long division, 99 divided by 9. Now, we should know at this point that 11 is a prime number, so we'll circle that and stop. And 9 is 3 times 3. So 3 is prime. We're going to circle these. We have our prime factorization for 198. It's 2 times 3 times 3 times 11. Let's write this on the next page. So 198 is 2 times 3 times 3 times 11. Okay, let's do 165 now. So just like with 198, I don't know two factors for this number off the top of my head. But again, using my divisibility rules, I see it ends in a 5. So I know I can do 165 divided by 5. 5 goes into 16 3 times. 3 times 5 is 15. Subtracting, get 1. Bring down the 5. 5 goes into 15 3 times. 3 times 5 is 15. Subtracting, get 0. So 33 times 5 gives me 165. Now 5 is a prime number, so I can circle this and stop. 33 is not. I know that 33 is divisible by 11. 33 divided by 11 is 3. So 33 would be 11 times 3. And 11 and 3 are both prime. So circle both of those. And so for 165, we get 3 times 5 times 11. Okay, for the last one, we have 132. And I can see that this number is even right away. So I know it's divisible by 2. The last two digits form the number 32. So that's divisible by 4. And 1 plus 3 is 4. 4 plus 2 is 6. 6 divided by 3 is 2, no remainder. So it's divisible by 4 and 3. So it has to be divisible by 12. So 132 divided by 12. 12 goes into 13 once. 1 times 12 is 12. Subtracting, get 1. Bring down the 2. 12 goes into 12 once. 1 times 12 is 12. Subtracting, get 0. So 12 times 11, okay, 12 times 11 would give me 132. Again, we know 11 is prime. 12 we could write as 4 times 3. 3 is prime. 4 is 2 times 2. 2 is prime, so we're going to circle both. So 132 is 2 times 2 times 3 times 11. Now we're going to form a little list and look for what's common. So I have a 2 in the prime factorization of 198. I don't have it in 165, so it's not going to be common in everything. Although I have 2 factors of 2 here, I can't use 2 in my list because, again, it's not common to everything. What about 3? I have that in 198, I have it in 165, and I have it in 132. So I can put one factor of 3 in that list. Now I have a second factor of 3 here, but I don't have a second factor of 3 in 165, so it can't go into the list. Now, the last thing we'd look at in the prime factorization of 198 is 11, and that's going to be common to everything. So there's an 11 here and here. So really the only thing that's common to all three would be one factor of 3 and one factor of 11. So when I build my GCD, my greatest common divisor, for 198, 165, and 132, it's going to be equal to, again, the product of the numbers on the list. So 3 times 11, or 33. Hello and welcome to Pre-Algebra Lesson 29. In this video, we're going to learn about simplifying fractions, otherwise known as reducing a fraction to its lowest terms. So the lesson objective for today is just to learn how to simplify fractions. And again, as I just said, this is also referred to as reducing a fraction to its lowest terms. So I just want to make you guys aware of a little notational change that's going to start in this video. Now, for a lot of you who haven't taken algebra yet, you've only used this symbol to imply multiplication. Right? This is for multiplication. So if I wanted something like 6 times 7, I write 6, then that symbol, then 7, and we know that equals 42. But kind of as you move higher in math, this symbol is going to go away. You're going to use some other method, right? And there's multiple methods you can use. I know earlier in the course we talked about a number being next to parentheses implies multiplication. You're going to have that. But primarily what we're going to use is a dot. Okay, we're going to use a dot. So if I wanted 6 times 7, I could write it like this. This symbol also means multiplication. So 6 times 7 equals 42. Or we could do 2 times 8, that equals 16. All right, I'm just replacing this familiar symbol with this new dot. And that's all that we're going to change. Now you might ask yourself, why do we go back and forth between these symbols? Well, as you get higher in math, you start working with variables. And this symbol here will get confused with the variable x, which is very, very common in algebra. So we have to switch to something else so that it's crystal clear what we want you to do. So before we kind of get into the math of simplifying fractions, I want you to take a look at these two rectangles on the screen. Now we have part of each rectangle that's shaded green and part that's just white. If I was to look at this top rectangle here, it's cut up into two equal parts. Here's the first part, here's the second part. So if I was to ask you to represent the amount that's shaded green with a fraction, you would come up with the fraction 1/2. Right? So shaded, you have one part, that's going to be your numerator, that's shaded, out of two equal parts. So that's the fraction 1/2. Now when we look at the rectangle below, we see that it's split up into 4 equal parts. So 1, 2, 3, 4. But I want you to observe that these two parts here take up the same space as this one part here. These two parts here, the parts that are shaded green, take up the same space as this one part here. So if I wanted to represent the shaded amount for this bottom rectangle, okay, so what's shaded in green? I now have two parts, okay, two parts, so that's my numerator, out of a total of 4 equal parts. So 4 is my denominator. So now we can visually see that 1/2 is the same as or is equal to 2/4. But you might say, how is that the case? How is that mathematically possible to have the same value from two different numbers? Well, let's just erase this 2/4 for a second and just start out with 1/2. All of you know at this point that if I multiply a number by 1, the number remains unchanged. So for example, if I multiply 5 times 1, I get 5. If I multiply 277 times 1, I get 277. If I multiply 1/2 times 1, I get 1/2. Now all of us also know that any non-zero number divided by itself is 1. So if I had 2 divided by 2, 2 divided by 2, this is the same thing as the number 1. So let's say I multiply 1/2 times 2 over 2. I'm basically multiplying 1/2 by 1. Now I know we haven't multiplied fractions yet officially, but essentially all we're going to do is multiply the numerator times the numerator and put that over the denominator times the denominator. So I would do 1 times 2, that would give me 2, and I would multiply 2 times 2, and that would give me 4. So I took 1/2 and I multiplied it basically by 1. It's a complicated form of 1, but 2 over 2 is 1. And I ended up with 2/4. So that's how we can have the same value out of two different fractions. And I could keep going. I could have multiplied 1/2 by, let's say, 5 over 5. 5 over 5 is 1. 1 times 5, 1 times 5 is 5. 2 times 5 is 10. So 5/10 is the same as 1/2. So equivalent fractions are fractions that have the same value. And we just saw that with 1/2, 2/4, and 5/10. Those are all equivalent fractions because at the end of the day, they have the same value. So now that we understand how two or more fractions can look different but have the same value, let's talk about reducing a fraction to its lowest terms. So a fraction is considered simplified, or your teacher or your textbook might say reduced to its lowest terms, when the numerator and denominator have no common factors other than 1. Other than 1. So to reduce a fraction to its lowest terms, or again, to simplify a fraction, you start out by factoring the numerator and denominator completely. Then you're going to cancel all common factors between the numerator and denominator. All right, so we're going to jump in and look at some practice problems now. We want to reduce each fraction to its lowest terms. Okay, we're going to begin with 15 over 27. So the first thing we want to do is factor the numerator and denominator completely. Now you've probably gotten pretty good at factoring whole numbers at this point. So you can use a factor tree if you need to, but for some of the smaller numbers, you probably have memorized the prime factorizations already. Like 15 you should know is 5 times 3. You shouldn't need a factor tree for that. 27, you know it's 3 times 3 times 3. 3 times 3 times 3. If you need a factor tree, pause the video and make one. You have 9 times 3. 3 is prime, circle that. 9 is 3 times 3. Circle both of those. So you see that you get 3 times 3 times 3. Now, after you've done that, you're looking to cancel common factors between the numerator and denominator. So in other words, if I have a 3 in the numerator, I can cancel that with one of the 3's in the denominator. Essentially, all I'm doing is I'm saying, hey, I have 3 over 3, and that's the same thing as 1. So when I go through, I don't have this 3 anymore. I just have a 5 in the numerator. And when I go through here, I don't have this 3 anymore. So I just have a 3 and another 3 in the denominator, and 3 times 3 is 9. So I'm basically saying that 15/27, or 15 over 27, is the same thing as 5/9. And again, reverse this process to kind of get a little insight as to what happened. So you have 5/9. If you multiply it by 3 over 3, again, 3 over 3 is the same thing as 1. So I'm not changing the value of the fraction. 5 times 3 is 15. 9 times 3 is 27. Okay, let's look at 18 over 60. So again, we want to factor the numerator and denominator completely. So for 18, let's just do a factor tree. Let's start out with 6 times 3. So 3 is prime, let's circle that. 6 is 2 times 3. 2 and 3 are both prime. Let's circle those. So 18 is 2 times 3 times 3. 2 times 3 times 3. For 60, let's do 10 times 6. 6 is 2 times 3. Those are both prime. So circle 2 and circle 3. 10 is 5 times 2. And those are both prime as well. So circle 5 and circle 2. So we're going to have 2 times 2. 2 times 2 times 3 times 5. So what's common between numerator and denominator? Well, I have one factor of 2 in the numerator that I can cancel with one factor of 2 in the denominator. 2 over 2 is equal to 1, so we can just remove that. Now, I have one factor of 3 in the numerator that I can cancel with one factor of 3 in the denominator. And then that's all. I have this 3 up here, but I have no other 3 down here to cancel it with. Then I have this 2 down here, but no other 2 up here to cancel it with. Right? I've already canceled out this 2. I can't use it again. And then finally I have this 5 here. No 5 up here to cancel it with. So our simplified version of this fraction, I have a 3 in the numerator, and then in the denominator, I have 2 times 5, or 10. So 18 over 60 is equal to 3 over 10, or 3/10. Let's take a look at 95 over 20. Again, we want to factor each number. So 95, I know, is 19 times 5. And those are both prime numbers. So we're going to circle those. So 19 times 5. 20, I know, is 4 times 5, and 4 is 2 times 2. So 2 times 2 times 5. Now, what's common between numerator and denominator? I have a 19 in the numerator, no 19 in the denominator. I have a 5 in the numerator, and I have a 5 in the denominator, so I can cancel those common factors between numerator and denominator. And then I have 2 2's in the denominator, but I don't have anything in the numerator that matches that. So my answer, I'm going to have a 19 in the numerator, and I'm going to have 2 times 2, or 4, in the denominator. So I end up with 19/4 as my answer. All right, what about negative 26 over 156? So we've never worked with a negative yet. And basically, when you see a negative, when you factor the number, just write a -1 out to the side, and then just write the prime factorization for the number 26. So for 26, it's 13 times 2. So I'm going to write -1 times 13 times 2, right? -1 times 13 is -13. -13 times 2 is -26. All right. Then we have 156. So let's make a factor tree for that one. So 156, I know that it's divisible by 2, and it's also divisible by 4, because 56 is divisible by 4. So let's do that off to the side. What is 156 divided by 4? 4 goes into 15 3 times. 3 times 4 is 12. Subtracting, get 3. Bring down the 6. 4 goes into 36 9 times. 9 times 4 is 36. Subtracting, get 0. So this would be 4 times 39. 4 is 2 times 2. And 39 is 13 times 3. So let's circle all of these because they're all prime. So we would have 2 times 2. 2 times 2 times 13 times 3. Now what can we cancel between numerator and denominator? We can cancel this 13 in the numerator with this 13 in the denominator. We can cancel this 2 in the numerator with one of the 2's in the denominator. Doesn't matter which one, just one of them. Now all I have left in my numerator is a -1. So that's going to be my numerator. And in the denominator, I have 2 times 3, or 6. So our simplified version is -1/6. All right, let's look at -33 over 77. So again, I have a negative value here. Just write -1 times, and then do the prime factorization for 33. And that's just going to be 3 times 11. What about 77? Well, 77 is 7 times 11. So 7 times 11. And as time goes on, you're going to recognize right away that the greatest common divisor of 33 and 77 is 11. So you're just going to kind of mentally divide each number by 11. So in other words, if I had -33 over 77, once I'm good at this, I'm not going to go through these steps. I'm going to say, okay, 33 divided by 11 is 3. So this would be -3 over 77 divided by 11 is 7. So I end up with -3/7. So you're going to be able to mentally do this after some practice. But for right now, it's best not to skip any steps. So we see that we have a common factor of 11 between the numerator and denominator, and that's all we can cancel. So we end up with -1 times 3, or -3, over 7. So you end up with -3/7 as your answer. What about 64 over 288? So 64, I know, is 2 to the 6th power. So 2 times 2 times 2 times 2 times 2 times 2. Again, if you didn't know that, you could do a factor tree, right? 64 is 8 times 8. 8 is 4 times 2. 2 is prime, so we're going to circle these. And then 4 is 2 times 2. Just after a while, you're going to start to recognize what the prime factorizations are for some of these common numbers. So I got 1, 2, 3, 4, 5, 6 factors of 2, which we have up there. And then what about 288? Well, I know it's divisible by 2, And 88 is definitely divisible by 4, so I can start with that. Let's divide 288 by 4 and see what we get. 4 goes into 28 7 times. 7 times 4 is 28. Subtracting gets 0. Bring down this 8 here. 4 goes in 8 twice. 2 times 4 is 8. Subtracting gets 0. So 72 times 4 is 288. Now, without making a factor tree, I know that 4 is 2 times 2. I know that 72 is 9 times 8. Okay? 9 is 3 times 3. 8 is 3 factors of 2. Again, if you're not comfortable with this yet, go ahead and make the factor tree. It's not a big deal. So 288, again, 4 times 72. 4 is 2 times 2. 72 is 8 times 9. 8 is 4 times 2. 9 is 3 times 3. 3 is prime. 2 is prime. And then 4 is 2 times 2. And then that's prime. So we have 1, 2, 3, 4, 5 factors of 2. So 2 to the 5th power times 2 factors of 3 are 3 squared. So 2 to the 5th power times 3 squared. And that's exactly what we got up here. We have 1, 2, 3, 4, 5 factors of 2 and 2 factors of 3. Okay, so now we're looking to cancel common factors between numerator and denominator. I can cancel this 2 with this 2, 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 and then this 2 with this 2. Now I have a last 2 up here because I have 1, 2, 3, 4, 5, 6 factors up here, but I only have 5 factors of 2 in the denominator. So I'm going to have 1 factor of 2 up here that I can't cancel with anything because I had 1 more up here than I had down here. These 3's I don't have anything to cancel with up in the numerator. So my simplified version of this fraction, I'm going to have a 2 in the numerator and 3 times 3 or 9 in the denominator. So we end up with 2/9 as our answer. All right, so now we have 25 over negative 135. 25 over negative 135. 25 is just 5 times 5. Negative 135, again, if you have a negative involved, just write -1 and then just do the prime factorization for 135. So 135, it ends in a 5, so I know it'll be divisible by 5. And what is that? 135 divided by 5. 5 would go into 13 twice. 2 times 5 is 10. Subtracting, get 3. Bring down the 5 there. 5 goes into 35 7 times. 7 times 5 is 35. Subtracting, get 0. So 27 times 5 is 135. And we know 5 is a prime number. We can circle that. And 27 we know is 3 factors of 3. Right? It's 9 times 3. 3 is prime. 9 again is 3 times 3. And 3 is prime. So we're going to circle both of these. So 3 times 3 times 3 times 5. So what can we cancel between numerator and denominator? Well, all I can do is cancel this 5 with this 5, and that's it. Right, I have one more 5 here, but nothing to cancel with down here. And I have some 3's down here, nothing to cancel with it up there. So we just end up with 5 in the numerator, and 1, 2, 3 3's in the denominator. 3 times 3 is 9, 9 times 3 is 27. Then multiply by -1, you get -27. Now, I can keep it as 5 over -27. I could also write this as -5 over 27, or I could write this as negative and then 5 over 27. All of these are the same thing. Remember that when we divide integers, a positive divided by a negative is a negative, or a negative divided by a positive is a negative, or you can just have the negative out here just saying, hey, the fraction is negative, and then 5/27. All of these mean the same thing. You have a -5/27 as your answer. Okay, let's take a look at 4/19. So 4 we know is 2 times 2. 19 is prime. If I looked at the greatest common divisor, or again, the greatest common factor of 4 and 19, your answer would be 1. So when you have this situation, you're not going to be able to simplify the fraction any further, and you just end up with 4/19 as your answer.
Hello and welcome to Pre-Algebra Lesson 30. In this video, we're going to learn about multiplying fractions. All right, so the lesson objective for today is just to learn how to multiply 2 or more fractions together. I'm going to give you an initial procedure, and then I'm going to modify it slightly. We're going to start doing something called cross-canceling, and that's going to allow us to simplify while we're doing the multiplication problem so that we don't have to simplify after. But let me give it to you this way first, and then we'll do the modification. So to multiply two or more fractions, you're going to multiply the numerators together, and then you're going to place the result over the product of the denominators. And I have here, we want to simplify, but we're going to change this up a little bit as we work through the problems. Now, before we get started, let me give you a brief explanation in terms of why we do this as the numerator times the numerator over the denominator times the denominator, and then we simplify. So let's suppose that I start off with a pizza, and I'm going to split this up into 4 equal slices. So each slice will be 1/4 of the pizza. So let's say this is 1, 2, 3, and then 4 slices. Suppose that I eat a slice of this pizza for breakfast, and then another one for lunch, and then a final one for dinner. So how much of the pizza did I eat? 3/4. How much of the pizza is left? 1/4. So we know that at this point. But how could I have gotten that 3/4? I would have said that, well, I ate 1, 2, 3, so I could just count pieces of pizza out of a total of 4 equal pieces of pizza that were available in this whole amount. So I could have said that this is 1/4, that's me eating at breakfast, plus 1/4, that's me eating at lunch, plus 1/4, that's me eating at dinner. So this should give me 3/4. Now, we're not going to really talk too much about adding fractions here. This is something we'll cover later on. It's a little bit complicated, but basically, if you have the same denominator, so here you have a 4, and a 4, what you do is you keep that denominator the same, and you just add the numerators. So you see that this is 1 plus 1 plus 1. So my 1 slice from breakfast plus my 1 slice from lunch plus my 1 slice from dinner, that 1 plus 1 plus 1, that gives me 3 slices that I ate out of a total of 4 slices in that whole pizza. So now that we understand that we should get 3/4 from 1/4 plus 1/4 plus 1/4, what we can do is transform this into a related multiplication statement. Remember, if you have something like, let's say 3 times 5, this is going to be 5 plus 5 plus 5. So either way, whether you do the multiplication from the multiplication tables or from the repeated addition here, you're going to get 15. So the same thing should be true here. If I write this as 3, because I have 1, 2, 3 of these guys, times 1/4, I should get 3/4. And how would we do that? Well, you could write 3 as 3 over 1. 3 divided by 1 is going to be 3. So I haven't changed anything. And then you could just multiply the numerators together. 3 times 1 would give me 3. And then you could put that over the product of the denominators. So 1 times 4 would give me 4. So that's how you would get 3/4. So you'll see me say we want to multiply the numerators together, put this over the product of the denominators. All right, let me give you another example here because it's not going to be that straightforward when you see something like, let's say 1/2 times 1/4. Well, what in the world does this mean if you try to translate it into repeated addition? We saw that when we had 3 times 1/4, this became 1/4 plus 1/4 plus 1/4 if we write it as a repeated addition. But if I write 1/2 times 1/4, well, I don't have 3 of these. What I want is 1/2 of this. So basically, it's like saying I want 1/2 of 1/4. So I have this first pizza, which is cut into 4 equal slices. What we're going to actually have to do is take this 1/4. Let me just mark this off right here. So this would be 1/4 of the pizza. And let me do this over here. Now this guy is cut into 8 equal slices. So let me mark this off. What you're going to have to do if you say that you want 1/2 of something, well, you need to cut it into 2 equal parts. So I'm going to slice this guy. Let me use a different color here. I'm going to slice this guy right here. And I want 1 out of those 2 equal parts. So I want this slice right here. Let me count these up. So this is 1, 2, 3, 4, 5, 6, 7, 8. So I want 1 slice out of a total of 8 equal slices. So this would give me 1/8. Because basically I'm starting with 1/4 of this whole amount. So 1 piece out of a total of 4 equal pieces. And I'm saying, hey, give me half of that. So it's kind of like I got this slice and I said, okay, well, we need to split it. So we split it like this, or I cut it in half. And now how much do I have? Well, I have 1 piece out of 8 pieces now, instead of having 1 piece out of 4 pieces. So this becomes the fraction 1/8. Now, when you look at it, again, it's the same procedure. Multiply the numerators. 1 times 1 would give me 1. And then put this over. You're going to multiply the denominators. 2 times 4 would give me 8. So 1/2 times 1/4 would give me 1/8. All right, let's take a look at some examples. So you'll find this process to be very, very easy. We have 2/5 times 1/7. So just following the procedure, we're going to multiply the numerators together. So 2 times 1 would give me 2. We're going to place that over. We're going to multiply the denominators together. So 5 times 7 would be 35. Now, 2 is a prime number, and 35, we just saw that came from 5 times 7. 5 is a prime number, and 7 is a prime number. So really, there's nothing here that I can cancel, right? The GCF is going to be 1. So we would say the simplified answer here is 2/35. All right, so here's one that's going to be a little bit tricky. So first, let's use our procedure. So we have 3/10 times 5/12. I'm going to multiply numerator times numerator. So 3 times 5 is 15. This is over denominator times denominator. So 10 times 12, that's 120. Okay, well, here is the problem. You see that this guy right here is the correct answer, 15 over 120, but it's not simplified. So if you report an answer and it's a fraction and it's not simplified, your teacher will probably at minimum take points off. Some of them will mark it wrong. It just depends on your teacher. So what you'd actually have to do is factor this, and you're going and undoing what you just did, right? So 15, you're going back to 3 times 5. And let me make that 3 a little bit better. And then for 120, if I break that down completely, 10 is going to be 5 times 2. And then 12 is 4, which is 2 times 2, and then times 3. Let me extend that a little bit. Now we know how to simplify fractions already. Basically, I'm looking at the numerators and the denominators, and I'm seeing what's common. So I can cancel this with this. 3 divided by 3 is 1. Now I would advise you at this point to put a 1 there. A lot of people will leave it off. It just depends on your preference. Some teachers will make you do it. Some teachers will tell you to put a 1 there and put a 1 there. And some teachers will say it doesn't matter. But the thing is, when you look at this one, I'm going to cancel this 5 with this 5. So I'm going to put a 1 here and a 1 here. Now, if your scratch work looks like this, let's say you get rid of all of this stuff. Well, the problem is the temptation for most students, they're going to say, okay, there's nothing in the numerator. I've canceled everything away. So they write a 0. Really, it's a 1, right? Because 3 divided by 3 was 1, and 5 divided by 5 was 1. So that's why if you put a little 1 there as a reminder, you can say, okay, well, I need to multiply 1 by 1. That's going to give me 1, and this is over. 2 times 2 times 2, that's going to be 8. So remember, it's just like I did the problem. 3 over 3 times 5 over 5 times 1 over, let's say 2 times 2 times 2, that's going to be 8. This is exactly going to give me the same answer as this. What happens is 3 over 3 is 1, right? So I can just say this is 1. 5 over 5, that's 1. So it's 1 times 1 times 1/8, which is 1/8. So this is the correct answer. You don't want to put a 0 up there. Okay, let me get rid of this. When we look at what we did, we double worked, right? First we multiplied, then we had to factor and break the multiplication back up, and then we canceled. What we actually want to do is cancel before we multiply. And this process is called cross-canceling. So to do this, you first want to look at your fractions and see, can I simplify them? So 3/10 can't do anything there. 5/12 can't do anything there. So once you're out of options there, you want to look at the numerator of this fraction, let's just say the left fraction, and the denominator of the right fraction. So this numerator and this denominator. And then you're going to do the same thing. Let me change my highlighter color here. So then this numerator and this denominator. And you're just going to ask the question, can I cancel any common factors between this numerator and this denominator, or this numerator and this denominator? Basically, are there any common factors between any numerator and any denominator? That's what you're asking. So to make this easier to see, I'm just going to break it down like we had it. So I'm going to put 3 over, we know 10 is 5 times 2, and then times, I'm going to put 5 over, 12 is 2 times 2 times 3. This 3 can cancel with this 3. So this numerator and this denominator, there's a common factor of 3. Again, I would put a 1 here. You can even put a 1 here if you want for clarity. You don't need it, but you can put it. Then here, you look at this numerator and this denominator, you can cancel this 5 with this 5. Again, you can put a 1 here and a 1 here. And then when you go through and multiply, well, 1 times 1 would give you 1. And this would be over. Let me make that a little bit better there. You would have, again, you can think about this as 1 times 2 or just 2, because 1 times anything is just itself. So really it's just 2 times 2 times 2, which is going to be 8. Again, this 1 would not change anything if you multiplied by it. So you end up with 1/8, which is the simplified answer. And notice that we didn't have to double work. We went ahead and canceled before we did the multiplication. So once we get our product, it's already simplified. All right, now that we understand the procedure, let me go a little bit quicker through the process. So we have 9 over 20 times 5 over 33. So I can't simplify this and I can't simplify this. Now, you could continue to do this and break it down all the way. So you could say this is 3 times 3 over 20 is 5 times 2 times 2. And then times, you have 5 over 33 is 3 times 11. You can do it this way, and then, again, I can just look at this numerator and this denominator. So let's cancel this 3 with this 3. Again, you could put a 1 here if you want and a 1 here if you want, just as a mental reminder. And then you can cancel between this numerator and this denominator, this 5 with this 5. So let's put a 1 here and a 1 here. All right, so this would give me what? So you have 3 times 1, which is 3, over, you're going to have 2 times 2, which is 4, times 11, which is 44. So you end up with 3 over 44 as your simplified answer. Now, let me show you a faster way to get this. Let me get rid of this, and we're going to go even faster. So here's how I do it. I would look at this guy and say, okay, well, 33 and 9, in my head, I'm immediately thinking, okay, well, 33 is divisible by 3. 33 divided by 3 is 11. So I'm going to cross this out and just put 11. Then 9 divided by 3 is 3, so I'm going to cross this out and put a 3. So basically, I'm dividing this guy by 3 and this guy by 3, and I'm just putting the result there. 33 divided by 3 is 11. 9 divided by 3 is 3. It's the same thing as if I factored and canceled. So this guy would look at 20, and I would look at 5. Well, 20 divided by 5 is 4. So cross this out, you could put a 1 there, and cross this out, you could put a 4 there. So 5 divided by 5 is 1. 20 divided by 5 is 4. It's a little bit faster than factoring. So now you just multiply 3 times 1, that's 3. And this is over 4 times 11, that's 44. Okay, let's look at one with 3 fractions involved. So we have 7 over 15 times 21 over 25 times 3 over 14. This is simplified, so is this, so is this. So what I would think about is 7 and 14 have a common factor of 7. So 7 divided by 7 is 1. 14 divided by 7 is 2. And then coming through here, now I have 21. Well, 21 is 7 times 3. Well, there's no 7 in any denominator now because I canceled this one away. But there is a 3. 21 divided by 3 would be 7. And then 15 divided by 3 would be 5. So I'm just canceling a common factor of 3 there. And then looking at this last one here, I have a 3, but this is a 5, this is 5 times 5, and this is a 2. So basically I'm stuck, I can't do anything else. So this would end up being what? 1 times 7, which is 7, times 3, which is 21, over, you'd have 5 times 25. You can stop and do a vertical multiplication for that. I think a lot of you do know that 5 times 5 times 5, or 5 cubed, is 125. So basically it would be 125 times 2, which is going to be 250. So 21 over 250 would be your simplified answer. Again, if that's a little too fast for you, you can always stop and break things up. So you can say that this would have been, let me do this down here. So 7 over 5 times 3, and then times 7 times 3 over 5 times 5, and then times 3 over 7 times 2. If you need to do this, it's fine. So I'm going to cancel this 7 with this 7. I'm going to cancel this 3 with this 3. And basically, that's it, right? So I'm just left with, I'm going to put a 1 here. Again, if I left that off, then I would have to go back and say, okay, well, this canceled, this is a 1. So a lot of times I leave that off because I know that, but for your scratch work, I think you should put it at this point so you're not confused. So this would be 1 times 7, which is 7, times 3, which is 21, over. You have 5 times 5 times 5. Again, that's 125 times 2, which is 250. So if you want to do it like this, because it's a little bit easier for you right now, then it's fine to break up the numbers completely and factor everything into the product of primes. In a lot of cases, as you move forward, you won't need to do that because it's just a little bit too time consuming. Okay, let's talk about the next topic here. So we're going to multiply whole numbers by fractions. So we have 6 times 1/3. So this would be what? You just take 6 and put it over 1, and you multiply it by 1/3, and you can cross cancel here. 6 divided by 3 would be 2. Right, so basically this is 2, and it's 2 times 1, which is 2 over. Again, you could write a 1 there. 1 times 1 is 1. So this is 2 over 1, or 2. And if you think about this, 6 times 1/3, 6 times 1/3 would be what? Well, this is 1/3 plus 1/3 plus 1/3. Let me make that 3 a little bit better. Plus 1/3 plus 1/3, and then plus another 1/3. So if I had 1/3 of a pizza plus another third plus another third, at this point right here, I'd have a full pizza. So this is 1 pizza. And then I'm doing the same thing over here. So this right here, this would be another pizza. So 1 plus 1 is 2. So this tells me I should have 2 pizzas. Again, if you do this using the addition that we're going to learn about later, you would basically keep this denominator the same because it's called a common denominator. and you would just add the numerators. So 1, 2, 3, 4, 5, 6 of those guys. You'd basically have a 6 up there. So you'd have 6 divided by 3 basically, which is going to be 2. Okay, let's take a look at 7 times 3 over 49. So this would be 7 over 1 times 3 over 49. And I'm going to say that 49 divided by 7 is 7. So this is 7. So now basically this is a 1 right here. So you can just forget about it. You could say it's 1 times 3, which is 3, over 1 times 7, which is 7. But you could also say 1 times anything is itself. So you could just say, okay, this is going to be 3/7. All right, here we have 19 over 15 times 5 over 38 times 36. So basically what I would do is treat this as 19 over 15 times 5 over 38 times 36 over 1. Let's go through and see if we can cancel. So I know that 38 is 19 times 2. So for this one, this would cancel with this. This would be a 1, and this would be a 2. Again, 38 divided by 19 is 2. 19 divided by 19 is 1. Then here, 15 divided by 5 is going to be 3, and 5 divided by 5 is going to be 1. Now for this one, as you get faster, you're not going to say, okay, well, 36 divided by 3 is 12, and then you'll say, well, 12 divided by 2 is going to be 6. You would do that in one shot. So in other words, what you could have done here, let me get rid of these cancelings here. You could say that 36 divided by 6 is going to be 6, and then basically cross those out because 3 times 2 is 6. Now again, you can write this as a 1, or as you move forward, you're just going to realize that that's canceled, so it's 1. So basically, this is a 1, this is a 1, 1 times 1 is 1, and 1 times anything is itself, 6 over 1 is 6, so this gives me a final answer that's just going to be 6. All right, let's look at another one. So we have 4 over 15 times 5 over 24 times 7 over 12 times negative 4. Okay, so 4 over 15 times 5 over 24 times 7 over 12 times negative 4. I'm going to write that over 1. All right, let's think about what we can do here to cancel. So starting with the 4 divided by 4 is 1. 24 divided by 4 is 6. And then 5 divided by 5 is 1. 15 divided by 5 is 3. And then if we keep going, I have a 7 here. 12 is going to be 2 times 2 times 3. This is 6, this is 3, so I can't do anything with that. All right, then I have this negative 4. Let me write that as negative 1 times 4. And what you could do is divide 4 by 4, you get 1, and 12 divided by 4 would be 3. So looking at what I have left in the numerators, 1 times 1, you can forget about those, it's not going to change anything. Then times 7, so let's just start with 7. So basically 7 times negative 1, that is negative 7, and this is over. Down here you have 3 times 6 times 3. So 3 times 3 is 9. 9 times 6 is 54. And then times 1, that's still 54. So this would give me negative 7 over 54 as my answer. All right, let's take a look at 2 quick word problems. So we have Fred spent 2/5 of his $50 allowance on comics. How much did he spend? So this is typical. When you see 2/5 of this $50, so what you're going to do is take 2/5 and multiply it by 50. And so I'm going to cancel this 50 with this 5. 50 divided by 5 is 10. Again, you could put a 1 down there if you want, and then just multiply. 2 times 10 is going to be 20. Again, you can go over 1 if you want, but it's just going to be 20 at the end of the day. So when it asks how much money did he spend, the answer is going to be $20, right? That's 2/5 of his $50. All right, now we have a recipe requires 1/2 cup of sugar. If we only want to make 3/4 of the recipe, how much sugar is needed? So again, just take 3/4 and multiply it by 1/2. And what is this going to give me? Nothing's going to be able to cancel here. This is simplified. This is simplified. 3 and 2, 1 and 4. Nothing I can do. So just multiply 3 times 1, that's 3. Over 4 times 2, that's 8. So basically, we could say that you would need 3/8 cup of sugar. Hello and welcome to Pre-Algebra Lesson 31. In this video, we're going to learn about dividing fractions. All right, so the lesson objectives for today, we want to learn how to find the reciprocal of a number, and then additionally, we want to learn how to divide fractions. All right, so now we're going to talk about how to find the reciprocal of a number. This is something we need when we start dividing fractions in a little while. So to find the reciprocal of a number, we interchange the numerator and denominator. So what do I mean by interchange? Well, let's start with a simple example. Let's say we had the fraction 4/5, and I want to interchange the numerator and denominator. Well, basically, I'm going to take this denominator from the fraction that I'm starting with, and that's going to become the numerator for the reciprocal. So this would be a 5 up here. And then let me put my fraction bar. I'm just going to take this numerator here from the fraction that I'm working with and drag that down into the denominator for the reciprocal. So the numerator becomes the denominator, and the denominator becomes the numerator. That's what I mean by interchange the numerator and denominator. So the reciprocal of 4/5 is going to be 5/4, and you could reverse that and say the reciprocal of 5/4 would be 4/5. Now, when we multiply a number by its reciprocal, the result is always going to be 1. So let's say we go back to 4/5, and the reciprocal is 5/4. So why is the result going to be 1? Well, think about it. This denominator becomes this numerator. So it's basically 5 over 5, which is 1, right? You can cross cancel here. Let's just put a 1 here and a 1 here. And then this numerator becomes this denominator. So it's 4 over 4, that's 1. So cancel this with this, and I'll put a 1 here and a 1 here. Well, if you multiply these together, you can just think about this as 1 times 1. That's going to give you 1. All right, so now let's look at a few problems. We are asked to find each reciprocal. So we are given 2/3. If you want to find the reciprocal, again, I'm just going to take this denominator and drag it into the numerator. And then I'm going to take this numerator and drag it down into the denominator. So the reciprocal of 2/3 will be 3/2. Again, you can go 2/3 times 3/2 if you want to check your work. So 2 over 2 is 1, and then 3 over 3 is 1. And so you have 1 times 1, which is 1. Again, the product here should always be 1. Okay, what about 8/9? So again, let's take this denominator here, bring it up into the numerator. Let's take this numerator here and drag it down into the denominator. So the reciprocal of 8/9 is going to be 9/8. All right, what about one with a negative involved? So let me take some time with this one. So if you have this set up here, the first thing you could do is just put a negative out in front, and then basically you could interchange the numerator and denominator. So I could bring the 5 up here, and then I could bring the 1 down here. So the denominator becomes the numerator becomes the denominator, and I just basically copied the negative sign. So the reciprocal here is -5 over 1, which is just -5. But there's other ways that you could have thought about this. You could say that this is equal to -1 over 5. You could also say this is equal to 1 over -5. Remember, a negative divided by a positive or a positive divided by a negative, that's going to give you a negative in each case. So 3 different ways to write the same thing. So you could choose to do it this way. You could say this is -1 over 5, and then you can bring this denominator up into the numerator, and you can bring this numerator down here into the denominator. So either way, it's going to be -5, right? 5 over -1 is just -5. Okay, let's look at one more problem. So now we're given an integer. So we have -4. So what are we going to do? Well, basically you want to change this into a fraction by writing it over 1. So I can write -4 over 1 like this. Dividing by 1 leaves the number unchanged. So this is still -4. So now I'm just going to take this denominator and bring it up into the numerator, and take this numerator, bring it down into the denominator. So the reciprocal of -4 is basically -1/4. You can write this again as -1 over 4, or you could write it as 1 over -4 as we have here, or you can say it's -1/4, whatever you want to do. All right, now let's move on and talk about dividing fractions. So I have here to divide fractions. We multiply the first fraction. So that's going to be your fraction on the left. We call that the dividend in your division problem, by the reciprocal of the second fraction. So that's the fraction on the right. That's going to be your divisor in the division problem. So for example, let's just say I had something like 3/8 divided by 1/2. This first fraction, or the leftmost fraction, would be unchanged. So you would just copy that down. Then you would multiply by the reciprocal of the second fraction, or the fraction on the right. So this is times 2 over 1. So basically at this point, it's just a multiplication problem. So between 8 and 2, there's a common factor of 2. 8 divided by 2 is 4. 2 divided by 2 is 1. And then you would multiply 3 times 1, that's 3, over 4 times 1, that's 4. So the answer here would be 3/4. All right, so the process of dividing fractions is pretty easy overall, but some people have a really difficult time understanding where the process comes from. So on the next 2 examples, I'm really going to break this down. I'm going to start off with a whole number divided by a fraction. I think that's the easier one to understand. So I'm just going to start off with some things we already know. So right now I have 4 boxes on the screen, and I'm just going to say this is 1, 2, 3, and then 4, just to count them out. Now let's suppose I asked you, what is 4 divided by 4? what does that mean again? Let's go back to basic division. Well, I'm asking how many equal groups of 4 can be made from 4. So here I have 1, 2, 3, 4. So this whole thing would be a group, right? So this would be a group of 4. So 4 divided by 4 would be 1. I can make one of those groups. I think we all know that at this point. Let me get rid of this. And let me change the problem up. So let's say we said 4 divided by 2 now. So we know this equals 2. But again, I'm asking how many equal groups of 2 can be made from 4? Well, here's a group, right? So 1, 2, and then another 1, 2. So 4 divided by 2 would be 2. Now, what if I change this up a little bit and I said, what is 4 divided by 1/2? Well, using the procedure I just gave you, you could write 4 as 4 over 1 and then multiply by the reciprocal of this, which is 2 over 1. So that should give me 8. Well, let's think about this down here. What does it mean to have 1/2 of something? Well, it means I have a whole amount. Let's say it was a pizza, or in this case, a box, and I split it into 2 equal parts. And then each part is 1/2. So this right here is 1/2, and this is 1/2. Then this is 1/2, and this is 1/2. This is 1/2, and this is 1/2, and then this is 1/2, and this is 1/2. So if I go through and just count them, how many 1/2s do I have? Or how many 1/2 of a boxes do I have? Well, I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, that starts to make a little bit of sense in terms of why I got 8 as the answer. When I say 4 divided by 1/2, what I'm actually asking is how many equal groups of 1/2 can be made from 4? Well, what you need to do is start out with the fact that you have 4 of these guys, so 4 boxes. So I'm just going to write that. And then in each box, there's going to be 2 half boxes, right? So 2 half boxes. So I need to actually multiply by 2 because here I'm getting 2, here I'm getting 2, here I'm getting 2, and here I'm getting 2. So that's why this turns into the problem 4 times 2, which gives us 8. If we go a little bit further and we think about something like 4 divided by 1/4, well, it's the same principle here. Let me go through and write these in. So this is 1/4, this is 1/4, this is 1/4, and this is 1/4. Okay, so thinking about this, if you went through and counted, what would you have? So this is 1, 2, 3, 4, and then you have 4 of those, so that's 16. So basically this turns into 4 of these boxes, 1, 2, 3, 4, and then in each box, there's 4 1/4. So I'm just going to do 4 times 4. So this becomes 16. Again, 4 stays the same, multiply by the reciprocal of 1/4. The reciprocal of 1/4 is 4 over 1, or just 4, so this becomes 16. Okay, let me give you an alternative way to look at this. A lot of people will teach this with what we call a complex fraction. So let's say we had 4 divided by 1/2. So I'm going to write this as 4 over 1 divided by 1/2. Now, we haven't talked about complex fractions yet. We're going to get to them later on in the course. For right now, a complex fraction is a fraction that contains another fraction in its numerator, its denominator, or both. So basically, all I'm going to do is take this part right here, which is the dividend, and I'm going to bring that up here into the numerator of the complex fraction. So this is 4 over 1. So this right here is the numerator. And then I'm going to have my fraction bar. So this is the fraction bar for the complex fraction. You could think about it as the main. So the main division. And then down here, I'm going to grab my divisor, and that's going to become my denominator here for the complex fraction. So this is 1/2. And let's just say that this right here would be your denominator. Okay, so the idea with this method is you're just going to transform the denominator into 1. And in order to do that, you would multiply this 1/2 by its reciprocal, which is 2 over 1. A number times its reciprocal is always 1, like we talked about earlier. But to make that legal, you'd have to also do that to the numerator. So the problem is 4 over 1 over, and then you have 1/2. And all I'm going to do is multiply the denominator by 2 over 1. And to make that legal, I'm going to multiply the numerator by 2 over 1. So I'm basically just multiplying the numerator and denominator of the complex fraction by 2. And this would be equal to what? Well, these guys down here, these are reciprocals. So 2 over 2 is 1. So let me put a 1 here. 1 times 1 would just be 1. So the denominator of the complex fraction is 1 now. Then up here, I just do 4 over 1 times 2 over 1. So 4 times 2 would be 8. You could put over 1, I guess, if you wanted to, but 8 over 1 is just 8. So at the end of the day, this is 8 over 1, which is 8 over 1, which becomes 8. So that's another way to show where it comes from. Again, you can use either method to prove it to yourself and think about how things work. I like using the visual example with the boxes, but some people prefer this method. All right, let's look at one that's a little bit more complicated to explain. So suppose you had 1/2 divided by 1/8. Again, let's use the procedure to start. So 1/2 times the reciprocal of 1/8 is 8 over 1. And so essentially, you can think about 8 and 2 have a common factor of 2. 8 divided by 2 is 4, and then 2 divided by 2 is 1. So this is canceled. You could just write this as a 1. So it's basically 1 times 4, which is just going to be 4. How can we show this and prove that we should take 1/2 and multiply by the reciprocal of 1/8? Well, again, you could have written this as a complex fraction. So you could do that again. So you could say this is 1/2 over 1/8. And again, if I want to make this denominator for the complex fraction into 1, I'm going to multiply by the reciprocal of this fraction here. So this is times 8 over 1. And then I'm going to do that to the numerator to make that legal. So you see that this right here is going to cancel. So this is a 1, and you could put a 1 down here. So this is a 1 now. And so this would be equal to, well, basically it's this 1/2, which we're starting with over here on the left, times this 8 over 1, which is the reciprocal of this rightmost guy here, this 1 over 8. So we end up with what? Again, like we just did, 8 divided by 2 is 4, and 2 divided by 2 is 1. So this is just 1 times 4, which is going to be 4. I mean, you can go through and say this is 4 over 1, and then over 1, and then this becomes 4 over 1 like this, and this is 4, but I think we can all see that this is 4. All right, let me give you a visual explanation in terms of why 1/2 divided by 1/8 ends up giving you 1/2 times, take the reciprocal of this, it's 8. So this ends up giving you 8 over 2 is 4. Okay, so we've seen this already using the complex fraction method. But if you want to look at this visually, what you would need to do, because you're dividing by 1/8, just start with some whole amount. You could take a pizza, a box, whatever you want to work with, and you're going to divide it up into 8 equal parts. If you're working with a pizza, you're going to have 8 equal slices. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8. If I was asking myself the question, how many groups of 1/8 would be in 1? It's 1 divided by 1/8. This would be 1 times, take the reciprocal of this, it would be 8. So this is 8. And you can go through and count that. I have 1, 2, 3, 4, 5, 6, 7, 8 1/8 in this whole pizza. Now, I don't have a whole pizza. I only have half of a pizza. So let's mark this out like this. So maybe this is going to be my half of the pizza. And I'm not really good at drawing, so I'm going to go over. But basically, if you ask yourself the question, well, how many 1/8 are there in 1/2? Well, you have 1, 2, 3, 4. So it makes sense that we're getting 4. We can visually see that. But again, why do we end up multiplying by 8? Well, 8 is the number of slices or equal parts in the whole amount. And then I don't have a whole amount. I only have half of that. So you're asking yourself the question, what is 1/2 of 8? And that's how we end up getting 4. So that's how you want to think about this. So hopefully this makes sense for you visually. You can always pause the video and think about it, or make your own example with a pizza or boxes or whatever you want to use. All right, so now that we understand the procedure, let's just blow through some problems. I think you're going to find this to be really easy once you get started. So we have 2/3 divided by 4/9. So leftmost fraction, you're going to leave that unchanged. And then we're going to multiply by the reciprocal of the rightmost fraction. So basically, I'm going to take 4/9 to find the reciprocal. That's going to be 9/4. The numerator becomes the denominator becomes the numerator. So now we can just go through and multiply. Let's cross cancel. So basically, between 2 and 4, you have a common factor of 2. So 4 divided by 2 is going to be 2. 2 divided by 2 is going to be 1. And then between 9 and 3, you have a common factor of 3. So 9 divided by 3 is 3. And then 3 divided by 3 is 1. So this right here is canceled, right? This is a 1. So basically, you're just going to have 1 times 3/2, which is 3/2. So that's going to be your answer. What about 6/7 divided by 15 over 28? So the leftmost fraction, the first fraction, stays unchanged. And we're going to multiply by the reciprocal of the second fraction or the rightmost fraction. So this 28, the denominator, becomes the numerator. Then this 15, the numerator, becomes the denominator. So the reciprocal of 15 over 28 is going to be 28 over 15. Okay, now we're ready to do some multiplication. So basically looking at 28 and 7, well, 28 divided by 7 is 4. So 28 divided by 7 is 4, and 7 divided by 7 is 1. So then between 6 and 15, each is divisible by 3. So 15 divided by 3 is 5. 6 divided by 3 is 2. So what I'm left with is 2 times 4, which is 8, so that's my numerator, over 1 times 5, that's 5, that's my denominator. So our answer here is going to be 8/5. What about 1/3 divided by 7? So the leftmost fraction, 1/3, we're going to keep that unchanged, and we're going to multiply by the reciprocal of what's on the right. Now, again, if this is not a fraction, if it's an integer or a whole number or something like that, then basically you're going to write it over 1. So let me actually change this up a little bit. Let me put divided by 7 over 1. And so this equals, you'd have 1/3 times the reciprocal of 7 over 1 is 1/7. So again, this 7, which is the numerator, becomes the denominator. This 1, which is the denominator, becomes the numerator. Now we just multiply. So nothing to cancel here. So 1 times 1 would be 1 over 3 times 7. That's going to be 21. So you get 1 over 21 as your answer. What about 2/9 divided by -4? So again, we can go 2/9 divided by -4 over 1. So let's say this equals, you have 2/9. So leftmost fraction, that's unchanged. And then times the reciprocal of the rightmost fraction. So again, the reciprocal here, let's just write -1 over 4. Again, you could write the negative down here if you want, or you can put it out in front. It really doesn't matter because when you're multiplying, a positive times a negative will give you a negative. So you could just put the negative sign in there and then forget about the signs and just work with the absolute values. So looking at it now, you can see that you have 9 and 1, nothing you can really do with that. And then you have 2 and 4. So there's a common factor of 2. So 4 divided by 2 is 2. 2 divided by 2 is 1. So we already know that this is negative. So let's just multiply 1 times 1. That's going to be 1 over 9 times 2. That's going to be 18. So the final answer here is -1 over 18. What about 12 divided by 1/3? So let's write this as 12 over 1. And then basically, instead of divided by 1/3, I'm going to go times 3 over 1. So this guy stays unchanged. I just wrote 12 as 12 over 1. And then I'm multiplying by, I'm just going to take the reciprocal of 1/3. So 3 comes up into the numerator, 1 goes down into the denominator. So now you just multiply. So 12 times 3 is 36. And this is over 1 times 1, that's 1. And of course, anything over 1 is just itself. So this just is equal to 36. All right, let's take a look at the next one. So we have -7 over 24 divided by 9 over -8. Okay, so what I'm going to do here is say the first fraction, -7 over 24, is unchanged, and then times the reciprocal of this fraction. I'm just going to put the negative out in front, and then I'll write 8/9 like this. Let me make these negatives a little bit better here. So this is -7 over 24 times -8/9. Okay, so we know that negative times negative is positive. You can put that there as a little reminder and then erase it or scratch it out after, or you could just leave it. It doesn't matter. And then I'm just going to work with the absolute values. So forget about the negative signs now. I'm going to think about, okay, well, 24 and 8, there's a common factor of 8. 24 divided by 8 is 3. 8 divided by 8 is 1. And then 7 and 9, nothing really in common there. 7's a prime number and 9 is 3 times 3. So what I'm going to do is multiply. We're going to say 7 times 1 is 7. Remember, I already know this is positive, so forget about the negatives here. And then down here, I have 3 times 9, that's going to be 27. So again, you can erase this at this point. You know it's positive. So you would say the answer is 7 over 27. All right, let's take a look at a problem with 2 divisions involved. So here we have 3/5 divided by 21/10, and then divided by 9/11. So the way I would do this problem, I would convert these divisions into multiplication by the reciprocal. It's just going to make it a little bit faster. The other way you could do it is you could do 3/5 divided by 21/10. So you could find that result and then divide that by 9/11. So that's up to you. It will give you the exact same answer. I'm going to do this as 3/5. I'm going to convert this division to multiplication by the reciprocal. So times 10 over 21. And then I'm going to convert this division into multiplication by the reciprocal. So times 11 over 9. So once you have it written this way, now it's a little bit easier because I can go through and just cancel things in one shot. So I can say, are there any common factors that I can cancel away between any numerator and any denominator? So looking through here, I have a 3 here and I have a 21 here. So 3 divided by 3 is 1. 21 divided by 3 is 7. So now looking at 10 and 5, well, yeah, 10 divided by 5 would be 2. 5 divided by 5 would be 1. Now looking at everything else, it looks like I'm basically done. So I would just multiply the numerators. 1 times 2 times 11, that's going to be 22, and put that over. You'd multiply the denominators. 1 times 7 times 9, that's going to be 63. So the answer here would be 22 over 63. And again, if you want to pause the video and try it a different way, you can do this division first and then get that result and then divide by this. You will still get 22 over 63.
Hello and welcome to Pre-Algebra Lesson 32. In this video, we're going to learn about finding the LCM, otherwise known as the least common multiple. So our lesson objective for today is just to learn how to find the least common multiple, again that's abbreviated LCM, for a group of numbers. So before we start talking about finding the least common multiple, we have to have a general understanding of what a multiple is. And there's a lot of different definitions that kind of float around, but for the purposes of pre-algebra, we're going to use this one. So to obtain the multiples of a number, we multiply the number by each non-zero whole number. So in other words, if we think about the whole numbers, remember they start with 0 and increase in increments of 1 out indefinitely. So all I'm going to do is exclude 0 from this list. So in this case, I'm going to start with 1 and increase in increments of 1 out indefinitely. So I'm going to take a number, multiply it by 1, then 2, then 3, then 4, then 5. Each result is a multiple of that original number. So let me give you an example. So let's take a look at finding the multiples for the number 3. So again, we want to multiply 3 by each non-zero whole number to obtain the multiples. So I'm going to start out with 3 times 1. So 3 times 1 is 3. Then I'd move on to 3 times 2. 3 times 2 is 6. Then I'd go to 3 times 3. 3 times 3 is 9. Then 3 times 4. 3 times 4 is 12. Then 3 times 5. 3 times 5 is 15. And you can kind of see where I'm going with this, right? I'm starting with 1. And then I'm increasing in increments of 1. So I'm multiplying by 1, then 2, then 3, then 4, then 5. And if I continued, it'd be 6, then 7, then 8, so on and so forth. But really, you can just list the multiples. You can kind of see that we're just increasing in increments of 3 every time, right? So if I think about kind of the multiples of 3, we have 3, then 6, then 9, then 12, then 15. And again, we're increasing in increments of 3. So then after 15 comes 18, then 21. And I'm going to put 3 dots here to say this pattern is going to continue forever, right? Increasing in increments of 3. And I'm just going to put here that these are the multiples of 3. Let's take a look at another one. What if I asked you to find some multiples of 11? So I take that number 11, and again, I'm going to multiply it by each non-zero whole number. I'm just going to start with 1 and just increase. So 11 times 1 is 11. Then 11 times 2 is 22. Then 11 times 3 is 33. Then 11 times 4 is 44. Then 11 times 5 is 55. And obviously you can continue this forever, right? There's no largest whole number. After 5 would be 6, then 7, then 8, so on and so forth. But I just want to generate a few of them so you can get an idea of what a multiple is. So let's write the first few multiples for 11. So it's 11, 22, 33, 44, 55. Then it would be what? 66, right? We're increasing in increments of 11. Then 77. And of course, at some point I can stop and put 3 dots to say, hey, this pattern where we're increasing in increments of 11 is going to continue forever. So these are some multiples of 11. So now that we have a basic understanding of how to find the multiples of a number, let's introduce this next concept called finding common multiples. So common multiples are just multiples that are common to all numbers of a group. So let's say that we have 2 numbers, and these 2 numbers, let's say they're 4 and 5. So let's say I want to find the multiples. Find the multiples of 4. So I'm going to write them just right here. So I'd start with 4, right? Because that's 4 times 1. Then I'd increase in increments of 4. So I'd go to 8, then 12, then 16, then 20, then 24, then 28, then 32, then 36, and I'm going to continue this down here. Then 40, then 44, then 48, then 52, then 56, then 60, and I'm going to put comma, dot, dot, dot. So the 3 dots just tell me that, hey, we're going to keep increasing in increments of 4 out indefinitely. And again, the way I figured this out is I start by multiplying 4, the number that I want to find the multiples for, by each non-zero whole number, just starting with 1. So 4 times 1 would be 4. And I'd increase to the next largest whole number. So now I'd multiply by 2. 4 times 2 is 8. Between here and here, I just increased by 4. So that's how I knew to go from 4 to 8. Now when I multiply by 3, I'm just increasing by 4 again. Right? This is plus 4. And I'm going to do that again. This is plus 4. So now I'm going to go to 12. And you just keep doing that. 12 plus 4 is 16. 16 plus 4 is 20. 20 plus 4 is 24. Again, so on and so forth. Now, if I did the same thing for the number 5, let's say I want to find the multiples of 5. So I would start out with 5 times 1, and that's going to give me 5. Then 5 times 2 is 10. Then 5 times 3 is 15. Each time, I'm just increasing in increments of 5. So then I'd have 20, then 25, then 30, then 35, then 40, then 45, then 50, then 55, then 60. And we're going to stop there. Okay, again, the 3 dots are telling me that this pattern, where we're increasing in increments of 5, is going to continue forever. Now, what's important here is to look through these 2 lists that we've generated. The list that we have for the multiples of 4 and the list that we have for the multiples of 5, we want to see what's common to both. Meaning, what number do we have in this list that's also in this list? So looking through here, I see that 20 appears here and also here. I see that 40 appears here and also here. And I see that 60 appears here and also here. So what it looks like is that every 20 numbers, we're going to have a multiple that's common to 4 and 5. Right? The next one would occur at 80. Right? If you went through here, you'd have 60, then 64, then 68, then 72, then 76, and then 80. And here you'd have 60, 65, 70, 75, 80. So it would next occur at 80, then 100, then 120, so on and so forth, just every 20 numbers. So we can see that we'd have an unlimited number or an infinite number of common multiples between 4 and 5 because these numbers continue forever, right? They're not going to stop. But what's important for this lesson is to be able to see what the least common multiple is, meaning what's the lowest in value. And that occurs here at 20, right? At 20. That's where it first happens, and that's the lowest in value, right? 20 is less than 40, it's less than 60, it's less than 80, it's less than all the other common multiples that will come in the future if we were to list out all the multiples. Let's try another one. Let's say we wanted to find the least common multiple between 15 and 20. So let's say we had 15, and we want to find the multiples for that number. We'd start out with 15 times 1, that's 15. Then you go to 15 times 2, that's 30. Then 15 times 3 is 45. And again, you can see that you're just increasing in increments of this number, right? I'm going up by 15 each time. So after 45 is 60, then 75, then 90, then 105, then 120, so on and so forth. I'm just going to put the 3 dots to say, hey, we're going to keep increasing in increments of 15 out indefinitely. Now, what about the multiples for 12? So for 12, we'd start at 12 and just increase in increments of 12 out indefinitely. So 24, 36, 48, 60, 72, 84, 96, 108, and let's put 120, and comma, dot, dot, dot. Again, the 3 dots are telling me that that pattern, where we're increasing in increments of 12, is going to continue forever. Now, when I look through the 2 lists here, I'm looking for multiples that they share, otherwise known as common multiples. So the first one's going to actually occur at 60. Right? We have a 60 in this list and a 60 in this list. And then you're going to see that they have common multiples at 120. Right? So 60 more. Started at 60, then it goes 60 more, and it happens again. And then it'll happen again 60 more after that. So it would happen at 180. And then it would happen at 240. And then it would happen at 300. So on and so forth. But again, if we want the least common multiple, we want the lowest value. So we want this one that occurs at 60. The one that started it all, the first one that kind of appears between the 2 lists. And so the LCM of 15 and 12 we can kind of notate that this way, would be equal to 60. All right, that's the least common multiple. Again, 120 is a common multiple, but it's not the least common multiple. Very important that you understand that. So far we've found the least common multiple by just listing the multiples of each number and just looking for the smallest that's in common. Now this method is slow, it's tedious, and it's impractical. So when you start taking tests on finding the least common multiple, you're going to use a different procedure. And basically what you're going to do is you're going to use the prime factorization of each number to build your LCM. So we're going to cover this right now. So finding the LCM from each number's prime factorization. So the first thing you're going to do is you're going to factor each number completely. Then the next thing we want to do is list the prime factors of each number in a table. And this isn't completely necessary. It's just a way to kind of organize your numbers and see what you're going to need. The next thing you're going to do is generate a list that contains each prime factor. But I'm going to tell you that this is where people get tripped up at. Although you need each prime factor, when a prime factor is repeated between two or more numbers, include only the largest number of repeats from any of the prime factorizations. Now, this step right here, again, is going to cause a lot of confusion, especially if you've never found the LCM before. So just write this down, and as we practice, I'm going to explain what this means. Now, the last step is to just generate your LCM. And the LCM is just going to be the product of the numbers on the list that we have created. All right, so let's look at some practice problems. We want to find the LCM for each group of numbers. We're going to start with a pretty easy one. We want to find the LCM for 9 and 12. So the first thing we want to do is factor each number completely. At this point, you probably don't need a factor tree to factor 9 or 12. So 9 we know is 3 times 3. And 12 we know is 4 times 3. And 4 is 2 times 2. So now what we're going to do is make a little table to organize our factors. Just going to make it nice and clear for us to see what we have in common. So I'm going to make a nice little table. I'm going to put 9 here and 12 here. And when you make your table, you're looking for the smallest prime factor between any of the numbers. So the smallest prime factor is a 2 that occurs in 12. I have 2 factors of 2. So let's start out by doing that. And then if I look in 9, I don't have any 2s. So I'm just going to put like a little space here to say, hey, there's no 2s in 9. I'm just going to kind of X that out to say they do not share that. Now, the next thing I'm going to do is look for my next smallest factor, which is a 3. In 12, I have 1 of those. In 9, I have 2 of those. So I'm going to put a little space here to say they don't share a second copy of 3, although they do share 1 copy of 3. So let me just highlight that. Now, here's where it gets kind of tricky. For the LCM of 9 and 12, each and every prime factor that occurs between these numbers has to go in that list. So in other words, we have 1, 2, and then a second 2 that occurs in the prime factorization of 12. So that has to go in. We have 1, 3, and then a second 3 that occurs in the prime factorization of 9. So that has to go in. The tricky part is not including this 3 here that's in the prime factorization of 12. You might say, well, why not? If I put a third 3 in here, I would get a common multiple for 9 and 12, but I wouldn't get the least common multiple. When there's a prime factor that is shared, you only use the largest number of repeats. So in other words, when we look at this, we see that we have 3 that's shared between 9 and 12. Once I see that, I only put the largest number of repeats that occurs between the 2 prime factorizations. In the prime factorization of 9, I have 2 factors. In the prime factorization of 12, I have 1 factor. So the largest number of repeats would be 2 factors. So when I build the list for the LCM, it only gets 2 factors of 3, not 3 factors of 3. Okay, that's very important that you understand that. Once you have that down, you simply multiply the numbers on the list. 2 times 2 is 4, 4 times 3 is 12, 12 times 3 is 36, and we have our LCM. Right? The LCM of 9 and 12 is simply going to be 36. And if you wanted to verify that, you can go through and kind of list out the multiples of 9. So it would be 9, then 18, then 27, then 36, then 45, then 54, so on and so forth. And then for 12, you'd have 12, 24, 36, 48, 60, again, so on and so forth. You can immediately see that 36 is the least common multiple, right? 36 is the least common multiple. All right, let's take a look at another easy one. So we want the least common multiple for 8 and then 42. So 8 we know at this point is 3 factors of 2. 42, let's just use a factor tree for that. I know it's 21 times 2. 2 is prime. 21 is 7 times 3. 7 and 3 are prime. So 42 is going to be 2 times 3 times 7. All right, so let's build a little table just to organize these numbers. All right, so my smallest prime factor is a 2. So in 8, I have 3 of those guys. So 2 times 2 times 2. And in 42, I just have 1. So I'm going to put a blank space there and there. And then in 42, I have a 3. I don't have a 3 in the prime factorization of 8. And then I have a 7. I don't have a 7 in the prime factorization of 8 either. So I'm going to put some X's here to say that, hey, these aren't included. And we can look to see what's in common. And basically, they just have one factor of 2 that's in common, right? So when we build our LCM, for 8 and 42, we're going to, again, include every prime factor that occurs between the prime factorizations. Don't think about 2 for a second. 42 has a 3 and a 7. So I'm going to put 3 times 7. There's no 3 in 8, and there's no 7 in 8. So I don't have to worry about how many I'm going to put in. It's just going to be one occurrence for each number. When we get to this number 2, again, if it's something they share, you only put the largest number of repeats that occurs between the 2 prime factorizations. In the prime factorization of 8, we have 3 factors of 2. In the prime factorization of 42, I only have 1. So the largest number of repeats would occur in the prime factorization of 8, where I have 3. So that's what's going to go in my list. So I'm going to put 1, 2, 3 factors of 2 when I'm building my LCM. So now I just need to go through and multiply. 2 times 2 is 4, 4 times 2 is 8, 8 times 3 is 24, and then 24 times 7, 24 times 7, 7 times 4 is 28, 7 times 2 is 14, plus 2 is 16, so this would be 168 for my answer. All right, let's take a look at the LCM of 20 and 35. So 20 is going to factor to 10 times 2. 2 is prime. 10 is 5 times 2. 2 and 5 are both prime. 35 is simply 5 times 7. Those are each prime numbers. So let's go ahead and just make a table. For 20, I've got 2 times 2 times 5. 2 times 2 times 5. For 35, I don't have any 2's, so I'm just going to X those out. I do have a 5, and then I have a 7, which I don't have up here. So I can see that they just have one 5 in common between the two of them. So to build my LCM for 20 and 35, again, every prime factor between the prime factorizations of the number has to go in. So 2 goes in, then another 2 goes in. It's just when you have something that's shared, you put the largest number of repeats between the 2 prime factorizations. Now, the largest number of repeats is going to be 1. I have 1 5 in this prime factorization and 1 5 in this prime factorization. So when I build this, I only put 1 5 in my list. Right? I don't need 2, just 1. Right? The largest number of repeats when something is shared. And then I need to put this 7 in. So now everything is accounted for. I've got 1 2, I've got a second 2, I've got only 1 5 because they share it, and the largest number of repeats is 1, and then I've got a 7. So now I can just multiply. 2 times 2 is 4, 4 times 5 is 20, 20 times 7 I can do as 2 times 7, that's 14, and attach one trailing 0, and I get 140 as my answer. All right, let's look at the least common multiple for 16, 18, and then 30. So we're going to factor each number. So we've got 16. You can start out with 4 times 4. 4 is 2 times 2. And of course, 2 is prime, so we're going to circle all of those. For 18, let's do 9 times 2. 2 is prime, and 9 is 3 times 3. 3 is prime. For 30, let's do 6 times 5. 5 is prime, 6 is then 3 times 2. 3 and 2 are both prime. So let's make ourselves a little table. So we have 16, we have 18, and we have 30. So our smallest prime factor in any of the prime factorizations is 2. And in 16, I'm going to have 4 factors of 2. So 2 times 2 times 2 times 2. Now in 18, I only have 1 factor of 2. So I'm going to put a 2 here and then some blank spaces here. And let me just X those guys out. Then in the prime factorization of 30, I only have 1 factor of 2. And let me put some blank spaces there and X this out. So the next smallest prime factor is going to be a 3. So in 18, there's 2 of those. And then in 30, there's only 1. So I'm going to put a blank space here and here and here. And let me just X that out. And then the next highest is going to be a 5, and that's only in the prime factorization of 30. So I'm going to space that out and that out. Let's put an X there and there. And let's go down and build our LCM now. So the LCM for 16, 18, and 30. Again, we're going to include every prime factor from all of these prime factorizations. We're just going to have a special rule when any of them are shared. So in this example, they share 1 factor of 2. Everything has at least 1 factor of 2. So when that occurs, we put the largest number of repeats between any of the prime factorizations. 16 has 4 factors of 2, so that's what's going to go on our list. We're going to put 1, 2, 3, 4. Again, don't make the mistake of putting 6 in there. Don't say, okay, I have 1, 2, 3, 4, 5, 6. When there's something that's common, you want to put the largest number of repeats that occurs in any of the prime factorizations. Now, the next number we're going to look at is 3. And you'll notice that 3 is shared between these two prime factorizations. So since 3 is shared between these two prime factorizations, I want the largest number of repeats in any of the prime factorizations. And in this case, it's going to be 2 that occurs in the prime factorization of 18. So that means that we're going to have 2 factors of 3 when we build our LCM. And then the last number is 5. It only occurs in the prime factorization of 30. So we just throw that guy in there. We just need to multiply. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 3 is going to be 48. Times 3 again is 144. Then multiply by 5, you'll get 720. Now I don't want you to get confused on this problem. Some of you might say, okay, well, when we did this one, they didn't all have a factor of 3 in it. That doesn't matter. If you're working with 3 numbers, or 4 numbers, or 5 numbers, if the prime factor is shared with at least 2 prime factorizations, you're always going to go with the largest number of repeats that occurs in any of those prime factorizations. In this case, we had 2 factors of 3 that occurred in the prime factorization of 18. That's more than the 1 that occurred in the prime factorization of 30. So we put 2 factors of 3 when we built our LCM. And again, we get 720 as our answer. All right, let's take a look at one final problem. We want to find the LCM for 120, 40, and then 225. So these numbers are kind of big, but not really. So 120, it ends with a 0, so we know we could do 12 times 10. 12, we could do 4 times 3. 3 is prime. 4 is 2 times 2. 2 is prime. 10 is 5 times 2. 5 and 2 are both prime. For 40, we'll do 4 times 10. 4 is 2 times 2. 2 is prime, so we're going to circle those. 10 is 5 times 2. 5 and 2 are both prime. Then for 225, that's 15 times 15. 15 is 5 times 3. 5 and 3 are both prime. Let's go ahead and build our table now. So for this, I'm going to put 40 first. then 120, then 225. So the smallest prime factor that occurs is 2. In 40, you've got 3 of them. 1, 2, 3. In 225, you don't have any. And in 120, you have 3 as well. 1, 2, 3. So for 225, I'm going to space these out and just put some X's in here. Okay, so the next smallest prime factor is going to be a 3. In 40, we don't have any. In 120, we have 1. And in 225, we have 2. So I'm going to space out here and here and here. Let's put some X's here. The next smallest prime factor is going to be 5. In 40, we have 1. In 120, we have 1. And in 225, we have 2. So I'm going to space these out and put an X here and here. So now when we build our LCM, so the LCM for 40, 120, and 225, again, we're going to include in this list each and every prime factor from all of the prime factorizations. If something's repeated between at least 2 of the prime factorizations, we're going with the largest number of repeats for that prime number. So when I start out, I notice that 40 and 120 both have 3 factors of 2 in their prime factorization. I always want to go with the largest number of repeats. Now, the largest number of repeats is just 3, right? 3 factors of 2, they each have the exact same amount. So when I build my LCM, I'm going to have 2 times 2 times 2. Now, the next number that we come across is 3. Now, 3 is shared between 120 and 225, but there's more factors of 3 in the prime factorization of 225. You have 2 factors of 3 here, only 1 here. Again, when something's shared, you go with the largest number of repeats. So the largest number of repeats would be 2. That, again, occurs in the prime factorization of 225. So I'm going to put 2 factors of 3 when I build my LCM. Now, lastly, we have 5. Now, everything has at least one 5 in it. So again, if it's something that's shared, you go with the largest number of repeats. The largest number of repeats occurs in the prime factorization of 225. There's 2 5s there, so I put 2 5s in when I build my LCM. And now we just need to multiply. 2 times 2 times 2 is 8, times 3 is 24, times 3 is 72, times 5 is going to be 360, and then times 5 one more time is going to be 1,800. And again, that's going to be our LCM for 40, 120, and 225.
Hello and welcome to Pre-Algebra Lesson 33. In this video, we're going to learn about adding and subtracting fractions. So the lesson objectives for today, we want to learn how to add and subtract fractions with a common denominator. We want to learn how to find the LCD, which is the least common denominator of 2 or more fractions. And then we want to learn how to add and subtract fractions without a common denominator. All right, so let me read this before we get started. So when we add or subtract fractions, we must, meaning it is not optional, have a common denominator. So when they're exactly the same, that's what we mean by a common denominator. All right, let's just start off with some easier examples where we're already given a common denominator, and then later on we'll deal with the more complicated scenario where we don't have a common denominator and we need to get one. So let's say you had the problem 1/5 plus 2/5. Well, I want you to notice that the denominator here is 5 and the denominator here is also 5. So we have a common denominator, meaning the denominators are exactly the same. So that means that I can immediately start and I can add these fractions together. But how exactly do I add 1/5 and 2/5 together? Well, let's think about that with this little pizza here. Let's say that I buy a pizza and I split it up into 5 equal slices. So let's say this is 1, 2, 3, 4, and then 5. So I eat 1 slice of pizza. So let me mark this out. So this is the slice that I'm going to eat. Now we know at this point that we could represent the amount of pizza that I'm going to eat with this fraction 1/5. I'm taking 1 part out of a total of 5 equal parts. In the terminology of a pizza, I could say I'm getting 1 slice out of a total of 5 equal slices. Let's say that a friend comes over and now he's going to get 2 slices out of a total of 5 equal slices, or 2/5 of the pizza. So let's say he's going to take, let me change my color up a little bit. Let's say he takes this one and he takes this one. So how much pizza did we eat together? Well, that's the addition problem, 1/5 plus 2/5. So looking at this, easily I can just count and say it's 1, 2, 3 out of a total of 5 pieces of pizza. So that would be the fraction 3/5. 3 slices out of a total of 5 equal slices. How could we have gotten this 3/5? Well, what we would want to do is have this 1/5 plus 2/5 be equal to, we would add the numerators together. So my slice plus my friend's 2 slices, so that 1 plus 2, that's going to give me the 3 slices we ate. Now notice this part right here is not going to change. This denominator is going to stay as a 5. I'm not going to add those 2 denominators together. I have a common denominator, so I'm just going to leave that alone, and it's just going to keep moving forward as I simplify this problem. So I start off with 1/5 plus 2/5. This equals 1 plus 2, so this numerator plus this numerator, over the common denominator of 5, and then it ends up giving me 3/5. Now, when you get your answer, you want to think about, can I simplify? In this case, 3 is a prime number and 5 is a prime number, so really we can't do anything to simplify. So my answer here would just be 3/5. Let's just blow through a few of these problems. If you have a common denominator, it's going to be very, very easy. So we have 3/8 minus 2/8. So again, we have a common denominator. So all you have to do is perform the operations with the numerators and place that over the common denominator. When you're done, you're just going to simplify. So I'm just going to say this is 3 minus 2 over the common denominator of 8. 3 minus 2 is 1, and this is over the common denominator of 8. So this gives me 1/8. Now, can I simplify? No. So we'll just go ahead and leave 1/8 as the final answer. What about 7 over 13 plus 4 over 13? Again, what I want to do is add the numerators, so 7 plus 4, place that over the common denominator. I have a 13 and a 13, so this will stay as a 13. So this becomes what? 7 plus 4 is 11, so this is 11 over 13. 11 and 13 are both prime numbers, so the greatest common factor here would be 1, so this is simplified. 11 over 13 is your final answer. All right, let's look at 3/4 plus 1/4. So again, just perform the operations with the numerators. We're going to go 3 plus 1 over the common denominator here is 4. So this becomes 3 plus 1, which is 4, over 4. Now, of course, we can simplify because 4 over 4 is 1. Any non-zero number divided by itself is always going to be 1. You could think about this with a pizza. If you had a whole pizza and you split it up into 4 equal slices and you still had all 4 slices, well, then you still have 1 pizza. Right, so 4 out of 4 slices would give you 1 pizza. What about 3 over 15 plus 2 over 15? So this would be 3 plus 2, just add the numerators, over the common denominator of 15. So 3 plus 2 is 5, so this is 5 over 15. You could rewrite this, let me just do this down here. You could rewrite this denominator as 5 times 3. And then you can cancel. 5 divided by 5 is 1. Remember, if your numerator cancels completely, you want to write a 1. A common mistake there is to write a 0. So 5 divided by 5 is 1. It's almost like we did the problem like this. Let's say I did 5 over 5 times 1 over 3, right? If we did the multiplication, this would be 5 over 15, which is what we have. So now if I cancel, this divided by this is 1. And so basically you have 1 times 1/3, which is 1/3. So that's why we get 1/3 as the simplified answer. Okay, let's look at 7 over 20 minus 3 over 20. So this would be 7 minus 3, again, just working with the numerators, over the common denominator of 20. 7 minus 3 is 4, so this would be 4 over 20. And if I think about 20, it's 5 times 4. So let's go ahead and say this is 4 over 5 times 4. So I'm just going to cancel this with this. Let me actually use a different color there so it shows up better. So cancel this with this. And then what I'll do is put this as a 1. Again, you do not want to put a 0 there. That's very common when you mark this out to see a student. Leave that and then say, okay, this is 0 over 5. No, this is going to be a 1. 4 over 4 is 1. So this would be 1 over 5 or 1/5. Okay, let's take a look at 1/3 minus 2/3. So we're going to subtract 1 minus 2 over the common denominator of 3. So 1 minus 2 is actually going to give me a negative. So if we think about that, 1 minus 2, again, you can always convert this if you need to. You can say this is 1 plus a negative 2, and then just use your rules for adding integers. So this ends up giving me a negative because the larger absolute value is negative. And then you would basically do larger absolute value minus smaller. So 2 minus 1 would be 1. So this would end up giving me negative 1. A lot of you know that 1 minus 2, you have 1, you take away 2, you get negative 1. Okay, let me get rid of this. So this would be negative 1 over 3. Now it's important to realize that when you have fractions, if you have negative 1 over 3, this is equal to 1 over negative 3, which is equal to the negative of 1 over 3. So 3 different ways to write that. A negative divided by a positive is going to be equal to a positive divided by a negative, which is equal to just the negative of that guy. Okay, so 3 different ways to write that. It's actually really important that you understand that. And we're going to use that in an example coming up. Okay, let's look at this one. So we have 31 over 50 minus 6 over 50. So we're going to do 31 minus 6 over 50. So 31 minus 6 is going to be 25. So you have 25 over 50. And we know that we could write 50 as 25 times 2. So this would become 25 over 25 times 2. Let's go ahead and cancel this 25 with this 25. So again, that's going to be a 1. And this will be equal to 1 half. Okay, let's look at one more of these. So I'm just going to think about what happens when we have some negatives already. So we have negative 1 over 8 plus 5 over negative 8. So here's what I would do. Notice that you have an 8 and then a negative 8. You can legally move this up here, like we talked about a little while ago. So what I would do is rewrite this problem as negative 1 over 8 plus negative 5 over 8. That is completely legal. Again, 5 over negative 8, positive over negative, is equal to negative over positive. You have to have exactly the same denominators. So you need 8 and then 8. You could, if you wanted to, do negative 8 and negative 8, but I think it makes it a little bit more complicated to understand, so I'm not going to do it that way. When you look at it here, you have 8 and negative 8, so those are not exactly the same, so you need to do something like this here in order to do the addition. So now what I would do is say this is negative 1 plus a negative 5 over the common denominator of 8, and so here, I'm just going to put that this is going to be negative, add the absolute values, 1 plus 5 is going to be 6, so this is negative 6 over 8. Now we're not done because we can simplify. I think I grabbed too much there. So let me just move this over here and I'll just get rid of that and draw that back in. So with this one, what I would do is write negative 1 and then times 2 times 3. And then for 8, let's write 2 times 2 times 2. And I'm going to cancel a common factor of 2 between numerator and denominator. So let's go ahead and do this one with this one. You could write a 1, but it's kind of unnecessary here because the numerator is still going to have something. It's really necessary when the numerator is completely canceled out, and that's where you're tempted to write a 0. In this case, you won't have a temptation to do that. So I'm going to go ahead and say that the numerator would be negative 1 times 3 or negative 3. And this is over 2 times 2, which is 4. So this would be negative 3/4. So you could write it like this. You could write 3 over negative 4, or a lot of people just put the negative out in front. So you say negative 3/4. Whatever you want to do, it's all the same answer. All right, now let's talk about the more challenging procedure. So we're going to do adding and subtracting fractions without, so let me highlight that, a common denominator. So the first step is to find the LCD. So this stands for least common denominator. This is going to be the LCM, which is the least common multiple of the denominators. So this right here causes a lot of confusion. If someone asks you to find the LCD, they are just asking you to find the LCM of the denominators. That's all it is. Then I have here for the next step to write equivalent fractions with the LCD as each denominator. I'm going to show you how to do that momentarily. Then we're going to add and subtract the numerators and simplify. So these two steps right here, we already know how to do that because we just did a ton of exercises where we already had a common denominator and we would just add or subtract the numerators, place that over the common denominator, and then just simplify. All we need to do is figure out how do we get the LCD and then how do we write equivalent fractions with the LCD as each denominator. All right, let's jump in and just look at a problem. When we get done with this problem, I'll go back and show you why this makes sense using some pizzas again. So let's start off by finding the LCD. So the LCD is the LCM of the denominators. I know this is very confusing. The denominators here, you have 3 and 4. So you have 3 and 4. So forget about the fact that we said LCD. If I asked you for the LCM or the least common multiple of 3 and 4, what would you do? You would first say, okay, well, 3 is a prime number, so I'm not going to factor that. And 4 is 2 times 2. Well, everything has to go in. So 3 has to go in, and then 2 factors of 2, those are going to have to go in. There's nothing that's common between the factorizations. So basically, it's just 3 times 4, right? It's going to give you 12. So I'm going to erase this and say that this is going to be 12. The next part is a little bit tricky. So basically, you have 1/3 and you have 1/4. And we've said that the LCD, which is the LCM of the two denominators, is 12. So what I want to do is I want to rewrite each fraction as an equivalent fraction where 12 is the denominator. So how can we do that? Well, I could multiply the denominator here by 4, and I could multiply the denominator here by 3. Let me put my addition sign in. But is that legal to do that? Well, not if I just do it like this. What I would have to do is match this number from the denominator in the numerator. So I would do 4 over 4 here, and then 3 over 3 here. The reason this is legal is because 4 over 4 is going to be 1, right? So this equals 1. Any non-zero number divided by itself is going to be 1. And if I multiply by 1, I don't change the number. So it's just like I said, 1/3 times 1, well, that's 1/3. I am not changing the number. I'm just changing what it looks like temporarily so I can do my addition. Okay, so let me get rid of this. And we're going to first multiply. So remember, we're multiplying 1 times 4, numerator times numerator, that's 4. And this is over 3 times 4, that's going to be 12. So denominator times denominator. So plus 1 times 3, so that's going to be 3, over 4 times 3, that's going to be 12. So at this point, I have a common denominator. I have 12 and I have 12. So it's just like the problems we did earlier. So you're going to add your numerators. So 4 plus 3, put that over the common denominator, that's 12. And so 4 plus 3 is 7, and this is over 12. So it's really that simple. The only 2 additional steps you need to do is to first find the LCD, which again is the least common multiple, or LCM, of the denominators. So 3 and 4, you're looking for the LCM of those two numbers, you get 12. Then you're going to transform each fraction into an equivalent fraction where the LCD is its denominator. So think about, what do I need to multiply each denominator by to get to a denominator of the LCD? And then you got to match that in the numerator and the denominator so that you're multiplying by 1 so that it's legal. So once you've done that, you're at the point where we were at the beginning of the lesson where we had a common denominator, and then you can just add or subtract your numerators, put that over the common denominator, and then simplify. All right, let me quickly explain why 1/3 plus 1/4 ends up becoming 4/12 plus 3/12, which gives us 7/12 in the end. So I'm going to use an example with pizzas. I think it works out kind of nicely. So let's assume that I buy 2 pizzas that are completely identical, and when I first get them, they're not sliced up. So I take the first one, the one on the left, and I cut it up into 3 equal parts. So you could say I slice it up into 3 equal slices. So 1, 2, and then 3. Now if I eat 1 piece out of the 3 equal pieces here, well, I've eaten 1/3 of the pizza. So let's say I've eaten this right here. So that is going to be represented with the fraction 1/3. Then let's say this pizza over here, I'm going to cut it up differently. So let's say I go 1, 2, 3, 4 equal parts, or 4 equal slices since it's a pizza. And let's say that my friend, he's going to eat 1 slice here. So he eats this slice right here. So let's say plus 1/4. Well, if we try to figure out how much pizza we ate, we can't just immediately do this problem here. We know that we didn't eat a full pizza. Even though there's 2 pizzas here, the amount of pizza I ate plus the amount of pizza he ate, it's not even going to add up to 1 pizza. But we can't really figure out immediately what amount of a pizza we ate, because if I try to add this one to this one, well, those are not the same, right? So this slice is not the same size as this slice because the pizzas are cut up differently. Obviously, looking at the fact that these 2 pizzas are the same size, well, this 1/3 of the pizza is going to be more than this 1/4 of the pizza. So what can we do? We would have to slice the pizza up in such a way that we can add like parts of a whole amount. So what do I mean by that? Let's start again with this 1/3 and then plus this 1/4. So you see here now I have 12 slices. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, I don't have two pizzas here because between the amounts that me and my friend ate, it's not even going to be a full pizza. So I'm just transferring everything in terms of one pizza so nobody gets confused about having two pizzas. So what I'm going to do now is think about, okay, if I cut this up into 12 pieces here, because that's the LCM of 3 and 4, how can I transform this amount of pizza to match over here? Well, I'd multiply this by 4 over 4, like we did earlier. So that would end up giving me 4 over 12. So if I go through and look at it, well, I would have eaten 1, 2, 3, 4 pieces of pizza had it been split up in such a way that I had 12 equal pieces of pizza. And you can see that this would be 1/3, right? So you go 1, 2, 3, 4, that's a third. Then 5, 6, 7, 8, that's another third. Then 9, 10, 11, 12, that's another third. So I still ate a third of the pizza. It just looks different. Then plus, over here, I'd multiply this by 3 over 3. And so this would give me 3 over 12. So let's say that I take 5, 6, and 7 for that, and I'll use a different color. So my friend, he eats 5, 6, and 7. So now we can clearly see just by counting, it's 1, 2, 3, 4, 5, 6, 7, that it's going to be 7 pieces of pizza that were eaten out of a total of 12 pieces. We could have also just done 4 plus 3, which again gives us 7 over 12. All right, let's look at some examples now. So we have 1/4 plus 1/2. So what is the LCD? The LCD is the LCM of the denominators. So 4 and 2. So I think you know that that's going to be 4. Again, 4 is going to be 2 times 2, and 2 is a prime number. It's not going to factor. So basically, you want 2 factors of 2. You can think about this as 1, 2, and here you have 2 2s. So you want the largest number of repeats, and that's going to be 2 2s or 4. Let me get rid of this. And basically, in this particular case, the 1/4, you don't have to do anything with that because the denominator is already the LCD, which is 4. So then plus, for 1/2, you're going to need to multiply this by 2 over 2. And so this gives you 1/4 plus 1 times 2 is 2 over 2 times 2, that's 4. So this gives you 1 plus 2, which is 3, over the common denominator of 4. So 3/4 would be your simplified answer. 3 is a prime number and 4 is 2 times 2. So your GCF is going to be 1 there. So really that's your simplified answer. All right, let's look at 5 over 21 plus 3 over 14. So this one will be a little bit of work. So the LCD is the LCM of 21 and 14. And so 14 is 2 times 7. And then 21 is going to be 3 times 7. So when you build this, it's going to be what? You're going to put a 2 in. You're going to put a 3 in. And then you only put in 1 7. There's 1 7 here and 1 7 here. So if it's common, just put the largest number of repeats between any of the factorizations. It happens once here and once here, so only 1 goes in. And let's put equals here. 2 times 3 is 6. 6 times 7 is 42. So here we would say that we have 5 over 21, and then times, let me just put this here, plus 3 over 14, and then times, let me put this here. When you think about this, you can look at this list and say, well, what do I need to get to 42? Well, basically, you have 7 times 3, I would need a 2, right? So you can say 2 over 2. Also, you can take this and divide by this. So 42 divided by 21 is 2. Whatever you want to do. Sometimes people will erase this and then put this as 42. And they've lost that information, so they start freaking out. Just you can take this and just divide it by this, and 42 divided by 21 would be 2, so I need to multiply by 2 so that I can get to 42. Then over here, I would need 3 over 3. 14 times 3 would be 42, so this would be equal to what? 5 times 2 is 10, over, we know that the denominators are 42, so you can just write them in, and then 3 times 3 is 9, and this is over 42. So now 10 plus 9 would be 19, over the common denominator of 42. So 19 is a prime number, and we know 42 is 2 times 3 times 7. We just factored it. So the GCF here is 1. So this is as simple as you can get it. 19 over 42 is your answer. All right, let's look at one that's a little bit tricky. So we have negative 7 over 3 plus 2 over negative 15. The idea here is that if you have a negative in the numerator or the denominator, what I would say is to put them in the numerator. Okay, so here it's in the numerator. I'm just going to move this up here. So I'm going to say this is negative 7 over 3, and then plus negative 2 over 15. You don't want to have opposite signs in your denominators. You want to make sure that when you get a common denominator, they're exactly the same. They can't be opposites. So you wouldn't want to end up with 15 and negative 15. Here, when you think about the LCD, which is the LCM of 3 and 15, Well, 3 is a prime number, and 15 is 3 times 5. So basically, the 3 goes in and the 5 goes in. The 3 only goes in once because you have it here and you have it here. So you're only putting in 1. So it's just going to be 15. So this would just be, let me erase this, and I'll just put that the LCD is equal to 15. We can say this equals, we'll have negative 7 over 3. I'm going to multiply this by 5 over 5 because 3 times 5 is 15. And then plus you have negative 2 over 15. So I don't need to mess with this one because the denominator is 15 and that's the LCD. So don't do anything there. So I'll say this equals, negative 7 times 5 is negative 35. This is over, 3 times 5 is 15. And then plus you have negative 2 over 15. Let me slide down a little bit here. So this equals what? You would just add the numerators, negative 35 plus negative 2. We know that's negative. And then add the absolute values. 35 plus 2 is 37. So this is negative 37 over 15. Now you could write this as a mixed number if you want. It's really up to you because you have an improper fraction here. So you could leave it like this. 37 is a prime number, so you're not going to be able to simplify. But you could say that this is negative what? So you could say 37 divided by 15. 15 goes into 37 twice. 2 times 15 is 30. Subtracting, you get 7. So that's your remainder. So you would say that this is negative 2 and then 7 over 15. Okay, so you could write it like that if you wanted to, or you could keep it like this, negative 37 over 15. Really, it's personal preference unless your teacher tells you which one they want. All right, let's take a look at 11 over 12 minus 3 over 20. So the LCD here is the LCM of 12 and 20. So 12 is going to be 4 times 3, so 2 times 2 times 3. And then 20 is 4 times 5, so 2 times 2 times 5. Okay, so what I'm going to do here is think about the fact that I have 2 that's common. So you want the largest number of repeats, and that's going to be 2 of them. So you want 2 times 2, which is 4. And then times, you're going to put in a 3, and then times 5. So 4 times 3 is 12. 12 times 5 is 60. So this would end up giving you 60. Okay, let me put equals here, and I'll just go down here. So 11 over 12. So what do I need to multiply the denominator by to get to 60? Well, notice that you have 4 times 3 there. That's 12. So you need another 5. So let's go ahead and put 5 here and then 5 up here. And then minus 3 over 20. Let me make this 3 a little bit better. I'm going to multiply this by, and that's not much better. So let me do that one more time. I'm going to multiply this by what? So 20 times 3 would be 60. So 3 over 3. So let's say this equals, and 11 times 5 is 55. Over 12 times 5 is 60. And then minus 3 times 3 is 9 over 20 times 3, that's 60. And now we can just subtract. So what is 55 minus 9? So maybe you want to do that as a vertical subtraction. Let's borrow here. This would be 4. This would be 15. 15 minus 9 is 6. Bring down the 4 there. So this would be 46. So you could say that this is going to be 46 over 60. Now, I know that 46 and 60 are even numbers. So at minimum, I can cancel a common factor of 2. So 46 would be 2 times 23, and 23 is a prime number. And then 60 is going to be 2 times 30. So I can cancel that common factor of 2 between numerator and denominator. And so this gives me 23 over 30 as my final answer. All right, what about 14 over 15 minus 17 over 25? So the LCD is the LCM of 15 and 25. So 15 is going to be 3 times 5, and 25 is a perfect square. It's 5 times 5. So this would be what? 3 goes in, and then for 5, you want the largest number of repeats because it's common. Here it's 1, here it's 2, so you're going to put in 2 of those guys. So 3 times 5 would be 3 times 25, so that's 75. So let me actually erase this and just put 75 like this. And let me get rid of this border, and I'll put equals here, and we'll just come down here. So 14 over 15. What do I need to multiply 15 by to get to 75? Well, 5. So I'm going to do times 5 over 5. And then minus 17 over 25. What do I need to multiply 25 by to get to 75? Well, 3. So times 3 over 3. All right, so 14 times 5. Let me do that off to the side. It's going to be 70, but let's do that off to the side. So 5 times 4 is 20. 0 down, carry the 2. 5 times 1 is 5, plus 2 is 7. So this is 70. So let's say this is 70 over. We know that, again, this is going to be 75. And then let's get rid of this. Now you have 17 times 3. Let's do that here real quick. So 3 times 7 is 21. 1 down, carry the 2. 3 times 1 is 3, plus 2 is 5. So that would be 51. So let's go minus 51. And again, we know this denominator is 75. So let's say this equals what? I think we could do 70 minus 51 in our head. That is going to end up giving me 19, which is a prime number, over 75. So this would be simplified. Again, 19 is a prime number. We know what 75 factors into. It's going to be 3 times 5 times 5. So nothing you can really do there other than to say that 19 over 75 is your simplified answer. All right, let's take a look at one final problem. So now we have more than two fractions involved. So you see we have 2/3 plus 1/4 minus 5/8. So again, let me just start by figuring out, well, what is the LCD? This is the LCM of the denominators. So 3, 4, and then 8. Okay, so 3 is a prime number, so don't worry about that. 4 is going to factor in a 2 times 2, and then 8 is going to be 2 times 2 times 2. Okay, so basically between 4 and 8, you see that you have 2 factors of 2 here, but 3 factors of 2 here. So you're going with the largest number of repeats. So I'm basically going with 8 here, and then I need the 3 there. So it's going to be 8 times 3, which is 24. So let me go ahead and just say that this is going to be equal to 24. Okay, let me write this down here because I'm going to need some room. So the LCD is equal to 24. Okay, let me get rid of this. And I'm just going to say that this is equal to 2/3 times, what do I need to multiply 3 by to get to 24? Well, 8. So I'll multiply this by 8 over 8. And then plus we have 1/4 times, what do I need to multiply 4 by to get to 24? Well, 6. So 6 over 6. This is probably not going to fit. So let me move this down here. Let me actually rearrange everything and move this over here. And I'll just drag this over here. Okay. Then minus, we have 5/8 times. What do I need to multiply 8 by to get to 24? Well, 3. So this is 3 over 3. All right, let me slide down here and just say equals. So first, let me just simplify everything. 2 times 8 would be 16 over, we know all the denominators would be 24. Then plus 1 times 6 is 6, again over 24. And then minus 5 times 3 is 15, and then over 24. So when you have all these different operations going on, again, if it's addition and subtraction, that's worked left to right. So I'm just going to think about it like I have this. 16 plus 6 minus 15 over the common denominator of 24. That's all I'm really doing. So I'm going to add first, and then I'm going to subtract last. So 16 plus 6, well, 16 plus 4 is 20, plus another 2 is 22. So this is 22 minus 15 over 24. And then 22 minus 15, well, that's going to be 7. So this ends up giving me 7 over 24. Now, 7 is a prime number, so you're not really going to be able to do anything. We know 24 is 3 times 8, right, or 2 cubed. So you really can't do anything to simplify there. It's just going to be 7 over 24 for the simplified answer. Hello and welcome to Pre-Algebra Lesson 34. In this video, we're going to learn about comparing fractions. So the lesson objective for today is just to learn how to compare the size of 2 or more fractions. All right, so in order to compare the size of 2 or more fractions, one thing we can do is we can convert all of the fractions into equivalent fractions with the same denominator. So with this first procedure I'm going to give you, you're basically going to figure out what is the LCD, or the least common denominator. You're going to transform each fraction into an equivalent fraction where the LCD is its denominator, and then you're going to compare the numerators. So given the fact that you have the same denominators, the largest numerator will belong to the largest fraction. This is one way to do it. It's the slower way, but we're going to use it to build up the concept. As we get further along in the lesson, I'll give you the shortcut, which basically involves just cross multiplying. All right, we want to replace the question mark with either the less than symbol or the greater than symbol. And we're going to start with something very easy just to get an understanding of the concept. We have 3/8 and then a question mark and then 5/8. So to think about this, I have a little pizza, and the pizza has been split up into 8 equal slices. So let's say that this is 1, 2, 3, 4, 5, 6, 7, 8. So let's say that we're at a party, and basically I say that I'm going to eat 3 slices of pizza. So let me mark these out. So I'm going to get this piece, I'm going to get this piece, and I'm going to get this piece. So I've taken 3/8 of the pizza, 3 slices out of a total of 8 available. And then you say, okay, I'm going to go ahead and take 5 out of the 8 slices and just finish the pizza off. So let's say you take this one, and then this one, and this one, and this one, and then this one. Well, who got more pizza? Well, of course you did. You got 5 slices out of 8, whereas I only got 3 slices out of 8. So when we have the same denominator, it's very easy to compare. We just think about what numerator is bigger. 5 is bigger than 3, so we can say that 5/8 is a bigger fraction. With this one, the 3/8 is on the left, so we would say 3/8 is less than 5/8. Of course, you could flip that around. Let me write that over here. You could say that 5/8 is greater than 3/8 if you were presented with the problem in a different way. Let's look at one that's a little bit more tedious. So now we have 2/5 question mark 3/7. So it's not as straightforward here because the denominators are not the same. So what we have to do is convert this over to where each fraction has the same denominator. Again, as we get further along the lesson, I'm going to give you a shortcut to do this very, very quickly. For right now, let's just build up the concept. So we have 2/5 and then we have 3/7. So when we think about the least common denominator, remember this is the least common multiple of the denominators. So of 5 and then 7. So this is equal to what? Well, 5 is a prime number and 7 is a prime number. So just multiply those two together. So this is 5 times 7, which is 35. So basically all I have to do is multiply this by 7/7 and multiply this by 5/5. And so that would give me 14/35. So 14/35. And then this would be 15. So 15/35. So let me actually move this over here like this and this like this so we know what we're talking about. And basically now that we have the same denominator, so this is 35 and this is 35, then I'm looking at which numerator is larger. In this case, 15 is bigger, so I'm going to put a less than here. So 14/35 is less than 15/35. In terms of the original problem, remember 2/5 is now 14/35, so I would say 2/5 is less than 3/7 is now 15/35, so we'll say 3/7. So to answer this, we'll say 2/5 is less than 3/7. All right, let's take a look at 7/20 and then a question mark 5/12. So let me actually write this. So 7/20. I'm going to leave some space and then I'm going to write this one 5/12. The first thing is with this method, we're going to find the LCD, which is the least common multiple of these denominators for 20 and then 12. Let's think about 20 for a second. I don't think we need a factor tree. 20 is 4 times 5, and 4 is 2 times 2. So this is 2 times 2 times 5. For 12, again, I don't think we need a factor tree. It's very simple. It's 4 times 3, and 4 is 2 times 2. So let's say 2 times 2 times 3. Now, when you look at these prime factorizations and you're trying to build your LCM, if there's something that's common, in this case, you have a 2 here and a 2 here, you want to go with the largest number of repeats between any of the factorizations. So here I have 2 factors of 2, and here I have 2 factors of 2, so the largest number of repeats would be 2. So I'm going to put in 2 times 2. The big mistake is everybody puts in 2 times 2 times 2 times 2, or they put in 16 there, right? You only need 4. Then here I want to put in the 5, and then I want to put in the 3. So everything goes in. So if something's common, put in the largest number of repeats between all of the prime factorizations. Okay, let me get rid of the scratch work. And you can just multiply now. So 2 times 2 is 4. 4 times 5 is 20. And 20 times 3 is going to be 60. So this would be 60. To figure out what I need to multiply by, all you do is take this LCD here, which is 60, divide by the denominator. So 60 divided by 20 is 3, so I need to multiply by 3/3. And then over here, I divide 60 by 12 and I get 5, so I need to multiply by 5/5. So this is going to end up becoming 7 times 3 is 21, so this would be 21/60. This, 5 times 5 is 25, so this would be 25/60. So now it's very easy, right? We have the same denominator, 60 and then 60, and I could just compare the numerators. So 21 is less than 25, so we would say 21/60 is less than 25/60. Again, to put this in terms of the original problem, that's how we want to answer. So 7/20 is going to be less than 5/12. All right, let's take a look at one that's pretty tedious, especially if you're doing it the slow way. In the future, we're just going to cross multiply, so it'll be a lot quicker. But let's start out by finding the LCD, which is the LCM of these denominators. So 14 and then 34. So I would factor 14, that's 2 times 7. And then I would factor 34, so that is 2 times 17. So to build up the LCM, you would basically put one factor of 2 in. Again, it's common to both of these factorizations, so you just put 1 in, the largest number of repeats, then times, you have 7, and then times 17. You can get rid of this if you want. And then basically, you can go through and crank this out. A lot of you are using calculators at this point. If you're not, just do 2 times 7, that's 14. 14 times 17 is going to be 238. You can always stop and do a quick vertical multiplication. So 14 times 17. 7 times 4 is going to be 28. 8 down, carry the 2. 7 times 1 is 7, plus 2 is 9, so this is 98. Let's erase this and shift down. Let me actually move this up here. And then 1 times 14 is 14, so 4 and then 1. Let's put some addition there. Bring down the 8. And then 9 plus 4 is 13. 3 down, carry the 1. 1 plus 1 is 2. So it's 238. Okay, let's get rid of this. Now, let me put this over here and say this is 5 over 14 times, I need to get to 238. Now notice that 14 is 2 times 7, so I would need to multiply by 17 to get to 238 in terms of the denominator. So I'm going to multiply the numerator and denominator by 17. Now you could have also said, what is 238 divided by 14? And you get 17. So that's another way to do it. And this guy over here, let's do 15 over 34. And we're going to multiply by, what do I need? Well, 34 times 7 would be 238. So 7 over 7. So now that we have that figured out, you can actually get rid of this if you want. You don't need it anymore. You would just do some multiplication. We know that the denominator is going to end up being 238 in each case. So let's put that up there. What is 5 times 17? Well, some of you might know that that's 85. Again, if you don't, you can always stop and do a little vertical multiplication. 5 times 7 is 35. 5 down, carry the 3. 5 times 1 is 5, plus 3 is 8. So that's 85. Okay, so the other one is going to be 15 times 7. So 15 times 7. 7 times 5 is 35. 5 down, carry the 3. 7 times 1 is 7, plus 3 is 10. So this would be 105. So if I think about the denominators, they're the same. So I just want to compare the numerators. So 105 is larger. So this guy right here, this 85 over 238 is smaller or less than 105 over 238. So I'll go ahead and translate that into the original problem. Let me get rid of this so I have some room. And I will just say that 5 over 14 is less than 15 over 34. All right, let's take a look at an example where we have the same numerators but different denominators. So we have 2/3 question mark 2/5. So let me write this out. So 2/3 and then 2/5. Let's start with the LCD method, and then we'll show you a little shortcut for this one. So we have the LCD is going to be the LCM of the denominators, so 3 and then 5. So because 3 and 5 are both prime numbers, we can just multiply them together. 3 times 5 would be 15. So I'd multiply this by 5 over 5, and I'd multiply this by 3 over 3. Let me get rid of the scratch work here. And so this 2 times 5 would be 10 over, we know the denominator is 15. Here, 2 times 3 is 6. We know the denominator is 15. Let me get rid of this and get rid of this. So given the fact that we have the same denominators now, we can just compare the numerators. So the larger numerator will belong to the larger fraction. So 10 is larger than 6, so we can say that 10/15 is greater than 6/15, which is going to translate into 2/3 being greater than 2/5. Now, we could have found that in a much quicker way. In fact, if we have the same numerators, all we have to do is look at the denominators and see which one is smaller. So whichever one is smaller belongs to the larger fraction. So I know that's a little bit tricky the first time you hear it. When you have the same numerators, you want to look at the denominators and see which one is smaller. So the smaller denominator will belong to the larger fraction. So here, 3 is smaller than 5, so 2/3 is greater than 2/5. Let me make this simple and give you a visual example with some pizzas. So let's say that you go to the pizza shop and you buy 2 identical pizzas. You get back to the house and you split them up in different ways. With the first pizza, or the one on the left, you're going to split it up into 3 equal pieces. So 1, 2, and then 3. With the one on the right, you're going to split it up into 5 equal pieces. So 1, 2, 3, 4, 5. So let's say this one's for you and this one's for a friend. So let's say you decide that you want to eat 2 pieces of pizza. So maybe you eat this piece right here and then this piece right here. So you've eaten 2/3 of the pizza. Now, when you think about your friend, he also wants to have 2 pieces of pizza. So let's say he eats this piece of pizza and then this piece of pizza. Okay, so I'm going to represent that with 2/5. So who ate more pizza, given the fact that they were identical pizzas before you sliced them up? Well, you did, right? You had 2/3 of the pizza and he had 2/5. In other words, your 2 is going to be a larger amount than his 2 because we're talking about the slices themselves being different, right? So your slices are larger. So when you eat 2 larger slices, that's going to be more than your friend who's eating 2 smaller slices. Okay, so you're thinking about how the pizzas are split up. So that tells me that 2/3 is going to be greater than 2/5. All right, let's take a look at 2 problems where we're asked to arrange from least to greatest. Once we're done with that, I'll show you the shortcut and we'll be able to move through these problems more quickly. All right, so we have 5/6, 11/12, and then 3/20. So we are asked to arrange these from least to greatest. Sometimes they want you to put in commas like you see here. So put the smallest, then comma, the next smallest, then comma, you would have the largest because here we have 3. And then sometimes they want you to use inequality symbols. So I'll just give you both ways in case you are asked for one of those on your test. So first and foremost, I would get the LCD, which is the LCM of the denominators. So 6, 12, and then 20. Okay, so this equals what? For 6, this factors in a 2 times 3. For 12, this factors into 4 times 3, so 4 is 2 times 2. And then 20 is going to be 4, which is 2 times 2, and then times 5. So when I build my LCM, again, if something is common, you want to think about the largest number of repeats. So here for 2, it occurs once here, and twice here. So the largest number of repeats is 2. So I'm putting 2 factors of 2 in when I build my LCM. Then I'm looking at 3. So it occurs once here and once here. So I'm putting in 1. And then I'm looking at 5. It only occurs once here. So I'm going to throw that in. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. So this would be 60. So I'm going to say 5/6 times, in order to get a denominator of 60, I need to multiply by 10. So I want times 10/10. And then 11/12. If I want a denominator of 60, I need to multiply by 5/5. And then 3/20. If I want a denominator of 60, I'm going to multiply by 3/3. Okay, let me get rid of this. We know that in each case, the denominator would be 60. So let me just write that in real quick. And then we'll do our multiplication. So 5 times 10 is 50. Then 11 times 5 is 55. And then 3 times 3 is 9. Okay, let me get rid of this. So thinking about how we would order this, the denominators are the same. So you have 60, you have 60, and you have 60. So I'm just thinking about, in terms of the smallest fraction, I would have the smallest numerator. So that would be 9. So that belongs to 9/60. So let's say that this is 9/60, and then comma. The next smallest, I'm looking for 50 here, because 50 is smaller than 55. So I would go 50/60. And then the largest is going to be the 55/60. So if I want to write this in terms of what we had originally, which is always what you want to do, well, if you think about 9/60, again, that's going to be 3/20. So let's list that first. So this is 3/20. I'm going to put a comma. 50/60 is going to be 5/6. So this is 5/6. Put a comma. And then 55/60 is 11/12. So 11/12. So if you're asked to do this with commas and arrange from least to greatest, this is how you would do it. So 3/20, comma, 5/6, comma, 11/12. They may ask you to arrange them from greatest to least. Sometimes they do that. So then you would put 11/12, comma, 5/6, comma, 3/20. A lot of times they'll also ask you to do this with inequality symbols. So generally speaking, you'll do this from least to greatest, but you can also see it from greatest to least. So I would say that this is 3/20 is less than 5/6, which is less than 11/12. All right, let's look at one more of these. So this one's pretty simple. We have 2/5, 2/3, 2/7, and then 1/6. With this one, I would not find the LCD. It's going to be a little bit faster since we have the numerators 2, 2, 2, and then a 1. I can just say this is times 2/2, which is going to give me 2/12. So let me go ahead and say, I'm just going to temporarily line this out. I'll bring it back in a moment, that this is 2/12. Okay, so given the fact that we have the same numerators now, the smallest fraction is going to have the largest denominator. Remember, if you have the same numerators, then the largest fraction is going to have the smallest denominator. So that means the smallest fraction is going to have the largest denominator. So if I think about this, the largest denominator is 12. So that means 2 over 12 or 1 over 6. Let me just bring it back. That's going to be the smallest. So let me say that this would be 1 over 6 and then comma. The next largest would be 7. So I'm going to put 2 over 7 and then comma. The next largest would be 5. So I'm going to put 2 over 5 and then comma. Lastly, the smallest denominator here is 3. So I'm going to use 2/3 as the largest. So again, when I think about these, I've already transformed this over. Let me temporarily put this back so we can think about it. So this is 2 over 12. Going back to my pizza example, if I think about having 2/3 of a pizza, I'm going to eat more of that pizza than if I had 2/5 of it. Here I'm eating 2 slices and here I'm eating 2 slices. But again, with the 2/3 example, the slices are bigger. With the 2/5 example, the slices are smaller. So that's why we would say that this 1/6 here, which is 2 over 12, is going to be smaller than 2 over 7, which is smaller than 2 over 5, which is smaller than 2/3. So if you want to use inequalities, we'll say 1/6 is less than 2/7, which is less than 2/5, which is less than 2/3. All right, so now let's get into the shortcut. So we can determine which fraction is larger by cross-multiplying and comparing the results. So now we're back to replace the question mark with the less than symbol or the greater than symbol. All right, so let's start off with this example here. So we have 4/9 question mark 5/12. So I'm going to build you up to the shortcut. We're going to start with what we know. So we have that the LCD is going to be the LCM of these denominators. So 9 and then 12. What is 9? It's 3 times 3. What is 12? It's 3 times 4, and 4 is 2 times 2. So 2 times 2 times 3. So when you build this, again, you look at this and you say, okay, well, there's going to be 2 factors of 2. So 2 factors of 2. But then I only need 2 factors of 3, right? Because there's 2 factors of 3 here and 1 here. Go with the largest number of repeats between any of those prime factorizations. So I'm going to put in 2 factors of 3. Get rid of this. We know that that's basically 4 times 9, which is 36. So let's put this as 36. So at this point, we know using our slower procedure, we would say 4 over 9 and then times, what do I need to multiply 9 by to get to 36? Well, 4. So I would do times 4 over 4. And then over here, I have 5 over 12. What do I need to multiply 12 by to get to 36? Well, 3. So times 3 over 3. And so this becomes 16 over 36. And then this becomes 15 over 36. And now that we have a common denominator, we can just compare the numerators. So 16 is greater than 15. So you'd say 16 over 36 is greater than 15 over 36, which gives me 4/9 is greater than 5/12. Okay, so we've been doing it that way, and it's a little bit slower than what I'm going to show you now. So let me erase this, and let's talk about the shortcut. In every case, you can just multiply the 2 denominators together to get a common denominator. It's not always going to be the least common denominator. Sometimes it will be, it just depends. But you can always just get a common denominator by doing that. So let's say I erase this, and I erase this. And I just say, okay, I'm not going to find the LCD here. I'm just going to get a common denominator. So I would multiply this by 12 over 12, and I would multiply this by 9 over 9. Okay, well, 4 times 12 is 48, and then 5 times 9 is 45. It actually does not matter what the denominator is because I know it's going to be the same, right? Because I'm multiplying the 2 denominators together. It's just in a different order. Here it's 9 times 12, and here it's 12 times 9. Now, 9 times 12 or 12 times 9, we know that's 108, so let's just go ahead and write that for completeness. At this point, I can just compare the numerators. So 48 is larger than 45, so you would say 48 over 108 is greater than 45 over 108. Okay, so what can we learn from this process? What I could have done, let me get rid of this for a moment. I could have just said, well, if I multiply those 2 denominators together, they're going to be the same. So I don't really care what they are. I just need to figure out what is this numerator times the other denominator, and what is this numerator times the other denominator, and just compare those numbers to figure out which fraction is bigger. So in other words, I can say 4/9 and then 5/12, and I can do something called cross-multiplying. So take this denominator and multiply it by this numerator. 9 times 5 is 45, and that's the exact same thing we got here. 5 times 9 is going to be 45. And then you're going to take this denominator, which is 12, and multiply it by this numerator, which is 4, and that's going to give you 48. So 4 times 12 is 48, done this way. So it's just a much quicker way to obtain which fraction is bigger. I only need to think about the 48 and the 45. 48 is bigger, so I'm going to go with 4/9, the fraction that is next to, as the bigger fraction. So I can say that 4/9 is greater than 5/12 using this cross-multiplying method. Okay, let's blow through a few examples. So we have 2/3, and then you have a question mark, and 4/5. So again, you're just going to cross-multiply. So 3 times 4 is 12, and then 5 times 2 is 10. So 12 is greater than 10, so you can say that 2/3 is smaller, right? So 2/3 is less than 4/5. What about 4/3 question mark 6/5? So don't worry about the fact that you have improper fractions here. It's not going to matter. You can use the same strategy. So let me write 4/3 and then 6/5. And again, we're just going to cross multiply. 3 times 6 is 18. Then 5 times 4 is 20. So 20 is bigger. So you would say 4/3 is greater than 6/5. Let me give you one example with some negatives. So these are a bit tricky because everything I said is going to now be reversed when you're thinking about a negative. So when I think about -3/4 and 2/-7, the first thing you want to do if you have negatives involved, bring your negative here into the numerator. And that's legal because a negative divided by a positive or a positive divided by a negative is a negative. I could just as well put the negative out in front, or I could put the negative in the numerator or the denominator. It's all legal. So let me put them both in the numerator, and then I would cross multiply. So 4 times -2 is -8, and 7 times -3 is -21. Okay, so here's where we got to be really, really careful. When we think about a bigger negative, it is further to the left, and it is therefore a smaller number. So -21 is a bigger negative, and therefore a smaller number than -8. So -21 would be next to the smaller fraction. So you would say that -3/4 is less than -2/7. If you had gotten the problem 3/4 and then 2/7, notice that the answer would be flipped. So you cross multiply here, you have 8, and then you have 21. Right? So 21 is greater than 8. So here you would say that 3/4 is greater than 2/7. But because these guys are negative, it's going to get reversed, right? Because now 3/4 becomes -3/4, and that's going to be a bigger negative and therefore a smaller number than this -2/7. All right, let's look at one more example where we arrange from least to greatest. So we have 2/15, 3/7, and 4/13. So what I do is just start with any two that you want. It doesn't really matter. So let's start with 2/15 and then 3/7 and just figure out the relationship. So 15 times 3 is 45, and then 7 times 2 is going to be 14. So this one is obviously smaller. So we'll say 2/15 is less than 3/7. Okay, so erase this. And now you can take this one right here, this 3/7, and compare it to 4/13. So I'm going to say 3/7 and then 4/13. You'll cross multiply. So 7 times 4 is 28. And then 13 times 3 is 39. So 3/7 is bigger. So I'm going to say that 3/7 is greater than 4/13. So we know that 2/15 is less than 3/7. We could also turn that around and say 3/7 is greater than 2/15. Here we see that 3/7 is also greater than 4/13. So I know that 3/7 is actually the biggest number. I only now need to compare these two numbers and see which one is larger. So let's slide this down a little bit and cross multiply. So 15 times 4 is 60, and then 13 times 2 is 26. You can say that 2/15 is going to be less than 4/13. So this would be the smallest number. So let me change my color here. So this is 2/15. I'll put a comma. This one would be in the middle. So it would be 4/13. And then the largest would be this 3/7. If you want to write this using inequality symbols, you would typically go from least to greatest in the order of the number line, but you could reverse that if you want. It's pretty much up to you. In most cases, you're going to see 2/15 is less than 4/13, which is less than 3/7.
Hello and welcome to Pre-Algebra Lesson 35. In this video, we're going to learn about ratios and rates. Okay, so for the lesson objectives for today, we want to learn how to write a ratio that describes a given situation, and we also want to learn how to write a unit rate that describes a given situation. So we're going to kind of just start out with a basic definition here. We're going to say that a ratio is a comparison of two quantities with the same units. And later on, we're going to talk about rates. And a rate is basically a special ratio where the units are going to be different. To kind of start off here, we're going to use ratios a lot moving forward. And they're actually something that will help you in your everyday life. As an example, let's say that you're at a school dance. And at the school dance, you talk to the chaperone and they tell you that there are 4 boys for every 2 girls at this dance. So 4 boys for every 2 girls at the dance. Well, we can describe this relationship by writing a nice little ratio. And there's 3 main ways we do this. So if we want the relationship between boys and girls, we can write boys to girls like this as a fraction. And so boys is in the numerator. So I'd put the number of boys in my numerator when I write the ratio. Girls is in the denominator, so I'd write the number of girls in the denominator when I write the ratio. And we'd say it differently, right? Instead of saying 4 over 2, we would say 4 to 2. Now, if we flip this and said girls to boys, this would be 2 to 4, right? It's relative, right? The number of girls I have is 2 to the number of boys that I'm told that I have is 4. Now, there's more ways to write it, but I want to show you something before I get into that. When you have a ratio, you always want to simplify it, just like we did when we work with fractions. So we know that 4 over 2, or 4 to 2, as a ratio, is the same as 2 to 1. If I divide 4 by 2, I get 2. If I divide 2 by 2, I get 1. Now, one main difference is, if I'm working with fractions and I have 2 over 1, I just write that as 2. When I'm working with a ratio, I have this relationship between boys and girls, so I leave the 1 there because I'm saying I have 2 boys for every 1 girl. 1 girl. And then over here, I could just rewrite this as 1 to 2. Some other ways that we could write this ratio. I could write boys to girls like this using a colon. Okay, so this would be 2 to 1, right? Because I have 2 boys for every 1 girl. And then I could also write it using the word 2. I could say boys to girls like this. And I could say 2 to the word 2, not the number 2, 1 like that. So all of these are ways that we can write a ratio. Most commonly, I would say you're going to see it this way or this way, right? As a fraction or with a colon. This is sort of uncommon, right? Sort of uncommon, but still you may see it from time to time, so you need to know that we're talking about a ratio when we see something like this. So let's kind of continue with this example, and I'll show you a common test question for ratios. So remember, we had 4 boys for every 2 girls. And we said that this simplified to a ratio where it's boys to girls of 2 to 1. Now, your typical question would say something like, if there were 42 kids at the dance, how many were boys, how many were girls? So let's think about that. So out of 42 kids, we're going to put boys, question mark, and then girls, question mark. How would we figure something like this out? Well, the first thing I would do is I would take my 2 numbers in my simplified ratio and I would add them together. So I have 2 boys to 1 girl. So 2 plus 1 is 3. So that tells me in one group, I will have 3 kids, and I will basically have 2 boys, and I'll have 1 girl. If I have 42 total kids, essentially I'm saying, how many equal groups of 3 can I make out of 42? Well, 42 divided by 3 is 14. So I'm essentially saying I have 14 of these groups, so I would multiply the numbers here by 14. So 2 times 14 would give me 28. So this tells me that for 42 kids, I would have 28 boys, and I would multiply 1 times 14 and get 14, so I'd have 14 girls. And if this isn't clear for you, let me just kind of make a little chart. So we would have kids, and then we would have boys, and then we would have girls. So if 3 kids attend, we know that 2 are boys, 1's a girl. And we're going to increase in increments of 3 here. So if we go from 3 to 6, then we're going to have what? We've doubled here, so we have to double everything here. Now we're going to have 4 boys and 2 girls. Right? All I did was multiply everything here by 2. 2 times 2 is 4, 1 times 2 is 2, 3 times 2 is 6. Right? Everything has just been doubled. Well, if I now go to 12 kids, essentially I'm taking the original amount and just multiplying it by 4. Right? So I have 4 times the amount of kids there. So instead of 2 boys, multiply by 4, I'd have 8. Instead of 1 girl, multiply by 4, I'd have 4. So we can take this all the way up to, let's say, 42. And basically it's 14 times the original amount. So I just multiply everything here by 14. 2 times 14 would be 28. So I'd have 28 boys. 1 times 14 would be 14. So I'd have 14 girls. All right, so let's take a look at a different problem. So we have a mixture that contains 24 milliliters of alcohol for every 8 milliliters of water. And we want to state the ratio of alcohol to water. So I'm just going to do this using a fraction, but again, if you want to use a colon, you can do that as well. So again, the ratio of alcohol to water, so alcohol to water. Notice that alcohol, the first word or the word that occurs before the word to, is in the numerator. Water, the second word, occurs in the denominator. So I have 24 milliliters to 8 milliliters. And again, with a ratio, you're going to have the same units, so you don't really have to write them because you can kind of think of them as just canceling each other out. So we could just write 24 over 8. And if we simplify this, we know that 24 divided by 8 is 3. So really I'd write it as 3 to 1. And again, very important, leave the 1 there. I know generally when we work with fractions, we just write that as 3. But with a ratio, we're talking about the relationship where we're saying we have 3 milliliters of alcohol to every 1 milliliter of water in this mixture. Now it says to state the ratio of water to alcohol. So again, if your words are flipped, you just flip your ratio. So water to alcohol. Remember when we looked at alcohol to water, the simplified version was 3 to 1. So when we look at water to alcohol, it's going to be 1 to 3, meaning I have 1 milliliter of water for every 3 milliliters of alcohol in this mixture. Let's take a look at some follow-up questions. So let's suppose that we have a 120 milliliter mixture. So I'm going to write here that we have a 120 milliliter mixture. We want to know how many milliliters of alcohol are in the mixture and how many milliliters of water are in the mixture. Let me kind of scroll down to the next page and get a little room going. Again, I'm going to write that it's a 120 milliliter mixture. And let's just write the ratio of alcohol to water. Alcohol to water. And remember, that's 3 to 1. 3 milliliters to 1 milliliter. And again, I left off the milliliter because, we could write that in there if you want. But again, these would basically cancel out. And you just write it as 3 to 1. That's just very common. That's what we do. All right, so if we want to find out how much alcohol is in this mixture and how much water is in this mixture, we have to think about what would be in one group. So one group would be 3 plus 1 or 4. 4 milliliters. That's one group. And you basically have 3 milliliters of alcohol. And you're going to have 1 milliliter of water. So how many of these groups can I make out of 120 milliliters? Well, you take 120 and you divide it by 4 and you would get 30. So I can make 30 of these groups. So I would just multiply 30 by 3 to get the amount of alcohol I'm going to have. 30 times 3 is 90. So I'm going to have 90 milliliters of alcohol. And I would multiply 1 times 30 to find out how many milliliters of water I'd have. 1 times 30 is 30. So I would have 30 milliliters of water. In a mixture with 120 milliliters, with an alcohol to water ratio of 3 to 1, you're going to have 90 milliliters of alcohol and 30 milliliters of water. So similar to ratios, a rate is a special type of ratio that compares two quantities with different units. So when we start talking about rates, we're generally going to be talking about something known as the unit rate. And that's going to be the amount of something per 1 unit. So generally speaking, we just divide the numerator by the denominator to get a unit rate, or the rate per single unit. So as an example, we have Jeff earned $63 in 9 hours. What is the unit rate in dollars per hour? So you just kind of set this up just like you would with a ratio. So we're going to put $63 in the numerator, and we're going to put 9 hours in the denominator. And essentially, to find the unit rate, or the amount of dollars that he earns per 1 hour, you're going to take the number in the numerator, which is 63, and divide it by the number in the denominator, which is 9. We know that 63 divided by 9 is 7. So when we basically just simplify this, we end up with $7 per 1 hour. Or he earns $7 per hour. We have that Jennifer drove 125 miles in 5 hours. What is the unit rate in miles per hour? So this is a common one you might use on a trip somewhere. So we have 125 miles. We'll put that in the numerator. And we'll have 5 hours. We're going to put that in the denominator. We're trying to find out how many miles per 1 hour. So again, we take the number in the numerator. We divide that by the number in the denominator. So 125 divided by 5 is 25. So this numerator is going to be 25 and then miles. And in the denominator, this is going to be a 1, and then it's going to be hour. So she was going 25 miles per 1 hour. So one common thing we use unit rates for is to compare prices. And a lot of times when you go to the grocery store, you'll see next to the price, it's this much per unit. Maybe this much per ounce or this much per gallon, so on and so forth. So in our example here, we have that 5 gallons of milk sells for $15, while 10 gallons of milk sells for $20. Which option has a lower cost per gallon? So what we would do is take the dollar amount in each case and divide it by the number of gallons of milk we're getting in each case. That'll give us the unit rate, or the price per gallon of milk. So the first scenario is $15 for 5 gallons of milk. So if I take 15 and divide by 5, I get 3. So this is essentially $3 per 1 gallon, right? And I could put gallon of milk, but just going to kind of shorten that a little bit. The next scenario is 10 gallons for $20. So I'm going to set this up as $20, and then in the denominator, I'll put 10 gallons of milk. And again, I'm going to do 20 divided by 10. That's going to give me 2. So my new numerator will say $2, and then per, again, 1 gallon. 1 gallon. So obviously this is cheaper. So between these two scenarios, this one is going to be cheaper, right? Spending $20 on 10 gallons of milk gets you a price of $2 per gallon. And again, if you were to spend $15 on 5 gallons of milk, you'd be paying more per gallon, or a price of $3 per gallon. Hello and welcome to Pre-Algebra Lesson 36. In this video, we're going to learn about proportions. So our lesson objective for today is just to learn how to determine if two ratios represent a proportion. So in the last lesson, we learned all about ratios, and we didn't go too much into depth, but we learned enough for pre-algebra. Now we're going to start talking about proportions, and this is another topic where we're going to go way deeper once we get into Algebra 1. But before we can start talking about proportions, we have to be able to answer a simple question. And that question is, how do we determine if two fractions are equal? Well, we're going to use something called the equality test for fractions. And basically what this tells us is that two fractions are going to be equal if their cross products are equal. So for example, let's say we take something like 1/2 and, I don't know, let's say 6/12. We can eyeball this and see that these two fractions are equal. I know that if I divide 6 by 6, I get 1. If I divide 12 by 6, I get 2. 1/2 and 6/12, they're equivalent fractions. So the equality test for fractions tells me that I can multiply this denominator by this numerator, and this denominator by this numerator, right? The cross products, we're multiplying across, and I should get the same answer. 2 times 6 would give me 12, and 12 times 1 gives me 12 as well. So we have the same value, and so we know those two fractions are equal. Let's try another one. Let's say we have something like 1/4 and, I don't know, let's say 3/7. We know these two fractions are not equal. One of the ways we can tell is that these two fractions are reduced to their lowest terms or simplified, and so I know that they're not going to be the same value. So I can multiply 4 times 3, that would give me 12, and 7 times 1, that would give me 7. 7 and 12 are not equal, so these two fractions are not equal. Now you might be asking, how does this little test work? How come when we have the same value here, we know that we have equal fractions or equivalent fractions? Well, you remember when we were talking about comparing fractions, we found that when we cross multiplied, if 12 was greater than 7, that tells us that 3/7 is the greater fraction. So that stems from the fact that we're comparing the numerators here if we had multiplied each fraction, top and bottom, by the other fraction's denominator. So, for example, if I have 1/4 and 3/7, what I can do is I can form a common denominator of this fraction's denominator times this fraction's denominator. 4 times 7 would be 28. Now, you can always do this. It's not always going to give you the least common denominator, but it will give you a common denominator. So if I multiply this fraction, top and bottom, by the denominator of this fraction, well, what I get? 1 times 7 is 7. That's what we had here. And then 4 times 7 is 28. So you get 7 over 28. Now, if I do the same thing over here, so I have 3 over 7, I'm going to multiply this top and bottom by the denominator of the other fraction, so times 4 over 4. 3 times 4 is 12. Notice that's what we got here. And then 7 times 4 is 28. So now it's easy to compare these two fractions. They have the same denominator. I just look at the numerator. And I know that 12 is bigger than 7, so this is the greater fraction. So 7/28 is less than 12/28. When we cross multiply, we are shortcutting this process. I am just saying, hey, all I need to know is what's the numerator going to be, right? In this case, I know the numerator is going to be a 7, and I know the numerator is going to be a 12 over here. 7 is less than 12, so I know this fraction is going to be smaller. I don't care what the denominator is going to be because the denominator is going to be the same, and again, that allows me to compare the numerators only. So again, when two fractions are equal, their cross products are equal. So if we have a problem like this, 1/4 is equal to 7/28, and I have a big question mark here. So we kind of have to prove it and say, okay, is this true or is this not? So I would just find the cross products. So I'd multiply 4 times 7, that gives me 28. I'd multiply 28 times 1, that gives me 28. So yes, these are equal. Yes. And one of the things you can do, if you have both fractions in their simplest form, you can easily tell if they're equal, right? Because if I can't reduce this any further, I can't reduce 1/4 any further. But if I look at 7 over 28, I can reduce that. 28 is divisible by 7. So if I divide 28 by 7, I'd have 4. If I divide 7 by 7, I'd have 1. So I'd end up with 1/4. What about 2/5 is equal to 6 over 20? Again, we can just form the cross product. So 5 times 6 is 30. And 20 times 2 is 40. So 40 is not equal to 30. So these two fractions are not equal. So no. What about 3/4 is equal to 9/12? Again, form the cross products. So 4 times 9 is 36. And 12 times 3 is also 36. So this would be a yes. These two fractions are equal. What about 17 over 12 is equal to 34 over 24? So we'd multiply 12 times 34. 2 times 4 is 8. 2 times 3 is 6. 1 times 34 is 34. Bring down the 8. 6 plus 4 is 10. 1 plus 3 is 4. So this is going to be 408. Then we're going to do 24 times 17. So 24 times 17. 7 times 4 is 28. 7 times 2 is 14 plus 2 is 16. And then 1 times 24 is 24. So bring down the 8. 6 plus 4 is 10. 1 plus 1 is 2. 2 plus 2 is 4. So this is going to be 408 also. So these two fractions are equal because their cross products are equal. So yes. All right, let's take a look at one final problem. We've got 12 over 13 is equal to 48 over 65. So multiply 13 times 48. So 48 times 13, 3 times 8 is 24, 3 times 4 is 12, plus 2 is 14, and then 1 times 48 is 48. Bring down the 4, 4 plus 8 is 12, 1 plus 1 is 2, plus 4 is 6, so that's 624. And then 65 times 12 is what we're going to do next. So 65 times 12, 2 times 5 is 10, 2 times 6 is 12, plus 1 is 13, and then 1 times 65 is 65. 3 plus 5 is 8, 1 plus 6 is 7, so that's 780. So 780 is not equal to 624, so no, these are not equal fractions. All right, so let's talk about what a proportion is now. So when two ratios are equal, or you could say when two rates are equal as well, they are called a proportion. And really you could extend that and say when two fractions are equal, they represent a proportion. So those examples that we looked at earlier, where we said yes, those were proportions. We start out with this example, 3 shrubs to 12 feet. And then we have 6 shrubs to 24 feet, and we're saying they're equal. So if this is true, then we'd have a proportion. Now the way you check this, if I have shrubs in the numerator here, I've got to have shrubs over here. I can't have shrubs here and then trees over here. That doesn't make any sense. And then whatever's in the denominator has to be the same. So feet here and feet here. So once you've checked that, all you need to do is cross multiply with the numbers. If the result of the cross products there are the same, you have a proportion. So in other words, here I would take 12 and multiply it by 6. 12 times 6 is 72. Then I would take 24 and multiply it by 3. 24 times 3 is also 72. So yes, here we have a proportion. Let's take a look at another one. Here we have 600 miles to 10 hours, and we're saying that's equal to 300 miles to 5 hours. Now, again, you're looking at what's in the numerator. We have miles here, miles here. What's in the denominator? We have hours and then hours. So that part checks out. Then you just work with the number parts. So I'm going to cross multiply. I'd have 10 times 300. So basically we just put another 0 at the end of 300. That's 3,000. Then I'm going to multiply 5 times 600. So 5 times 6 is 30. And then we have 2 trailing zeros, so we put 1, 2 zeros at the end. And in each case we get 3,000. So yeah, this is a proportion. So yes, this is a proportion. Here we have 12 points to 48 games. We're saying this is equal to 36 points to 96 games. So again, we check everything out in the numerator, points and points. In the denominator, we have games and then games. So that's all okay. Then we're just going to cross multiply with the numbers. So 48 times 36. And just in the interest of time, we'll do that with a calculator. It's 1,728. And then we do 96 times 12, and that's 1,152. So these two numbers are not the same, so this is not a proportion. So not a proportion. All right, for the next one, we have $2 to 7 euros. We're saying this is equal to $5 to 18 euros. So again, we have dollars and dollars, euros and euros. So that's okay. Now we would cross multiply. 7 times 5 is 35. 18 times 2 is 36. 36 and 35 are not equal, so we don't have a proportion. So just not a proportion. Okay, let's take a look at one more problem. Again, this is really, really simple. So we have 13 gallons to 4 acres, and we're saying this is equal to 39 gallons to 12 acres. So again, we have gallons and gallons, and acres and acres. So that checks out. So then we just want to cross multiply the number parts. So 4 times 39 is 156. And then 12 times 13 is also 156. So those two numbers are the same, so we do have a proportion. So yes, this is a proportion. Hello and welcome to Pre-Algebra Lesson 37. In this video, we're going to learn about operations with mixed numbers. So the lesson objective for today is to learn how to add, subtract, multiply, and divide mixed numbers. So when we add or subtract mixed numbers, we're going to add or subtract the fractions first, followed by the whole numbers. So let's just start out with an example. We have 3 1/2 plus 6 1/4. So I want you to remember that if we see something like 3 1/2, this is really 3 plus 1/2, right? It's just written this way for convenience, right? We don't want to take up all the space with a plus sign each time. So 6 1/4 is really 6 plus 1/4. So to add these two mixed numbers, all we're going to do is just kind of rewrite them as 3 plus 1/2 and then plus 6 plus 1/4. And then I'm going to do some reordering. Remember, I can do that with addition because it's commutative. So I'm going to put my fractions next to each other. I'm going to put 1/2 plus 1/4. And then I'm going to put my whole numbers next to each other. So I'm going to put plus 3 plus 6. So now what I'm going to do, again, as I said, I'm going to add the fractions first, and then I'll add the whole numbers last. So what if I had 1/2 plus 1/4? What would I do? Well, I'd find my LCD, and between 2 and 4, I know the LCD would be 4, right? 4 is 2 factors of 2. 2 does not factor. So if I have 1/2, again, plus 1/4, I'd multiply 1/2 by 2 over 2 so that I could get the denominator of 4. So 1 times 2 is 2, over 2 times 2, that's 4. And then we're adding to that 1/4. So we'd add these numerators. 2 plus 1 is 3. And we place that over the common denominator of 4. All right, so let me erase all this and just kind of go back up to the top now. So we know at this point that adding the fractions here gives us the result of 3/4. So I'm going to put 3/4 plus, and then again, you have 3 plus 6 there. Now, adding the whole numbers are easy, right? 3 plus 6 is 9. You can do that in your head. So now when I look at it, I have 3/4 plus 9. If I just reorder this one more time to 9 plus 3/4, I can then use my convenient notation that I have up here, the way that we just write a mixed number, right? So this is going to be equal to 9 and 3/4. All right, let's take a look at another one. We have 6 3/8 plus 2 1/12. So again, what I'm going to do is I'm going to rewrite this. I'm going to put 6 plus 3/8 and then plus 2 plus 1/12. So I'm going to reorder this addition to where the fractions are next to each other and the whole numbers are next to each other. So I'm going to put 3/8 plus 1/12 and then plus 6 and then plus 2. And again, you don't have to do that. You can just kind of add these together and add these together, and you'd end up with the same result. I just do this so that it's convenient to see what we're doing. All right, so moving on now. We're going to add our fractions first. And let's just do this down here to make it convenient. So if I have 3/8 and I have 1/12, what's going to be my LCD? Well, it's going to be the LCM, the least common multiple, of 8 and 12. So again, how do we figure something like that out? Well, we've been working with fractions for a long time now. We know that 8 factors into 3 factors of 2. So 2 times 2 times 2. We know that 12 is 2 factors of 2, and I've already accounted for that, and then 1 factor of 3, so that's got to go in. So basically my LCD is going to be 2 times 2 times 2, or 8, times 3, which is 24. So when I'm adding these fractions, what I'm going to do is I'm going to first transform the fractions into equivalent fractions where they have a denominator of 24. So I'm going to multiply this by 3 over 3, and I'm going to multiply this by 2 over 2. So what we're going to get is 3 times 3, that's 9, over 24, plus 1 times 2 is 2, again, over 12 times 2, which is 24. So now we have our common denominator. We can just add the numerators. 9 plus 2 is 11, and that's going to be over the common denominator of 24. So let's erase all this and go back up. We know what the fraction part's going to be. It's going to be 11 over 24. So I'm going to put equals 11 over 24, and then plus. Now the whole number parts, 6 and then 2, if we add those together, that's going to give us 8. And again, I can just reorder this one more time. 8 plus 11 over 24. And again, to write this as a mixed number, we just simply drop out that addition sign, right? Just for convenience. So this is really going to be 8 and 11/24. All right, let's take a look at one final addition problem, and then we'll move on to subtraction, multiplication, and division. So we're adding 9 1/5 plus 13 and 1/4 plus 2 and 7/8. Again, I'm going to just write this out as 9 plus 1/5 plus 13 plus 1/4 plus 2 plus 7/8. And I'm going to reorder it again to where my whole numbers are next to each other and my fractions are next to each other. Let me just put my whole numbers first. So let's do 9 plus 13 plus 2. And then plus, down here I'm going to put my fractions of 1/5 plus 1/4 plus 7/8. So let's take care of the fraction parts first. And we're going to scroll down and do that. So if I have 1/5 plus 1/4 plus 7/8, again, I need to find the LCD to start. So what's my LCD going to be? Again, it's going to be the least common multiple for these denominators. So of 5, 4, and 8. So 5 doesn't factor, so that goes in. 4 is 2 times 2. And 8 is 3 factors of 2. So because I already have 2 factors of 2 in here, I just need to add one more in. So the LCD is going to be 5 times 2, which is 10, times 2 again, which is 20, times 2 one more time, which is 40. So I need to rewrite each fraction as an equivalent fraction with 40 as its denominator. So for 1/5, I'm going to multiply by 8 over 8. For 1/4, I'm going to multiply by 10 over 10. And for 7/8, I'm going to multiply by 5 over 5. Okay, so 1 times 8 is 8. Over 5 times 8, that's 40. Then plus 1 times 10 is 10. Over 4 times 10, that's 40. Then plus 7 times 5 is 35. Over 8 times 5, that's 40. So we have 8 plus 10, that's 18, plus 35, which is going to give us 53. So we'd have 53 over the common denominator of 40. Now, when you get a result that is greater than 1, remember, you're working with mixed numbers here. So your fraction part has to be a proper fraction. This is an improper fraction. So what you want to actually do here is convert this into a whole number part and a fraction part, right? And that fraction part is going to be a proper fraction. And we remember how to do that, right? We take 53 and we would divide it by 40. So 40 goes into 53 once. 1 times 40 is 40. Subtracting, we get 13. We would have 1 and 13 over 40 as our mixed number there. So let me erase all of this. And we're going to go back up to the top. And I'm just going to rewrite this right here. 9 plus 13 plus 2 plus. I just found out that the result from adding the fractions was 1 and 13/40. So I'm going to put a 1 here to add along with my whole numbers, and then plus 13 over 40. This fraction part I don't need to do anything else with. So now I'm just going to add these whole numbers together. 9 plus 13 is 22. 22 plus 2 is 24. Then 24 plus 1 is 25. So I would have 25 plus 13 over 40. And again, as a mixed number, we just write this as 25 and 13/40. Okay, now let's look at some subtraction problems. And really, when you work with subtraction problems, they're not any more difficult, except for the simple fact that sometimes you'll be subtracting fractions, and the fraction you're subtracting from is too small. So you have to do a little bit of borrowing, and we're going to come across that in the next problem. So we're going to start out with 23 1/3 minus 20 1/7. So again, what I'm going to do is I'm going to subtract the fraction parts first, and then I'm going to subtract the whole numbers. So in other words, I'm going to take 1/3 and I'm going to subtract away 1/7. Now you have to do it in that order here because remember, subtraction is not commutative like addition. So I'm going to take 1/3 and I'm going to subtract away 1/7. Now to do this, I need to get a common denominator going, and my LCD here would be the product of the denominators, 3 times 7. And that's because 3 and 7 are both prime numbers. So I'm going to multiply this by 7 over 7. I'm going to multiply this by 3 over 3. And we're going to end up with 7 over 21 minus 3 over 21. And that's going to give me 4 over 21. Right? 7 minus 3 is 4 over the common denominator of 21. So now that we know the fraction part, we only need to subtract the whole number part. And again, I have to be specific about how I do it. It's 23 minus 20. If I do it in a different order, I'll get the wrong answer. So 23 minus 20 would be 3. So what we end up with is 3 for the whole number part, and then 4 over 21 for the fraction part. All right, let's take a look at another subtraction one. So we have 14 and 3/5 minus 5 and 13/15. So we would start this problem out the same way. So we do 3/5 minus 13/15, right? Just subtract your fractions first, get that out of the way. What's going to happen is you're going to find out that 3/5 is smaller than 13/15. So the result of this is going to be a negative number. Now we don't want that. So what we're going to do is we're going to end up borrowing from the whole number part. So let me show you how to do that. The first thing I'm going to do is pretend that I don't know that this number is smaller. So I'm going to start out by saying, okay, the LCD between the two fractions is 15. So I'd multiply this by 3 over 3. And what would happen is I'd see that, okay, I have 9 over 15 minus 13 over 15. And I'd say, okay, this is going to result in negative 4 over 15. What do I do now? Again, to correct this, I'm going to borrow. So instead of having 14 there, I'm going to rewrite this and say that this whole number is going to be 13. And instead of 3/5, what I'm going to do is I'm going to add 5/5. So that's where this 1 went. I took 1 away, and I basically said, okay, instead of having 14, I now have 13. That 1, where it went, I wrote it as 5/5, and then I'm adding that to 3/5. So essentially my fraction part now is going to temporarily be 8/5, right? So you can just think of this as having 13 and 8/5. And that's not how we write mixed numbers, right? We always want a whole number and a proper fraction, but we're just doing it so that we can perform our operation. So if I have this as 13 and 8/5, now when I look to subtract the fractions, what I'm going to have is I'm going to have 8/5 minus 13/15. Again, the LCD is still going to be 15, so I'd multiply this by 3 over 3. And what we'd end up with now is we'd have 3 times 8, that's 24, over 3 times 5, that's 15, minus 13 over 15. And you can see that 24 is bigger than 13, so you can do the subtraction and not get a negative number. So 24 minus 13 is going to give us 11. So this ends up being 11 over 15 for our fraction part. Now, when we subtract the whole numbers, now we have a different whole number to work with. Because we lent 1 to our fraction, we no longer have 14 as our whole number part, we have a 13. So we have to keep that in mind. So we would do 13 minus 5, and 13 minus 5 is going to give us 8. So 8 and 11/15 would be our answer. Okay, let's take a look at another one. We have 12 and 4/9 minus 8 and 7/8. So again, when I have a subtraction problem and I'm working with mixed numbers, I'm going to try to subtract my fraction part first, and then I'm going to worry about the whole numbers. So I would subtract 4/9 minus 7/8. 4/9 minus 7/8. Again, you got to do it in that order because subtraction is not commutative. Now, when I look here, I see that 9 and 8, they're not going to have any common factors, right? 9 is 3 times 3. 8 is 3 factors of 2. So really the LCD here is going to be the product of the two denominators, or 72. So I'd multiply this by 8 over 8, and I'd multiply this by 9 over 9. And when you do this, you see you have a problem, right? 8 times 4 is 32. So this would be 32 over 72. Minus 7 times 9, that's 63 over, again, 72. So when we perform this subtraction, we end up with a negative result. And although we can do it that way, it makes it more complicated. So to keep things nice and simple, let's erase all this. And I just want you to, again, temporarily think about this. We're going to borrow 1 from this whole number. So instead of 12, I'm going to have 11. And so this 4/9 here, I'm going to just temporarily add 1 to that 4/9, but just using fractions. So instead of 4/9, if I add 1 in fractional form, I'm going to add 9/9, and that's going to give me 13/9. So instead of having 4/9 there, I basically have 13/9. And again, this is now 11 for the whole number part. So now if we subtract fractions, I would do 13/9 minus 7/8. we're going to have the same LCD. So I'm going to multiply this by 8 over 8. I'm going to multiply this by 9 over 9. And let me just scroll down here so we have a little room. 13 times 8 is 104. And this would be over 9 times 8, that's 72. Then we'd subtract away 7 times 9, that's 63. Over 8 times 9, that's, again, 72. 104 minus 63 is 41. And this is over the common denominator of 72. So the result of subtracting the fractions would give us 41 over 72. So this is 41 over 72 for that part. And now we just subtract the whole numbers. So remember, I don't have 12 anymore because I borrowed to do my subtraction with the fractions. So I have an 11 here, and then I'm just subtracting away 8. 11 minus 8 would give me 3. So we'd end up with 3 and 41 over 72 as our answer. So now we're going to start doing some multiplication and division. And we're going to change something up here. Now, when you add or subtract mixed numbers, generally what everybody's going to say is to add or subtract the fraction parts first, then add or subtract your whole number parts. Now, alternatively, if you wanted to, when you add or subtract mixed numbers, you could have converted those mixed numbers into improper fractions, perform the addition or subtraction, and then you can convert them back to mixed numbers if you have to. It's totally up to you which way you want to do it. It's just usually faster to do it the way that I showed you. Now, when we multiply or divide mixed numbers, we're going to convert each mixed number into an improper fraction. Once we're done, if it's required, we'll convert the answer back to a mixed number. Sometimes your teacher won't tell you to convert it back. You can just leave it as an improper fraction. Whatever they want you to do, just follow the instructions you're given. So we're going to start with 5 2/5 times 3 1/7. So what I'm going to do is convert each of these into an improper fraction. 5 times 5 is 25, plus 2 is 27. So I'd have 27 fifths times 7 times 3 is 21, plus 1 is 22, over 7. So again, when I multiply, I always look to cross cancel first. There's no common factors between anything here, so I just do the multiplication. 27 times 22 is going to give me 594. And this is over 5 times 7, which is 35. So our answer here is 594 over 35. Now, like I said, if you wanted to, you can leave this as an improper fraction. If your teacher makes you, convert it back to a mixed number. So let's do 1 or 2 where we convert it back, and then we'll just leave them as improper fractions moving forward. So 594, we're going to divide that by 35. 35 goes into 59 once. 1 times 35 is 35. Subtract here, 9 minus 5 is 4. 5 minus 3 is 2. Bring down the 4. 35 is going to go into 244 6 times. 6 times 35 is going to give us 210. Subtract here. 4 minus 0 is 4. 4 minus 1 is 3. So that's going to give us 34 as the remainder. So as a mixed number, this would be 16 and 34 over 35. Okay, for the next one, we have 8 elevenths times 4 1/2. So I'm going to keep 8 elevenths unchanged. That's already a fraction. And I'm going to multiply by 4 1/2 after I convert it into an improper fraction. 2 times 4 is 8, plus 1 is 9. So we'll have 9 halves here. We look to see what we can cross cancel. I know that 8 is divisible by 2. 8 divided by 2 is 4. So just think about canceling a factor of 2. That would give me 4. Cancel a factor of 2. That would give me 1. So now I basically have 4 times 9, that's 36. Over 11 times 1, that's 11. So I get 36 elevenths as my answer. Now again, for the last time, we're going to convert this into a mixed number. Again, this is something you should already know how to do. So if your teacher requires it, go ahead and do it. But again, a lot of teachers will just say, however you get the answer, as long as it's simplified, it really doesn't matter. So 36 divided by 11. 11 goes into 36 3 times. 3 times 11 is 33. Subtract and get 3. So if we write this as a mixed number, we'd have 3 and 3 elevenths. 3 and 3 elevenths. Now we have 4 2/5 times 6 1/4. So I'm going to convert each into an improper fraction. 5 times 4 is 20, plus 2 is 22. So we'd have 22 over 5 times, for this one, 4 times 6 is 24, plus 1 is 25. And that's over 4. And we can see we can do some cross canceling here. I know that 25 is divisible by 5. 25 divided by 5 is 5. So this will cancel out completely and become 1. This will cancel, become 5. 22 is divisible by 2, and so is 4. So 22 divided by 2 is 11. 4 divided by 2 is 2. So now we have 11 times 5, that's 55. Over 1 times 2, that's 2. So we end up with 55 halves as our answer. Let's take a look at a few division problems now. So we have 8 and 2/9 divided by 7 and 1/2. Again, what I want to do is change each of these mixed numbers into an improper fraction, then do the division. So 8 and 2/9, I'm going to change this. 9 times 8 is 72. 72 plus 2 is 74. And this is going to be over 9. And we're dividing by 7 and 1/2. 2 times 7 is 14. 14 plus 1 is 15. So that's 15 halves. And again, if you're dividing fractions, the first fraction or the left fraction stays unchanged. So 74/9, we don't do anything to that. Then we're going to multiply by the reciprocal of 15 halves. So that's going to be 2/15. And we look to see if we can cross cancel anything. Nothing I can really do here. 74 is not divisible by 3 or 5, so I can't really cancel anything. So we just multiply. 74 times 2 is 148. And this will be over 9 times 15, which is 135. So my answer here is 148 over 135. All right, for the next one, we have -6 divided by 2 and 1/8. So we have -6, and since we're dealing with fractions here, I'm going to go ahead and write that as -6 over 1, and then divided by, I'm going to convert this into an improper fraction. 8 times 2 is 16, plus 1 is 17, so you'd have 17 over 8. Again, to divide fractions, this leftmost fraction, -6 over 1, will stay unchanged, and we'll multiply by the reciprocal of this fraction, so times 8 over 17. So nothing I can cross cancel here, so I just need to multiply. -6 times 8 is -48, and this is over 1 times 17 or 17, so we get -48/17 as our answer. All right, final problem. We have 2 and 1/5 divided by 4 and 1/3. So again, I'm going to convert each into an improper fraction. 5 times 2 is 10, plus 1 is 11. So this will be 11/5. And then divided by 4 and 1/3, I'm going to have 3 times 4, that's 12. 12 plus 1 is 13. And then over 3. So 11/5 times the reciprocal of 13/3 would be 3/13. Nothing to cross cancel. 11 times 3 is 33. 5 times 13 is 65. So we'd have 33 over 65 as our answer. Hello and welcome to Pre-Algebra Lesson 38. In this video, we're going to learn about complex fractions. So the lesson objective for today is to learn how to simplify a complex fraction using 2 different methods. So before we kind of get started, let me just give you a basic definition for a complex fraction. A complex fraction is a fraction that contains at least one fraction in its numerator or denominator. It could have a fraction in its numerator and denominator as well. So let's start out by looking at a problem. So here's a complex fraction. We have 1/5 plus 2/5 over 1/3 plus 4/3. So notice how we have an operation in the numerator and in the denominator, and there's fractions in both the numerator and the denominator. So one way you can simplify this is to simplify the numerator and the denominator separately, and then you're going to have a main division. This is going to be your main division for the complex fraction. So if we kind of go through here, and let me just erase this real quick. If we kind of go through here and simplify the numerator, we already have a common denominator. So we have 1/5 plus 2/5. We would just add 1 plus 2, that's 3. Put that over the common denominator of 5. And then in the denominator here, we have 1/3 plus 4/3. Again, we have a common denominator, so we can do 1 plus 4, that's 5. Put that over the common denominator of 3. So at this point, we have a complex fraction that's nothing more than a division problem. We have 3/5 basically divided by 5/3. So if you saw that problem written this way, you would know that you take 3/5 and leave it unchanged, and you're going to multiply by the reciprocal of the second fraction, which is 3/5 as well. So you're going to do the same thing here. You just got to get used to looking at it differently. We have 3/5 again divided by 5/3. So 3/5 is going to stay the same. And we're multiplying by the reciprocal of what we're dividing by. So the reciprocal of 5/3 again is 3/5. And we just multiply. 3 times 3 is 9. 5 times 5 is 25. So we get 9/25 as our answer. All right, for the second problem, we have kind of an easier one. This is basically just a division problem. We have 4/15 over 12/13. This is the problem 4/15 times the reciprocal of what we're dividing by. So times 13 over 12. Now I can cross cancel here. The greatest common divisor between 4 and 12 is 4. So if I divide 4 by 4, I get 1. If I divide 12 by 4, I get 3. Nothing I can really do between 13 and 15. So we'd end up just multiplying here. 1 times 13 is 13. Over 15 times 3, that's 45. So this is going to simplify to 13 over 45. All right, let's take a look at 5 plus 3 halves over -2. So again, we're going to work by simplifying the numerator and denominator separately. Our denominator here is simplified already, so I can just kind of copy that. I don't need to do anything. For the numerator, if I have 5 plus 3 halves, I got to get a common denominator going there. So I can write 5 as 5 over 1, and the least common denominator I'm going to be able to form here is going to be 2. So I can take 5 over 1 and multiply it by 2 over 2, and I'm going to add that to 3 halves. So continuing, 5 times 2 is going to be 10. That's going to be over 2 plus 3 halves. And I'm just going to copy this denominator for the complex fraction. That's -2. And I'm going to continue down here. But in the numerator of the complex fraction, I have a common denominator now of 2. So I'm just going to add the numerator. So 10 plus 3 is 13. So that's 13 over 2. And basically we could say this is divided by or over -2. Now to make this easy on ourselves, I'm going to write -2 as -2 over 1. So now I can see this problem as 13 halves divided by -2 over 1. So again, it's just a division problem at this point. This fraction here, 13 halves, will stay unchanged. And I'm going to multiply by the reciprocal of -2 over 1, which would be 1 over -2, or you could put -1 over 2. It doesn't really matter. Nothing to cross cancel, so we just multiply. 13 times -1 is -13. 2 times 2 is 4. So you get -13/4 as your answer. All right, let's take a look at another one. So we have 3/7 minus 5 over 21. That's the numerator for the complex fraction, and this is over. You have 5/8 plus 2/5. So this one will be a little bit tedious to work through. So let's kind of just simplify the numerator here, and then we'll work on the denominator in a minute. So we have 3/7 minus 5 over 21. So we got to get a common denominator going. And the least common denominator we're going to be able to form is going to be 21, right? 21 is 7 times 3. Here we just have a 7. So what I'll do is I'll multiply 3/7 by 3 over 3. That'll give me a denominator of 21 there. Then minus 5 over 21. So 3 times 3 is 9. So we'll have 9 over 21 minus 5 over 21. That's going to give me 4 over 21. So my simplified numerator for the complex fraction is 4 over 21. So I'm just going to write up here that this is 4 over 21, and then over. Let's figure out what the simplified denominator for the complex fraction is going to be. So we have 5/8 plus 2/5. So 5/8 plus 2/5. Now, to find the LCD here, 5 is a prime number, and 8 is 3 factors of 2. So the LCD is basically found by multiplying 8 times 5. That would give you 40. So what I'm going to do is I'm going to take 5/8 and multiply by 5 over 5. And I'm going to take 2/5 and I'm going to multiply by 8 over 8. So 5 times 5 is 25. And of course this is over 40, right? 8 times 5 is 40. Then plus 2 times 8, that's 16. And again, this is over 5 times 8, which is 40. So 25 plus 16 is going to be 41. And then the common denominator is 40, so this is over 40. All right, so we have 41 over 40 here. So my simplified denominator, again, is 41 over 40. So now we basically have a division problem. We have 4 over 21 divided by, or over, 41 over 40. So to divide this, we take 4 over 21, leave that unchanged. We multiply by the reciprocal of what we're dividing by. So the reciprocal of 41 over 40 is 40 over 41. And we can see that we can't really cross cancel here because 4 is 2 times 2, 41 is a prime number. 21 is 7 times 3, and 40 is 2 times 5, times 2 times 2. So nothing I can cancel here, so I just multiply. 4 times 40 is 160 over 21 times 41, and that's 861. So we're going to end up with 160 over 861 as our answer. So let's take a look at 5 minus 1/9, and then this is over 3. So I'm going to write this as 5 over 1 because I'm working with fractions. And I'm going to multiply 5 over 1 by 9 over 9 so that I can have a common denominator of 9. So then minus 1/9, and this is all over 3. So 5 times 9 is 45, so this would be 45 over 9 minus 1 over 9, and then this is all over 3. Continuing down here, in the numerator of the complex fraction, I have a common denominator now, so I would do 45 minus 1, that's 44, over the common denominator of 9, and then this is divided by or over 3. Now when we work with fractions, I like to have fractions everywhere because it makes it easier to think about what I'm doing. So instead of just having a 3, I'm going to write 3 over 1. So I can see the division problem is 44 over 9 divided by 3 over 1. That's easy to do. So we have 44 over 9, that stays the same. And we multiply by the reciprocal of 3 over 1, which is 1/3. So 4 plus 4 is 8, so it's not divisible by 3. So there's not really anything I can do to cancel here. So I just go through and multiply. 44 times 1 is 44. 9 times 3 is 27. So we end up with 44 over 27 as our answer. So alternatively, we can find the LCD of all denominators involved, then multiply the numerator and denominator of the complex fraction by the LCD. So when I say multiply the numerator and denominator of the complex fraction by the LCD, you have to pay close attention to that. And I'll show you why in this example. So we have 4/5 over 2/5. So what's my LCD here? Well, the denominator of this fraction is 5. The denominator of this fraction is also 5. So the least common denominator is going to be 5, right? Because they both have the same denominator. So when we say we're going to multiply the numerator and denominator of the complex fraction by 5, I'm essentially saying I'm going to multiply this part here by 5, and I can do by 5 over 1 if it makes it more convenient, and then this part by 5 as well. Right? This is the numerator of the complex fraction, this is the denominator of the complex fraction, and each part gets multiplied by 5. Again, this is legal because I'm multiplying by 5 over 5, which is 1. So if you go through, what's going to happen is this 5 will cancel with this 5 will cancel with this 5, and I will be left with 4 over 1, which is 4, divided by 2 over 1, which is 2. Right? So I can keep it like this in fractional form, or I can rewrite it if I want and just say this is 4 divided by 2. Right? Because this way I would have 4 over 1 times the reciprocal of 2 over 1, which is 1/2. It's the same thing as 4 over 2. Right? So when we do this division, 4 over 2, or 4 divided by 2, is 2. All right, here's one that's a little bit more complicated. We have 1/4 plus 3/5, and this is over 3/8 plus 5/12. So look at all your denominators involved. You have a 4, a 5, an 8, and a 12. So what's your LCD here? Again, this is the LCM for 4, 5, 8, and 12. So if you think about what we're going to put in the prime factorization for the LCM, 4 is 2 times 2. 5 doesn't factor, so it just goes in. 8 is 3 factors of 2. I already put 2 factors of 2 in, so I only need to put in the largest number of repeats between any of the prime factorizations. So I'm just going to add 1, 2 in there. Then 12 is 4, which is 2 times 2, that's already accounted for, times 3. So I'm going to put times 3. That's all I need to add to it because I already have 3 factors of 2 in there. So if I multiply this out, 2 times 2 is 4, 4 times 5 is 20, 20 times 2 is 40, 40 times 3 is 120. So now what we're going to do is we're going to multiply the numerator of the complex fraction by 120. And you can do, again, 120 over 1 if that makes it more convenient for you. And you're going to multiply the denominator of the complex fraction by 120 also. So what is this going to give us? We have to use the distributive property here because you have some addition going on. So 120 times 1/4. Think about what that would be. So 120 basically over 4, and that would be 30. So I'm just going to write this over here. This would be 30 plus, next you'd have 120 times 3/5. So 120 times 3/5. And let me write this over 1 to make it a little bit more convenient. So I can cross cancel 120 with 5. I know 120 divided by 5 is 24. So this cancels with this and gives me 24. And then 24 times 3 is 72. So the denominator is gone. You can put it over 1 if you want, but basically it's gone. So we're just going to put a 72 there. And again, if you wanted to write 30 over 1 plus 72 over 1, you can, but it's just completely unnecessary. So we'll just write it like this. And then our denominator, again, we're going to do the same thing. We're going to multiply 120 times 3/8, and then we're going to add to that 120 times 5/12. So for 3/8 times 120, and again, we can put 120 over 1 if we want. 120 divided by 8 is 15. So I can cancel this with this and get 15. 3 times 15 is 45. So you'd have 45 over 1 or just 45. And then plus, again, we're going to multiply 120 times 5/12. So we'll have 5/12 times 120. Again, you can put that over 1 if you want. 120 divided by 12 is 10. So this cancels with this and gives you 10. 5 times 10 is 50. And again, you can put that as 50 over 1 if you want, but I'm just going to put 50. So now we have 30 plus 72, and I'm going to write that down here. That's going to be 102 over 45 plus 50, and that's going to be 95. So our fraction has been simplified to 102 over 95. Okay, let's take a look at one more like this. We have 3/5 plus 1/2, and this is over 5/6 minus 1/3. So look at your denominators involved. You have a 5, a 2, a 6, and a 3. So what's the LCD? Well, it's going to be the least common multiple of 5, 2, 6, and 3. So again, 5 doesn't factor, so that goes in. 2 doesn't factor, that's going in. 6 is 2 times 3. I already have a 2, so I'm just going to put a 3 in. And then 3, we already have that in there. So 5 times 2 is 10. 10 times 3 is 30. So that's going to be your least common denominator. And so again, what we're going to do is we're going to multiply the numerator of the complex fraction by 30. And I'll put times 30 over 1. And we're going to also do that to the denominator. So times 30 over 1. And again, if I multiply by 30 over 30, I'm multiplying by 1. I'm not changing the value of the fraction. I know it looks more complicated, but really you're still doing the same thing. You're multiplying by a complex form of 1. So again, we're going to do this using the distributive property. So we would have 30 over 1 times 3/5 to start. So 30 divided by 5 is 6. So I cancel this with this and get a 6. 6 times 3 is 18. So this would be 18 over 1, or just 18. Then plus. Next, we're going to have 30 over 1 times 1/2. And I can do this down here, but basically we know that we would have 30 divided by 2 in that case, right? Because we're just saying, what is half of 30? That's 15, right? 30 divided by 2 is 15. So I'll put a 15 here. And this is over. Next, we have 30 over 1 times 5/6. So 30 over 1 times 5/6. So I know that 30 divided by 6 is 5. So cancel this with this, and I'll get a 5. 5 times 5 is then 25. Then minus. Next, I'm going to do 30 over 1 times 1/3. So 30 over 1 times 1/3. 30 divided by 3 is 10. So this would cancel and become 10. And I'm just left with 10 times 1, or 10, over 1, which we can just write as 10. So simplifying this, I have 18 plus 15, which is 33, over 25 minus 10, which is 15. Now I'm not done because I always want to report a fraction in its simplest form. I know that there's a common factor of 3 between 33 and 15, right? 33 is 3 times 11, 15 is 3 times 5. So really, if I just divide each by 3, I'm going to end up with 11 over 5, or 11/5, as my final answer.